Good morning, everyone. Thank you for joining us this morning for the Biogeochemistry Working Group session. My name is Keith Lindsay. I am the Working Group Community Liaison. The Working Group co-chairs, Abby Swan, Gretchen Keppel-Alex, and Matt Long are all unavailable, so we're going to the second string here. Myself and Charlie Coven are going to help moderate the meeting. We've allocated 15 minutes for every speaker, so I think the game plan is 12 minutes of talking plus a few minutes for questions and transition to other speakers. The speakers in the beginning part of the session before our break are all going to be online, so fingers crossed things work technically well. To advance the slide. There we go. At NCAR, we try to have respectful dialogue, so please adhere to these principles so that we have a constructive environment for all participants. With that said, our first speaker is Min-Hui Lo, who is remote. And Fletcher is our AV guy, is going to operate the computer for the technically challenged liaison. So Min, can you please share your screen?
Yes, can you hear me now?
Yes, we can hear you now. Thank you for checking.
Can you see my screen now?
Yes. Looks good here on site. So take it away, Min.
Okay, great. Thanks. Thanks, Keith, and good morning, everyone. This is Min-Hui Lo from Department of Agricultural Science, National Taiwan University. So today I would like to share some of the recent work in my group, try to using CESM to explore how the deforestation induce the land and atmosphere interactions. So basically, I will split to two parts. First of all, try to understand how the role of forests in moderating the local interannual evapotranspiration variations. And the second part, I will talk a little bit about the mean state dependence of deforestation-induced rainfall changes. And then the region target will be in the Southeast Asia, these are maritime continent regions. So first of all, the first part, the role of forests in moderating the ET variations. So from our previous studies that precipitation decreases that from neutral conditions compared to the El Nino conditions. So we know that because under the El Nino conditions in maritime continent regions will be a substance anomalies. So usually the precipitation decreases. However, if we look at the evapotranspiration, and usually if we sum up them, it actually increases a little bit, especially the canopy transpirations increases more when compared to the evaporation. Canopy evaporation a little bit decreases, but in some we still can see in general the evapotranspiration increases. So this is from the prescribed sea surface temperature simulations. So further, we try to use observational or kind of reanalysis data, try to see whether this phenomena still exists. So here we use precipitation from GPCC and evapotranspiration from Era 5 then, and also we use glimpse data, but today's result I will show in Era 5 only. And then later on, the result I will show is differences between El Nino and La Nina, try to show the internal variations by this way. Because under these regions, the El Nino minus La Nina conditions usually will see a precipitation decreases. But we want to know whether the evapotranspiration increases or decreases under these climate conditions. So this is the bar chart shows that the precipitation decreases, as we know already, but the evapotranspiration also decreases from observation or from area 5 land. But if we see the partitioning from canopy evaporation and canopy transpiration or soil evaporation, we see this compensating effect, so that when we see the precipitation changes compared to the original climatology, it decreased about 23%. But in terms of evapotranspiration, it decreased only about like 1.3%. So that we try to argue that this ET, because of this partitioning compensating effect between transpiration and evaporation, so that evapotranspiration is internal variation is very small. So further, we try to use CLN, NCAR-CLN, try to test whether this how the forest can damp these ET variations. So we kind of conduct idealized experiments using CLN under the prescribed atmosphere forcing, so which is offline simulations. So the control run is like originally the rainforest, but under the deforestation run, we kind of cut out all the trees represent as a bare soil. And again, later on, we try to see the differences between the El Nino and La Nina. The simulation result is from 1981 to 2014. So we have several big El Nino and La Nina years can be used to see their responses. And this is the results from using CRU V7 forcing. We also use GSWP3 forcing, and the results are similar. So here I will show the result from CRU V7 forcing. And as you can see, like under the control simulation, which is under using which is the land type is rainforest, so the evapotranspiration also decreases, but with this large compensating effect between canopy evaporation and canopy transpiration. So similar from what we've seen from the area 5 land data set. But under the deforestation experiments, as we can see that this compensating effect is gone because right now there is no forest. So the canopy evaporation or canopy transpiration becomes minimal. So under the El Nino conditions, the soil evaporation kind of dominates the decreasing part. So this result in this ET decreases significantly compared to when the forest exists. So this is something we found from the sensitivity test, but this is offline. So further, we try to use a couple model simulations. Here we use the CESM2 fully coupled, the ocean and atmosphere are involved. We have 40 ensemble years, which including El Nino and La Ninas. So again, in these fully coupled simulations, we try to see the differences between El Nino and La Nina. And this is a result that the precipitation also decreases, of course, under the El Nino condition compared to the La Nina condition. And the canopy, the total evaporation under these control simulations decrease only a little bit. And again, it's due to the compensating effect between the canopy evaporation and the canopy transpiration. However, under the deforestation case, which is with the bare soil PFT, then this compensating effect is gone as well under these fully coupled model simulations. So the soil evaporation decreases because the precipitation right now under El Nino is lower, so the soil is drier. So there is less soil evaporations. So resulting in this lower total evapotranspiration under the El Nino conditions. One thing I want to note is that, as you can see in this precipitation changes under the deforestation case, actually you see a lower precipitation decreases when compared to El Nino versus La Nina. So this means that under the deforestation case, the El Nino versus La Nina, their variations are become smaller. So this is something different from what we see about these ET variations. So in other words, the total ET variation becomes larger under the deforestation case, but the rainfall is a different story. It seems to become a little bit smaller. So the second part is that we want to explore a little bit further why these precipitation variations or interannual variations become smaller after deforestation. So this leads to our second part. So the precipitation under the neutral conditions or like normal years after deforestation from our previous studies, actually in the maritime continental regions with the deforestation, the precipitation increases. However, it increases more under the El Nino conditions. So in other words, that it seems that there is a negative feedback under the drier conditions that the precipitation can increase more under the deforestation cases. So here we again use fully coupled simulations. Try the green color here shows where the forest has been replaced with the bare soil. And the ensemble members here, we try to use macro perturbations. So we select several El Nino initial conditions and also several La Nina initial conditions. Try to understand the differences between the El Nino condition and La Nina conditions when there is a deforestation, how they respond. And this is a result here. We show that there are 40 cases. So we try to select with the precipitation changes between the deforestation run and control run. The increase is the most first quartile, and then the increase the last quartile. Actually, it become like precipitation decreases in these 40 cases. So if we compare to the original control run, we found that the increase is more after the deforestation. We found that their control simulations precipitation actually has less climatology of the rainfall. On the other hand, when the climatology rainfall in the control simulations has higher precipitation, it actually will induce lower precipitation after the deforestation. So if we look at their moist static energy vertical profiles, you will see the red curves here is the increases higher rainfall after the deforestation. On the other hand, with this blue curve of vertical profile of the moist static energy, it actually will lead to less rainfall increases. And in fact, it actually resulted in a decrease of rainfall. So in other words, when the original vertical profile of this MSE is in this negative concave, and because of the higher MSE in the lower atmosphere layer, so it actually induced more moist static energy transport to the mid and low level atmospheres. So in this case, it actually induced more rainfall compared to original this kind of positive concave of the MSE profile. So here we try to argue that a group with greater anomaly precipitations, the climate state in this control run tend to be drier, and this actually implies a negative feedback between the control simulations and the anomaly precipitation. So this is a schematic plot that we try to show that if originally with this negative concave type of MSE, it actually is drier conditions. So its control simulation has a smaller precipitation. But after deforestation, actually it will increase a greater increase in precipitation. On the other hand, when the when there is a passive concave type of the control simulation, actually it usually has the greater precision, but after deforestation, it usually has a smaller increases in the precision. So the take-home message here is that after deforestation, the group with the negative concave MSD means they tend to cause a stronger increase in precision. So here is my quick two summaries that evapotranspiration variability actually will amplified after the deforestation, but the deforestation actually induced this negative impact on the local precipitations. So the local rainfall actually is internal variations will become smaller after the deforestation. So it's kind of different from what we found in the evapotranspiration responses. With that, I would like to take any questions. Thanks for your attention.
Summary as far as which modes are well represented versus not. The ENSO temperature.
We have questions?
Minwi, this is very good presentation. So for the first part, is that you would expect from the current level of the forestation that when it is dry, it can extract water from the deeper root and then it can compensate for some of the precipitation decrease, and then correspondingly it increases the transpiration part, but the canopy evaporation decreases because the precipitation is less. So does that mean the current landscape offers a resiliency against this kind of interannual climate variability? Or is it my interpretation is correct or not?
Yeah, that's what I thought after we found this result, that the forest over the trees seems like play a compensating role here, that it can actually extract more water from the deeper layers under its dry conditions. So provide or kind of stabilize the evapotranspiration under the dry conditions. Yeah, so I think your interpretation is similar to what we found here. Yeah.
All right. Thanks a lot, Minwi. I guess
Sure.
if you could stop sharing, and then Thomas Cavu is up next. Thomas, if you're on, could you start sharing? All right, great. Yeah. So up next is Thomas Cavu. Thanks, Thomas.
Can you hear me?
Yes, we can hear you.
Okay, everything is good. Okay. Thank you, everyone. Today I'm going to be presenting a portion of my research, and we are going to be talking about parameter sensitivity study of the NCAN simulation tool in the Southeast United States. And I have to mention a special appreciation and acknowledgement to my supervisor, Dr. Sajiv Kumar, and Dr. Daniel Kennedy. I am from the College of Forestry and Wildlife and Environment at Auburn University. Thank you. I welcome you to follow through my presentation. So an introduction to my study is that estimates of change, especially with evapotranspiration, are key to understanding the terrestrial hydrological cycle and the changing environments. And when we talk of these complex earth system processes, we talk about representing them in models, and most of these models, they have increasing complexity and comprehensiveness, and this leads to more uncertainty because we have the representation of different processes within these models, and this results to significant biases when estimating water carbon cycle processes. And as you can see just from this particular diagram, we have a simulation and an observation of evapotranspiration in one of the National Ecological and Observatory networks that is tall. And from the diagram, you can see the black line that represents the observation. There is a significant bias between the model output and the observations. And today we are going to look at some of the key parameters that attribute to such differences. And motivation for this study is growing complexity and uncertainty. Land models increasingly complex and comprehensive. And we can see from this diagram that there are so many parameters and processes represented in most of the Earth system models, which the CLM is one of them. And this results to increasing number of uncertain parameters, which poses a challenge to accurate simulations. And the other motivation is that the parameter uncertainty is not yet quantified, and the extent of this uncertainty remains a big challenge to research, because if we don't understand how much or how large a process is affected by some of the model parameters or some of the model processes, then it becomes a big challenge to be able to interpret the result. And systematic parameter calibration for actionable science, that is implementing a systematic parameter approach, is crucial. This will help us to understand some of the key processes that drive certain variables such as evapotranspiration, gross primary productivity, and this will enhance the accuracy of simulations within these models. And the improved accuracy will increase the suitability and accessibility of CESM or any land service model for actionable science applications. That is
downstairs.
That is climate change mitigation. That is also in terms of planning and preparations for the risk mitigations. So in this particular talk of today, we're going to be specifically talking about the application or the integration of the NEON data sets into CLM. The NEON is a very robust and high efficient and frequency data sets that is recorded by the National Ecological and Observatory Networks, and the data presents a tool and itself, and it's very useful for land service model processes. And we see that when we use the NEON data, for example, the climate data, it can be used to drive CLM simulations, and we use the land use data to initialize and constrain model parameters, which leads to enhancement of model performance and fidelity in simulating real-world systems. From the map, we can see the spatial distribution of the NEON stations, which shows a significant and good coverage within the United States, which shows that there are data for different regions, ecosystems, different climate patterns, and this data can be used to run or can be used as control when you are dealing with especially flux exchange, things like aquatic processes, ecosystem processes, etc. So for this work, we are only focusing on 3 ecoregions, that is domain 7, domain 8, and domain 3. And domain 7, we are using the Talladega Forest NEON site. Domain 7, we are using the ORNL site, and for domain 3, we are using the OSBS site. And one of the key reasons why we are looking at these specific 3 regions within the southeastern United States is that some of the uncertainties, exaggeration in CLM are mostly notable in regions with dense vegetation, and these regions represent exactly that. And for domain 2 and 3, they represent a similar ecosystem, that is their needle leaf vegetation, and for domain 7 is deciduous vegetation. So in my work, I use about 30 parameters that affect different processes, including photosynthesis, hydrology, plant hydraulics, carbon nitrogen allocation, fixed uptake of nitrogen, service fluxes, and biomass heat storage. And these parameters are a combination of plant functional types, name list, and hard-coded parameters, and they were obtained from extensive literature review and from some of the ongoing experiments, especially the PPE experiment. These parameters were sampled using the Latin hypercube, and Latin hypercube has proven to be efficient and effective, especially when dealing with complex ecosystems. And this here is just a highlight of the differences between the Latin hypercube and the conventional Monte Carlo sampling method. And as you can see from the red dot, it just shows random samples. But when you look at the Latin hypercube sampling, it shows that every space is covered within the matrix. And this is just a clear indication of, despite the fact that the Latin hypercube uses fewer samples. It effectively samples the parameter space efficiently. And the method that we are going to use is that we are going to use a variance-based sensitivity analysis to determine the relative contribution of different parameters to the model output. And this work is a branch from my main work, which was on PPE, and we already had run simulations trying to constrain uncertainties. And then after doing all those simulations, because we have like 1,200 simulations, then we were like, okay, can we look at the parameter contributions to this particular, especially the ET and GPP. So we thought of using a variance-based sensitivity analysis, which quantifies the contribution of each specific parameter. And there is a method which was proposed by Razi, and it has, according to their work, the method is very efficient, and it is a data-driven approach in that we didn't need to run more simulations. We can just use whatever model outputs that we already have. And the method uses joint probability density function to analyze the data between, and then it correlates the input and output parameters. And it's a very efficient sensitivity analysis method as it calculates sensitivity indices without rerunning the model. And this is the outline of our work. We had the initial parameter file. Then from the subset of the 30 parameters, we sampled them using Latin hypercube, and we updated the default parameter file with each sample, and then created new parameter files from 01 to 400. That we had like 400 new parameter files. And then we had the initial, that is the default run. Then we cloned that run, update the username list file with a new parameter file, set up, build, and submit the new cases, spin it up for 200 years, and then do production runs for 4 years. And this work was done for each of the 3 sites. And this step was repeated for all the 3 sites. And then we do a global sensitivity analysis, because the way we were sampling, we were all doing the Latin hypercube is changing all the 30 parameters at once and creating files based on that. So our work is basically on varying all the parameters at the same time. So when we did the simulation, one of the key things we are trying to look at is what are some of the key parameters to gross primary productivity. And this matrix presents a result, and I organize the matrix in the y-axis, we have the parameters, and on the x-axis, we have the different processes that it affects. And just looking at the matrix, it's clear that photosynthesis-related parameters are key to GPP, that is gross primary productivity. And some of the parameters that stand out include the Jmax B1, we have the Medlin intercept, we have the SLA top, we have the PSI 50. And the question is, why do these parameters stand out? Like, why are they more important when it comes to gross primary productivity? And then we look at the Jmax B1. It's a parameter that is responsible for electron transport rate to light absorption. This is a key contribution or a key contributor to photosynthesis. The other thing is the Medlin intercept. It also affects the sensitivity of stomatoconductance to atmospheric CO2, also a key driver to photosynthesis. And PSI 50, it regulates water transport through plants. Kmax B1 is about water flow rate through plants, and the fruit leaf, it's about the carbon partitioning between above and below ground biomass. And all these factors, they are all either gas exchange, either water regulation, or up and below biomass. And these are key things that drive photosynthesis. And again, when we look at the latent heat flux, again, photosynthesis related parameters stand out. But now with the GPP, it was the Jmax B1, which was the main key factor. But now for the latent heat flux, we have the SLA top. We also have a new parameter, that is the leak canopy storage scala. And also looking at these parameters, we see the SLA top, it regulates, or it's the relationship between transpiration and absorbed light. And the leak canopy scala is about the canopy water storage, and the WCWJBO simulates the effect of temperature on the balance between rubesico-limited and light-limited photosynthesis. Again, either about gas exchange or water transport within vegetation. And interestingly, when you compare these two processes, that is the gross primary productivity and the latent heat flux, the sensitivities, the differences do not seem so significant in terms of the key drivers or the key parameters that drive these processes. And this matrix shows that we have the SLA top, we have the Jmax P1, the WC2WJBO, Medlin intercept, Lee canopy scala, and the PSI 50 as the key main parameters that contribute or drive these processes, and of which this output is from a global sensitivity analysis, but also it aligns with some of the existing work like that which sampled like one at a time. It also highlights some of these parameters as key parameters to these processes. And interestingly, some of the existing researchers has highlighted the Medlin slope as a key parameter to driving these processes. But interestingly, in our case, the Medlin slope does not seem to be a key or a significant parameter or input driving these processes. And we've been thinking maybe it's because of we used a constant carbon concentration. That might be the case, but we're still investigating to see why the Medlin slope is not very sensitive to either of these processes. And finally, understanding the sensitivity of CLM outputs to these parameters can inform the model calibration, in that once you know like the key parameters or the key variables that affect a certain process, then it can easily guide you in terms of model calibration, in terms of knowing what parameter to tune or what process to adjust. And also it improves our understanding of land atmosphere interactions and can lead to better predictions of ecosystem function and climate change impact. Thank you.
Any questions? If not, I have one. Did you see any differences between the sites in terms of the parameter sensitivity?
No, there are no significant differences. Most of them, they just highlight the same parameters within the P sites.
Great, thanks so much. Yeah, so I guess now if you could stop sharing. Up next is Ben Sanderson from Cicero in Norway.
Hey, can you hear me?
Yes, we can hear you, Ben.
Cool, awesome. Hi everyone, good morning. Very sorry I can't be there, it will be fun. So this is some work on CMIP, coupled carbon climate feedback interactions, which we've been doing with Charlie and with Abby Swan and Rosie, plus a few other co-authors over the last few years. And I'm going to try and tie together a few loose ends. And so the story started with a paper which Charlie led on a climate restoration experiment. So this is where the cumulative emissions curve follows a Gaussian, and so the emissions curve then follows the first derivative of a Gaussian. So the idea is this is like an idealized net zero transition. So at year 150, the emissions go from positive down to negative, and by the end of the experiment, you've removed all the carbon you've initially put in. And so the question is, like, how different from the pure expectations you would have from TCRE you get in this experiment. And so pure TCRE response would look like the cumulative emissions curve. You would have temperatures which go up, peak at year 150, and then come back down to zero at year 300. And so in the CESM2 experiments, there were a few differences from this expectation. So that this is the red curve at the bottom, shows temperature. There was a peak in temperature a little bit before net zero. And then you get this weird little cooling dip towards the end of the experiment, and then a long period where temperatures are greater than pre-industrial on a millennial timescale. And so this is to do with the different dynamics of the ocean thermal transfer in the positive and negative directions. But what I don't want to go into too much into the physical details today. What we're trying to look at here is whether we can have corrective terms for the TCRE relationship to account for these differences which we saw in Charlie's experiment. And so the second part of the story is a paper led by Stuart Jenkins, where they propose a first order correction to TCRE, where you have your initial TCRE term, so that's the kappa multiplied by delta G, so that's a constant multiplied by your cumulative emissions. But then you have a second term, which is like a long-term trend emergence, and so this is the average emissions over the entire experiment, and then multiplied by a time constant. So you get increasing warming over time, and so what this means is that even when you've reached net zero, there is the capacity for some models to show a continual warming or cooling trend over a multi-centennial timescale. Or another way of looking at it is that the emissions which are consistent with holding temperatures constant can be non-zero. And in Stuart's paper, he fits this to lots of different CMIP models and finds that this rate of emissions, which is consistent with no temperature increase, varies by model, and he calls this thing the rays. Okay, so those are two threads. Can we tie them together? So another way we can think about the rays is to think about things as a pulse response. So if you imagine we have a pulse of emissions, a delta function in the top curve here, then cumulative emissions would tell you that the warming which you would get associated with that pulse of emissions is a step function. So the dashed line here. And the rays correction means that step function gets corrected to also is associated with a long-term trend. Okay, so if we fit this to the behavior which we had in Charlie's models, in Charlie's experiments, so we now have the two terms, and then we use this as a simple climate model and fit it to the outcome of the experiment. We can explain the TCRE-like part, and we can explain the long-term warming part, which falls out of the dynamics of the fit. If you have slightly different responses in terms of the long-term carbon feedbacks and the long-term thermal feedbacks, but we can't represent two other features. We can't represent the fact that we hit net zero. We have peak warming before we hit net zero, and we can't explain this little cooling dip. So we need another term in our experiment. And so in order to think about what might be missing, we can go back to a set of pulse response experiments which were done in an idealized sense by Hughes et al. A decade ago. And these were pulses of a single pulse of carbon into the atmosphere, and then you look at how several Earth system models respond. And broadly, they show this step function response in temperature, and they show this long-term trend over between 100 and 1,000 years. But the other thing which differs from the step function is this behavior, these short-term transients in the first 20 years of the experiments. And so what this kind of tells us is that we need perhaps another term in our simple climate model to account for these short-term transients. So this is like how the system responds to the emissions which have happened in just the last few years. So the simplest way we can parameterize this is by having a moving average of the emissions which have happened in the last few years. So this is the little block which we have between years 0 and A in our pulse response fit. So we can adjust the height of the blip, and we can adjust the time scale A, and that's another parameter in our simple model fit. So now we have three terms. We have TCRE, we have rays, which is the long-term response, and we have this short-term adjustment which we call DARE. So now, if we try again to fit the output of Charlie's experiment to the restoration emissions curve, we're now beginning to resolve the two features we were looking for before. We can resolve the fact that we have peak warming slightly before net zero, and we resolve this slight cooling dip afterwards. And it's not perfect, but it's broadly capturing the first order or second order dynamics in the problem. And the nice thing about this is we can take this fit and then we can apply it to another experiment. And so there was a series of coordinated experiments called ZECMIP in CMIP 6. And they were looking at the dynamics of coupled carbon climate models in response to zero emissions by branching off the 1% CO2 run with zero emissions after they hit cumulative emissions of 1,000 petagrams of carbon. And the nice thing here is that the fits that we do from Charlie's experiment, when we apply it to this this emissions curve, which you get from the ZECMIP experiments, which is a gradual increase and then an instant cessation, we actually reproduce pretty well the dynamics of the temperature dynamics of how the model will respond. So we can take so this leads us to some confidence that we're sort of these three terms are sort of successfully capturing the temporal dynamics of how the system is responding with a minimal number of parameters. And so what this means in conclusion is that what we're calling TCRE at the moment should really be thought of as a mix of transient and permanent effects. And those transients, especially in CESM2, which is a little bit of an outlier here, are a pretty sizable fraction of the TCRE, and they decay away 50 to 70 years after the cessation of emissions. And so this maps on to what we've in ZEC world we've been calling ZEC 50, this initial relaxation after the emissions have ceased. But then in the long term, this long-term warming trend kicks in. And so we can think about what this means. Oh no, we can't, because I've left that out. But never mind. That's the basic point. We can also look at this in the cumulative emission space, and it explains the basic the basic dynamics which we see. So I'm going to move on to a second, if I've got time, a second short study, which is thinking about how the Grassi correction for how to treat managed land in terms of translating between UNFCCC accounting of carbon and the traditional ESM IAM accounting of carbon. I want to think about this from an Earth system model perspective. The Grassi paper was written primarily in terms of translating IAM scenarios between IAM output and UNFCCC accounting. And so UNFCCC accounting tends to the reason this adjustment needs to happen is that when countries submit their emissions, these are their emissions plus their land use, their active land use change plus a land use sink associated with managed land in within the domain. And so when we replicate the Grassi response and then we use this to separate out the land sinks and the carbon feedbacks in Earth system models, we can redefine the cumulative emissions relationship using UNFCCC accounting. So this is taking managed land as part of countries' emissions. And so that gives us potentially an alternative value of TCRE, which is directly relatable to the way that countries are currently assessing their emissions. So the red curves here are using UNFCCC accounting of cumulative emissions, and the black curves are using the traditional system model accounting of cumulative emissions. And so that means that we can, for each model in which performed 1% CO2 coupled experiments in C4MIP, we can look at the on the x-axis is the normal TCRE, the way we normally think about it. On the y-axis is what we're calling TCRE star, which is the response, the cumulative response of the system to emissions as they are defined in the UNFCCC. And so it's remarkably well behaved, really. There's this constant offset between TCRE and TCRE star of about 0.2 degrees C. Which means that for emissions, the way that we're currently defining them in an international context, you need to add on this amount, 0.2 Kelvin of warming per 1,000 gigatons of carbon. But what's more interesting, perhaps, is the way that uncertainties break down between the managed land and the pristine part of the land sink here. So on the left-hand side is the cumulative carbon uptake on managed land using the sort of pristine, using the mask of land which countries are currently defining as being managed. And the point to notice here is there's quite a lot more intermodal spread on the managed land plots amongst CMIP6 models than there is on the pristine land. And so what this implies is that when we do this correction when we do our accounting in the way that we're doing it in terms of initial international negotiations. We're transferring uncertainty from the Earth system response to the emissions. And also it's quite scenario dependent. So here's the managed land sink now annual for 3 different scenarios. And so the Earth system models agree pretty much on what it does for the high mitigation scenario, SSB 126. But then as you go towards the higher emission scenarios, there's more difference between the managed land sink in the 3 different models where we have enough data to piece this back together. And so in the very high warming scenario, there's quite a big difference between the managed land sink at the end of the century in CESM2 and IPSL, which are the end members of this of the distribution. And so yeah, so this it kind of means that that there's some interesting logic associated with whether countries are benefiting or not from using the managed land sink as part of their carbon accounting today, and whether that will continue to be an advantage to them is it changes as a function of scenario, and it potentially is subject to quite a large amount of model uncertainty. And so this final plot illustrates in the left-hand column the fact that if we take the traditional ESM accounting of the land sink, all of our uncertainty here is in the land sink itself, and the emissions are certain, at least the way they're defined in the scenario. But if we use the UNFCCC accounting, there's much more agreement on the globally integrated land sink, now excluding the managed land, but that uncertainty goes into the emissions. And so yeah, so we can potentially by specifying this TCRE star, we can provide a fairly easy way for countries to relate their current emissions to their temperature implications in the way that emissions are being defined, including the managed land sink. But this implies a transfer of uncertainty. And so very briefly, I also want to talk a little bit about CMIP 7, just to gain some community interest. Yep. Okay.
Maybe we can come back to this point in discussion, Ben, since a lot of it's going to be I think the question we want to motivate is precisely the one you were just about to touch on. So hopefully you can stay on until after the next 2 speakers.
Sure. Yep.
Great. Thanks, Ben. So up next is Daniel Kennedy, I believe, right? Is it Daniel or Abby? Daniel. Yeah. Up next is Daniel. Daniel, are you there? Awesome. Thanks, Daniel.
Yeah, I'm here. All right, yeah, so Thomas gave a nice lead into this. I'll be talking about biogeochemical cycling in the CLM PPE, so similar to kind of Thomas's stuff, but on the global scale. And I'll be talking about persistent uncertainty in the terrestrial carbon sink. So here's a plot of the terrestrial carbon sink accumulated over the historical period and then extended out to 2100 from CMIP 5. And over in this experiment, there was actually disagreement among the land models of whether the model's land would be a carbon sink or a carbon source over the course of the 21st century. CMIP 6, we're seeing a similar spread. We're now agreeing on the sign, but featuring a roughly equivalent spread. And this is what I mean by persistent uncertainty. So despite knowing that this was kind of an issue and land models weren't really able to make a ton of progress on this in between CMIP 5 and CMIP 6. And so what we're curious about in the context of the PPE is how much of this is structural uncertainty, different equations in the different models, and how much of this spread could be achieved by one model just by altering the parameters. And so for that, we did a perturbed parameter ensemble. So for perturbed parameter ensemble, just strategically varying parameters, running one or more simulations per parameter set. You could vary your parameters one at a time, or random, or Latin hypercube. And I think Thomas gave a nice introduction on that. So as a first pass, we varied the parameters one at a time. So we identified about 200 CLM parameters, defined ranges, so a minimum and a maximum value. We developed an ultra low cost CLM configuration so that we could affordably vary all of them. And we varied the parameters one at a time and did a simulation with the parameter at its minimum value and at its maximum value. And then what comes out of that is, which parameter affects which variable. And you can see, I guess the text is small here, but depending on the biome, we got different responses for leaf area index. And Will shouted this out yesterday, but we've got a nice diagnostics website, which has, a lot of plots like this for all sorts of different carbon cycle variables or biophysical variables. So I'd encourage you to check that out if you're interested in parameter effects in CLM. So off of that one at a time simulation, we switched over to multi-factor ensemble, where we're specifically focused on leaf area index. We picked leaf area index because it's challenging but tractable to calibrate. It's a foundational variable within the BGC version of CLM, and it has observational constraints. It's a fairly well-observed variable. Our experimental design, we subset out of those 200, we picked 32 relevant parameters for leaf area index, 500 simulations, and this is fully transient from 1850 to 2014. So by varying those leaf area index parameters, we got a pretty wide range of leaf area that came out of the simulations. This is the global one at a time response, and I'll just kind of take the range of the largest parameter and overlay it on what we got out of the Latin hypercube. And you can see that what we achieved in the Latin hypercube was a much wider spread than what we achieved in the one at a time. And this makes perfect sense because you're layering together multiple parameter perturbations, which can have multiplicative effects. And then from the one at a time response, you get a sense of the range of, for example, what Kmax influence on leaf area index, but you don't necessarily know the shape of that curve. So from the Latin hypercube ensemble, we see a very similar effect size, which is reassuring. But what we learn by having the Latin hypercube instead of one at a time is that there's a distinctly nonlinear parameter response to Kmax, which is very useful for calibration. All right, so how does LAI variance project onto other variables? This is something that I think is going to be our primary interest. So here's one example. This is on the x-axis, global leaf area index, and on the y-axis, global photosynthesis, gross primary production. And it makes sense, right? So ensemble members that have low leaf area index tend to have low photosynthesis. So when we alter the parameters that results in low leaf area, you get a generally less productive model. And you can see where, the variations in leaf area index, generate a large variation in photosynthesis, fourfold in terms of the photosynthesis globally. And then what's interesting for us, if we're interested in the carbon sink generally, is looking at net carbon fluxes. So this is accumulated net biosphere production. So this is a measure of the land sink over the course of the historical period. The shading represents different percentile bands, and then the black line is the CLM default model. And the take-home message here is that parameter sampling generates a 200 petagram spread in terms of the land carbon sink over the historical period. And this represents about 30% of CO2 emissions over this period. This is a really large spread. And we want to put this in the context of the multi-model spread. So this is a slightly different version. So it's not cumulative. This is kind of the annual land sink. In the left, I have the results from the PPE. And in the right, I have the analogous plot, but from the global carbon budget from 2022. And from here, you can see that the PPE spread is basically 5 petagrams carbon across the whole ensemble, whereas it's, maybe something like a little bit shy of 2 petagrams in the global carbon budget. So what we're showing here is that the PPE achieves a much larger spread than the multi-model. But I think the better comparison here, because this is from basically first to 99th percentile, the better comparison is just 1 standard deviation. And here we see now we're kind of similar order of magnitude, maybe slightly larger, but it answers our question, can one model achieve as large a spread? And what's worth noting here is that I'm only perturbing LAI influencing parameters. So there's a lot of other BGC parameters that weren't chosen here that would also interface with the land sink. So this is just one subspace of the total carbon sink uncertainty, but we're already achieving equivalent spread to the multi-model product. And so then you start thinking, are all of these simulations equally likely? Is that uncertainty really the true uncertainty, or could we discard some of these simulations? On the low end of the ensemble, you're turning the whole planet into kind of a semi-barren ecosystem. And then on the high end, the planet is on average a tropical forest. So both of these end members can definitely be safely eliminated. They're unrealistic. And so I can then add on the black dot here is the default simulation, and then the green is maybe an observational constraint from ILAM. We're not sure exactly what the bounds of that box should be. It's certainly larger than that, but this gives us a sense of maybe where the model should be. But we're still kind of figuring out exactly the correct bounds for that. But I can now look at the spread of outcomes in the PPE and maybe filter on, making sure that the model has realistic LAI. So I'm not going to make it super tight because we weren't sure exactly about the spread, but I'll bound it to LAI between 1.5 and 3 and see if we get a nice constraint on the carbon sink by having realistic LAI. And actually, you're used to seeing these where you add a constraint and you get this really nice tight histogram. But in this case, despite ruling out greater than 50% of the ensemble, we got no reduction in the spread of the carbon sink, meaning that global annual LAI is not a viable constraint on NBP for CLM. And if you plot them against each other, it makes perfect sense. Our constraint here was from 1.5 to 3, and you can see that the spread on the y-axis within this band is as large as across the whole ensemble. We also have some knowledge over the cumulative carbon sink over the historical period. When you put together the managed carbon sink and the non-managed carbon sink, it's probably approaching 0 now, but our simulation only runs to 2014, so it's probably a little bit negative over the historical period. Again, the bands on these are kind of just best guesses. We're just starting some of this work, but this could be an added constraint, right? So if we're thinking about projecting into the future, like those first plots I showed on the first slide out to 2100, maybe this is a secondary constraint where we ask our model to have good LAI and a good historical carbon sink, and then take that and do a constraint on the future carbon sink. But early indications are that that probably isn't going to be super promising either. Here I'm plotting the annual carbon sink in the 1950s from all of our simulations against the annual carbon sink in the 2000s. And you can see there's not a very strong relationship between them. So if I, say that the 1950s carbon sink should be negative 0.5 petagrams per year, I don't know whether in the 2000s we should have something that's 1 petagram per year or 2 petagrams per year, and that's a big difference. And so I think in a way this is a non-result showing that we don't have good constraints on this from our first couple of guesses, but I think this actually makes a lot of sense. If it were well constrained, then we would have seen not much spread in the kind of CMIP5 and CMIP6 examples. So I think that this is actually a nice result, really showing why this is a challenging problem. So our next step is to extend our simulation. So at this point, we've run through 2014, and we're going to this summer extend them out to 2100. We're very interested in finding out how large is the spread by the end of the 21st century. And if annual leaf area index doesn't provide a good constraint on this, are there other metrics that could help reduce uncertainty, like getting good interannual variability, or having the correct trends? And then I think what's going to be really important is to bring in more of the BGC perspective on this, and say, if we have information about carbon use efficiency or carbon turnover times, I think that might be the key information that really helps us to reduce the spread in the long-term carbon sink. So with that, I'll hit the conclusion. So the key point, CLM PPE has generated useful infrastructure and 2 valuable data sets. Parameter perturbations in the Latin hypercube generated a wide range of leaf area index with an accompanying spread in carbon fluxes. And our first couple of guesses don't provide meaningful constraints on the terrestrial carbon sink, which I thought was pretty interesting. We're going to follow up by extending to 2100 and then testing a wider range of observational constraints. And then likewise, we're hoping to compare to a reanalysis product to have us, compare observational uncertainty, parametric uncertainty, structural uncertainty. But yeah, with that, I would take a question if there's time.
Questions for Daniel? Sanjeev?
Good, Daniel. Like I'm seeing some results now. So I think you already indicated that, we need multiple constraints to only using the LAI constraint is not sufficient. So do you think based on our result, what we know that both the carbon and water cycle are not really independent, or at least the parameter-wise, same parameter shows in the ET calibration versus photosynthesis calibration or sensitivity. So if you bring in little more better observe variable like ET or the water fluxes, does it whether it will provide you better constraint?
Yeah, and I think that's the key, is finding out. I think the key for us is going to be leveraging interannual variability and figuring out how NVP responds to like historical climate variation. And I think one of the big ones will be water availability. So I think that's exactly right. And having the right amount of water stress versus light limited photosynthesis and bringing in ET could help with that.
Great. Thanks a lot, Daniel. Next is Abby Swan. So, yeah, Daniel, can you stop sharing?
It does look like Ben has a question. Take that later.
Ben, do you have a question for Daniel?
I mean, just on the degree to which the super cool talk. How much do we know? Is there a risk of circularity in constraining by what we think we know about the current land sink, given that primarily comes from trendy? That was my only question.
Daniel's muted.
He's gone? All right.
No, I'm still here. I hit the video button instead of the mute. No, I agree. We're thinking about that.
All right, great. Thanks. Thanks again, Daniel. Abby.
Excellent. Those were really wonderful introductions from Ben and Daniel to what I'm going to talk about today, which is not any work of mine at all, and mostly just a set of slides to prompt some discussion. I also want to start out by saying I'm going to compare multiple versions of CMIT, multiple experiments, multiple variables, kind of loosely, just to motivate a conversation. And I'm also by no means the expert in many of these things. So forgive me if I get to some of the details wrong here, but hopefully it will start a conversation that we can take forward. So I'll start by saying that there's a large spread in expected global mean temperature due to human choices. We're all very familiar with that. So spread across scenarios from CMIP 6. Additionally, carbon cycle feedbacks create a spread in the projected CO2 for a given scenario. And so this is showing the spread in the light blue lines of about 250 parts per million of atmospheric CO2 for a single emissions trajectory. So when we do an emissions forced run and we allow the carbon cycle models to predict their own atmospheric CO2 concentrations. The concentration driven run would be the red line, and we get this spread of different concentrations resulting from allowing carbon cycle processes to play out. And relatedly, that spread in atmospheric CO2 is going to have temperature consequences associated with it, because warming is largely driven by the content of greenhouse gases in the atmosphere. And so these are the carbon cycle feedbacks that many folks in the room there have been working on for a long time. But just this idea that carbon cycle processes can also alter the content of carbon in the atmosphere, which then alters temperatures. This across model spread in CO2 is largely due to differences in land fluxes, not entirely, but the spread across the modeled carbon uptake on carbon sinks on land is much broader than the spread across models for the carbon uptake by oceans. I don't have the perfect plot for this, but this is I scaled the ocean plot to the same y-axis as the land plot here for the cumulative land or ocean atmosphere fluxes. And so we can just see that there's a lot more model disagreement across those land fluxes than there is across the ocean fluxes. There's still spread in the ocean, but a lot of this difference in the atmospheric CO2 spread is going to be due to uncertainties on land. And we also know that land parameter choice can generate a large spread in atmospheric CO2 within a single model. So I'll come back to what Daniel was talking about in just a moment. This is an older experiment, so CMIP 3 era, showing from the Hadley Center model that when they varied land parameters in a fully coupled carbon cycle model, they generated a spread of about 450 parts per million. This is an older scenario, but my headphones are going to die right then. So looking that you can get this pretty large spread in atmospheric CO2 within a single emissions trajectory within a single model. So not only do we have this large spread across models, but we can generate a large spread within a single model due to variations in land parameters. And then adding on here on the side, this is comparing it to that spread across models in the pink dots and the spread across scenarios in the black line there, showing that this range within a single model was large relative even at the time to the spread across models and the spread across scenarios. And again, the spread in carbon dioxide is then going to lead to a spread in temperature. And this is now looking at those same experiments compared to perturbing parameters in other parts of components of the model. So the green lines again are the variations in land parameters. And this is now plotting temperature on the y-axis and showing about, I'm just roughly 2.5 degrees spread across that ensemble. When they perturbed atmospheric physics parameters, they get a spread of something like 3 degrees. And I understand these aren't all totally equal comparisons, but just motivating that this variations in land parameters are having implications that are of order similar magnitude to varying parameters in other parts of the model that such as atmospheric physics. I wanted to note that not all of this warming is due to differences in the sort of radiative effects of that atmospheric CO2, although a lot of it is. So just the fact that the land processes generate a different amount of CO2 in the atmosphere by changing sinks leads to a different radiative forcing from that CO2. There's additionally some amount of that temperature change that's due to other things related to the CO2 increasing. I'm going to lump those together here and call them physiologically driven warming. So this is some work by Claire Zarakis, just showing for CMIP 5 and CMIP 6 that we get a spread of something like 0.7 degrees Celsius across models where the land is allowed to see the CO2 increasing, but not the atmosphere. So we still generate warming, even just from allowing those CO2 to increase. So we have some part of that warming, if we're looking at temperature, that's coming from the radiative effects of changing the CO2 in the atmosphere, and some part that's coming from other physical ways in which land surface responses change surface temperatures. Perturbing land parameters generates a large spread in GPP. Daniel just made this point much better than I will here in this slide, but the slide I had access to is from some newer work by Claire Zarakis, which hopefully some of you saw her present on Monday. This is showing, she did an ensemble of perturbing land parameters, a limited set of land parameters with a coupled land atmosphere system, so not coupled with the full prognostic carbon in the atmosphere, but allowing atmospheric feedbacks to happen. And so mostly relevant for this argument here is just that we generated quite a large range in annual carbon uptake. So or gross carbon uptake, so GPP, we had a range of 56 petagrams per year. I think Daniel was showing an even larger range across his land-only ensemble. Comparing this to the spread across CMIP 6 models from the C4MIP project, they get about a 15 petagram per year spread across the models in annual uptake. And so just again, saying that this within model spread is large relative to the across model spread. Again, without allowing that coupling with the atmospheric CO2. So we could change this 56 number to something else. Daniel was able to sample a lot more parameters than we were. But we just thinking basically that spread within CESM alone in terms of carbon fluxes due to changing land parameters is going to be large. That is going to create a spread in atmospheric CO2, and that atmospheric CO2 has implications for climate, again, both directly through the radiative effects and indirectly through changing things like snow model conductance and plant water use and surface energy fluxes. So my argument for discussion here, excuse me, is let's do a CESM carbon cycle PPE. I think it'd be really interesting to see what uncertainty that generates if we project it all the way into the atmospheric CO2 concentrations, and also trying to understand what some of those additional feedbacks would be. So from Daniel presenting the land only runs that he'd like to do into the future, those will be hugely important, and thinking about additionally what we could learn from or at least project into a very relevant space by showing how much that will affect atmospheric CO2 concentrations and what those possible feedbacks by changing the atmospheric CO2 concentrations might be. And so some challenges for doing this, the largest one being spin up, and this is where I will really extend beyond my expertise, so all of you in the room will have to pipe in with what you know to be the big challenges here. So for emission-driven runs generally, of which hopefully we'll hear from Ben in a moment in the discussion about why we hope to have more of them in CMIP 7. There's long timescales for ocean spin-up. I think my understanding is those are assisted by Keith Lindsay's Newton-Krylov solver, and maybe Keith can say more about that in the discussion. Land carbon pools, such as especially soil carbon pools, can take a long time to spin up, and there's nitrogen dynamics associated with that as well. So there's some long time scales. There's Ichilo sort of created this matrix approach, which has been implemented in CLM. I'm not sure exactly what the process is currently, or if there's ways to make that more operational for doing a lot of simulations. And then I know Forrest Hoffman created a sparse grid, which Daniel Kennedy has been using to run his land-only ensembles. I'm less sure about how that could be used to repopulate the full grid if we're thinking about doing full globally coupled runs, but if there's something there that we could leverage where we run the sparse grid, repopulate the full grid, et cetera. And so again, you all know more about this than me, but I'm just throwing out some topics for discussion. I also wanted to note that changing parameters can alter the mean climate state, so that might require some additional spin up associated with that. This is another plot from Claire's Zerakis's perturbed parameter ensemble, again, coupled with the atmosphere. And so changing land parameters actually changes the mean state climate quite dramatically over land. So in the context of thinking about a PPE for the carbon cycle, there'd be additional constraints, and that each parameter change might then be out of equilibrium from the base state for both climate and carbon fluxes, requiring some additional spin up and probably some creativity to deal with that. So I see this as something that would be really useful for illustrating uncertainty in future climate projections, especially potentially under decarbonization scenarios. We have reason to believe that CESM would generate a wide range of possible atmospheric CO2 for a given emissions trajectory. And I recognize that there are very large challenges to doing that. But as a community, I would love to hear ideas about how we might address some of those challenges. So that I put myself right before the discussion, so we can just transfer right into a group discussion here. And thanks for listening and for humoring me. And also, I'm sorry that I'm not able to join you in person.
Thanks, Abby. Keith, do you have anything you want to respond to, since you were directly called out in terms of this ocean carbon spin up?
Thank you, Abby, for challenging us. In terms of spinning up the ocean, what we did in CESM2 was I did use the Newton-Krylov solver to spin up a subset of the ocean BGC. It is not yet working for the full ocean BGC model. And so we still needed to do a multi-thousand-year run of the ocean model to bring the nutrient cycles into balance. So the solver technology is not yet working for the full-blown BGC, and it's also not working at all for our new ocean model, MOM. So it's even more challenging right now than it was then. There's more work to be done to get the solver to work for MOM, plus the full-blown BGC. On the land side of spin-up, there's also the challenges of having a fast approach working if you are running with mimics, because the existing accelerated decomposition techniques don't work or are not applicable to mimics. So there's challenges there as well, and I don't think Yichi's model, a matrix model, applies to that as well. So if we're going with mimics, then I'm looking at Will to see maybe we'll go with mimics if we get spin up working. I'm not sure what the the plans for mimics are with CESM3, but there's challenges there too. So there's challenges, and actually, in terms of some other challenges that you didn't even mention that come to mind are. When Claire showed you're showing Claire's plots of the atmospheric temperature response to the PPE in the land model, I don't recall seeing like a plot on the impact on the radiative balance. And typically when we're going to run the coupled model, we try to have a 1850 condition that is radiatively balanced. And this is often accomplished with hand tuning of cam parameters to get a radiative balance. And I'm not sure that exists an automated way of doing that would be, I think if you're really trying to do a full-blown PPE where you're trying to attack many perturbation experiments, that's another challenge, is that having not just perturbing the parameters, but then confining yourself into a regime where you have radiative balance in your 1850 coupled model situation. So I think it's actually harder than what you were suggesting. I'll just throw out one approach might be if we choose a handful of end member states of things that give big perturbations in these experiments, and look to see, instead of trying to do full PPE with a full interactive carbon cycle, well, what is the impact of going to a full interactive carbon cycle for a subset of the parameter space? See what's the impact in just that subset of the parameter space, even smaller subset than what Forest's sparse grid does, but that might be a way of reducing the complexity. All the issues that were brought up still apply, but if you try to do it to a smaller subset of the parameter combinations, that might make it more tractable. Still challenging though, but that's just my quick 2 cents. Please move to the microphone, Jeff.
So I've seen a number of really great PPE talks during this meeting. However, I'm a bit concerned, and so I want to remind folks that the Latin hypercube method is for an efficient method of sampling mostly uncorrelated discrete perturbations to an unknown distribution. And in many of the talks here, that's how it's been used. In essence, it's a way to find out if there is potential sensitivity to a particular parameter. It is not a method to sample distributions. It does not provide you sample of distributions, particularly in the way here where it has been used, the perturbations are on what may be extreme values of potentially accepted parameters. And so if you try to make conclusions that involve any measures of a distribution like quantiles, means, standard deviations, or other things, this is not an appropriate method. There are efficient ways to sample if you know things about the correlated distribution. I don't think you know much about the correlated distribution of the parameters in these cases. And so you are then back to the curse of dimensionality that affects all sampling methods in high dimensions. And so I just want to caution this community. I've seen a few talks here, I will not name them, that make conclusions that are not supported by the methods that are being used here. And I think you need to step back a little bit. Again, I think there's great science being done here. I'm not saying to stop this, but I think there is a need for caution on the way these things are being interpreted. They do not provide samples of distributions. Thanks.
Thanks for your insights, Jeff.
Hi, Benjamin has his hand up online.
Ben, go ahead.
Yeah, I mean, I guess I second what Jeff said in terms of. I mean, I think maybe with the follow-up that LHC distributions can, if used to train emulator systems, can be a very useful step towards building meaningful distributions. But I agree with your basic point. The wider question in response to Abby's talk was. Could we talk a little bit more about a halfway house in terms of AMIP joint perturbations of land and atmosphere? So obviously the ocean is perhaps a huge computational ask for a PPE, but is it more plausible to think about joint AMIP perturbations in a land atmosphere context? This is we're having some discussions amongst a few different groups on whether to do a coordinated AMIP atmospheric PPE effort for CMIP7, and I would very much like to see land involvement in that. And so, yeah, I'd be interested in the feedback from this community on whether they think that's a plausible thing to hope for.
Does anyone want to field that? Dave?
Yeah, it's a good idea, Ben. I think we'd lose some of the feedbacks, but maybe we can't let perfect be the enemy of the good. I think we could learn a lot from a atmosphere land coupled ensemble with sort of a joint goals of understanding the carbon cycle on land and maybe some atmospheric processes, related to the biogeophysical effects. So I think that'd be worth pursuing it. Related to Abby, maybe we could target hopefully Keith makes progress on Newton Krylov, right? Keith knows he's single point of failure in this particular endeavor. So that'd be great. But even if we can't, maybe we don't get to a PPE, but what if we even just have 2, right? And n equals 2 or 3, which is maybe something that would be hard, but it would be possible. You can envision that happening. That's one thing I was thinking about in a fully coupled. Probably would not. Obviously, that wouldn't be a CMIP activity. That would be a NCAR activity with a single model, I think. And then just responding to Jeff. Jeff, good point, right? And of course, there's this, as you know, there's the LEAP project, which is exploring all this stuff in more detail than what you're seeing in the presentations. But I think we could definitely benefit from your expertise on making the best decisions going forward, because it is going to be a significant activity over the next, hopefully, years or so on primary estimation. For all aspects of the model, we're starting on the land, but we're also thinking about the atmosphere. And I'm saying a lot here, but then the last thing I want to say is that as part of LEAP, one potential target of LEAP would be coming to one of Keith's concerns about the balancing the atmosphere, is to actually try to build an automated tool to do that, because right now we're relying on humans to do that. And there's been a few talks by that in previous meetings, right? I think Chris Fletcher talked about that a little bit previously, going from different resolutions. But I think that's one thing that LEAP needs to target, or someone needs to target, is like getting the humans out of that loop of calibrating the model at that last stage, because it's a real limiting step in producing new model configurations. So that was like 6 things, but.
Sanjeev?
I'm not a carbon cycle person, so what I'm saying may not be very relevant. But yeah, Abby, I want to put you on the spot. When you said like a carbon cycle PPE, are you thinking about 500 run or 30 run? And okay. Yeah, so I think that answers my question. Yeah, what I was thinking, yeah, based on the Daniel's result, that yeah, we can select based on the Daniel's results parameter set that realistically represent the kind of present day, at least the land condition. We do not want to select the end member or do the kind of 2 extremes that may not be realistic.
Thank you, Sanjeev.
Ben, I just wanted to give you an opportunity to give at least a very brief pitch for the greater use of emissions-driven scenarios for CMIP 7 that I think you were about to give before we cut you off.
I don't want to use up too much time, but if I could show like a couple of slides, just because we're kind of like we'd really like community input on this. I'm sorry I went over before. So let's go. Okay, so so like as many of you know, the discussions about CMIP 7 are spinning up, and there's a workshop next week in Reading on organised by Scenario on determining the scenario structure which is going to underpin CMIP 7. And one topic which I think should get decent airtime is whether in CMIP 7 we should start reassessing whether a default way of representing scenarios is in the concentration-driven framework. And so a little bit of overview of how the CMIP 7 process is going at the moment. The current thinking is that the deck will remain constant. But then there will be a set of science-based fast stream experiments and policy-driven fast stream experiments, which would be the aim is to take the burden off the modeling centers, but to say that there's like a small number of high-priority experiments, which it would be good if everybody did in times for AR7. This isn't final, but this is just an illustration of what the structure would look like. And then individual MIPs would then be free to work on their own timescale. And so the question here then is in the context of scenario MIP, whether some of these fast stream experiments should be emissions driven. And so I'm trying to put together like a large multi-author paper, and if you're not yet involved and you would like to be involved, drop me an email on sort of like the motivating on arguments for why Earth system models potentially add the most value if we start using them in an emissions and land use driven context, and how we could benefit from this in CMIP 7. So if you're interested in that, get in touch. But also in the context, the immediate context of next week, a group led of current European modeling centers is trying to put together a sort of like a shortlist of potential candidates to go into this high priority CMIP 7 cluster, and with the goal of having both a meaningful spread of emissions-driven mitigation and policy relevance experiments, which sort of like explore interesting dimensions of land use and carbon removal and aerosols, but then also have idealized experiments to back them up. So this kind of is now stepping into C4 MIP territory, but what exists in addition to the existing C4 MIP experimental design, what do you need in there to understand the mitigation dynamics and aside from TCRE, what do we need to know? Do we need to know ZEC, or should we be looking at something else? These kind of questions. I've left a link up there. If you have thoughts about this, would be useful to get feedback from as many different places as possible. Yeah, and so that's all for now. I'll open it up, but yeah, feedback on whether we should be pushing for this, also including if you don't think we should be pushing for this, would be valuable. That's all.
Everybody 5 seconds to scan your QR code before, and then you can stop sharing. Thanks, Ben.
Yep.
All right, so any last discussion points before our coffee break? Yeah, actually, well, okay, yeah, Wim has his question, a hand up. I actually have another quick question for Ben that I'm going to try and sneak into.
Yeah, this is a quick question for Ben. I think in terms of timeline, I think it could be interesting to bring on the scenario meeting the point that if we want downstream impact communities or dynamical downscaling communities to use the CMIP runs, that the timeline will be really critical, because we've seen in AR6 that CMIP 6 runs came in too late for the impact modeling community to do their work. So if that could be an item on the scenario MIP meeting, I think that could be helpful. Thanks.
Yeah, it certainly is an item. I mean, one proposal which is on the table for that is to actually keep some concentration-driven runs in there, but don't change them from the CMIP 6 configuration. So have some scenarios which remain exactly constant across model generations. And for the impact community, where you're, at least in AR6, we were mostly thinking about warming impacts at warming levels. That could provide some consistency across generations and allow sort of impact studies which were done on CMIP 6 data to still then be relevant for AR7. So that's one proposal on the table, not the only one. But yeah, I think some concentration-driven runs are necessary for at least that point, and also to include centers which can't or won't do this.
And then, Ben, can I ask you one quick question too on your Grassi correction? Do we need to use that Grassi correction to redefine like the idea of the zero emissions, translates to climate stabilization, to actually say that there's, with the Grassi correction, it's actually negative emissions that corresponds to zero emissions because you've lost part of your land sink or moved it into emissions. Is that the right way of interpreting that?
Right. I mean, for the actual in the point where you cross net zero, that's the one time where it doesn't really matter, because your land sink is approximately zero. But there's some minor correction depending on the model. But yeah. So I think for that particular question, it doesn't necessarily make too much difference. but it becomes a game theory problem. That your individual national level emissions commitments are then dependent on what everyone else does. So it gets fun in that respect.
Got it. Great. Thanks a lot. And thanks everybody for this first session. This has been really great. And we will be back after coffee at 10:30. Thanks again, everybody. Thanks to the speakers.
Welcome back, everyone. Folks online, I don't know if you, what you can see, but we're herding cats right now, getting folks back into the room after getting refueled. Our first speaker now after the break is going to be Josh Koop. So we have a string of speakers who are now on site, and I'll try to give you a 2-minute warning so we can try to stay on time. So Josh, come on up. To the mic so it's picked up. And you can see here does the mouse show online? Okay. Okay.
I can do that.
Take it away, Josh.
All right. Hello. My name is Josh Koop, and I'm a postdoc at CU Boulder. And I'm going to be presenting on some work that I've been working on the past few months on implementing an ultraviolet radiation damage function for phytoplankton in CSM and marble. So this work is part of a project on understanding the mechanisms for extinction of the asteroid impact at the KPG boundary 66 million years ago. So that's some of the motivations behind developing this enhanced surveyation. So for example, CFC emissions caused the destruction of quite a bit of stratospheric ozone and led to an ozone hole. And there were a lot of studies about this ozone hole 30, 20 years ago. Especially, there were concerns about how this increased UV radiation would affect phytoplankton, especially in the Southern Ocean. So we, for this study, we're adapting from a lot of these studies from like the 90s. Additionally, the injection of smoke, dust, sulfate aerosols in the stratosphere can cause reduced stratospheric ozone and increased surface UV radiation. This can happen via a nuclear war. Large-scale nuclear war causes cities to burn across the globe. All of this smoke gets lofted up into the upper atmosphere, causes heating in the stratosphere, and that leads to the destruction of stratospheric ozone. And once that smoke clears, maybe 6 to 10 years afterwards, then you get UV radiation coming to the surface. Wildfires, specifically really large-scale wildfires that produce pyrocumulonimbus clouds, which can inject smoke into the upper atmosphere, can also destroy ozone via the same mechanism. Volcanic eruptions and their sulfate aerosols, also very similar mechanisms for destruction of stratospheric ozone. And finally, the asteroid impact, which can inject all of those aerosols, smoke, dust, sulfate aerosols, and cause the destruction of ozone. They can also inject halogens, especially when an asteroid impacts, say, seawater, and bromine and chlorine gets into the upper atmosphere and will accelerate those reactions that destroy ozone. So these are the potential scenarios that this function that we developed can be used for. And so this, getting to the function itself, we're adapting from a paper from 1992 that developed this biological weighting function specifically for a diatom, Phaeodactylum. So this plot here shows at lower wavelengths, UVB around 280, you see this exponential increase in sensitivity to UVB radiation, which represents an inhibition of photosynthesis. We try to simulate that in this function, but the response to UVB radiation can be complicated by things like photo repair. So over time, phytoplankton can mitigate UVB radiation by growing these flavonoids at low UVB levels. We're not going to represent that. Also, the response to the UVB radiation can be affected by other climate stressors. So if nutrient temperature limitations are high, phytoplankton could be further impacted by UV radiation. So this is our model setup, CSM 2.1.4, using Wacom 6. And the new component that we're using is the tropospheric and ultraviolet and visible radiation model, or TUV, which allows us to simulate UVA, UVB, photosynthetically active radiation over narrow spectral bands compared to the current radiation model. So this has that advantage of being able to actually simulate the amount of UV radiation that gets to the surface. The other new thing that we're using here is in marble, we have 4 phytoplankton functional types and 2 zooplankton functional types. And we're primarily using that configuration of marble, but we're also testing the 3P1Z and 4P1Z types, which are 3 phytoplankton and 1 zooplankton types. So TUV calculates the UV radiation at the surface, and this damage function for diatoms is actually already built into the TUV model. So it's calculated in the atmosphere, and that gets passed down into marble. And then we construct a UV limitation term, which ranges from 0 to 1, 0 being the most limiting, 1 being not limiting at all, via this equation where the inhibition is, as it increases, you get the limitation term approaches 0. So this is kind of just illustrating how the model is set up. WACM, TUV is attached to WACM. TUV sends UVA and UVB, as well as photosynthetic active radiation, UV inhibition term. Normally, just shortwave radiation gets sent to POP. So we have 2 potential streams of radiation now that POP and marble can use. The old method was just a constant multiplied by shortwave radiation to get this photosynthetically active radiation, or PAR. Or we can use TUV PAR, which theoretically should be more accurate. This gets sent to marble, and then within the computing photosynthesis subroutine, we calculate this inhibition and UV radiation limitation term and multiply that by photosynthesis, and you get this UV inhibited photosynthesis, which we will be simulating. So that's how you get the surface UV radiation. You also have to attenuate this throughout the column. So UV radiation does not make it that deep in the ocean. It gets attenuated very quickly, which we learned early on when we accidentally irradiated a lot of the mixed layer. So we developed, or we're using this empirical relationship from the Silvermans and Augusti study, where they looked at how UV attenuates in the Red Sea. And so it's a function of this, the K is an attenuation coefficient. It's a function of chlorophyll. That's what CHL stands for. And through the column, this figure is showing how at various levels of chlorophyll, how far UV radiation gets into the ocean. And the gray line is the 99% attenuation line, an oft-cited metric. And you can see here that across most levels of chlorophyll, UV only gets 15, 25 meters at most into the ocean. So this is going to mostly affect phytoplankton below 25 meters. And so any phytoplankton that can live a lot lower will have a great chance of survival for an event that really increases UV radiation. So first results, we simulated a no UV inhibition case and compared it to a case that had pre-industrial levels of stratospheric ozone, normal inhibition case. And here you can see there's pretty minimal effects for pre-industrial levels of stratospheric ozone. So 0.34 petagrams of carbon per year change in MPP in year 2 of a spin-up run. It's less than 1% change. So with this damage function, there's pretty low sensitivity to these pre-industrial levels, but we really wanted to test on the high end what would happen if the surface was bathed in UV radiation. So we injected over 1,000 teragrams of halogens into the stratosphere to try to destroy ozone as much as we could. And the effects were also sort of minimal. I mean, about a 16% reduction in NPP over the course of a year. We adapted this from an asteroid impact simulation. But we saw the inhibition of photosynthesis in this simulation. So there is some response. It works, essentially, is the point of this. If we look deeper into how the response works throughout the column, you see, as I was implying before, it only inhibits photosynthesis above 25 meters. So the entire top part of the ocean is severely inhibited, whereas actually phytoplankton 60 to 25 meters, you see growth. They benefit at the expense of the really top level phytoplankton. There's also some variability dependent on the phytoplankton functional type. So we have diatoms, small phytoplankton, diazotrophs, and coccolithophores. Initially, before you eject the halogens, small phytoplankton are the majority of the contribution to MPP in this model. But you actually see a shift towards diatoms when you add this UV inhibition term, which is interesting. The small phytoplankton die off a little bit, and the diatoms are more than 50%. Also, some interesting patterns in the coccolithophores. I haven't explored this too much. These are kind of preliminary results, but there's some interesting patterns to explore why coccolithophores in the Southern Ocean are dying off, whereas in the high latitude in the Northern Hemisphere, they're actually thriving. And this is just another view of calcium carbonate of coccolithophores, and you can see that in the Southern Ocean, extremely diminished, whereas in the high latitude Northern Oceans, there's a lot more calcium carbonate. Also looked at, this is just to show not much sensitivity when you look at the different configurations. So 4P2Z, 4P1Z, 3P1Z, generally around 14 to 17% changes, which is, we're happy with that. It doesn't seem to be too sensitive to the type of configuration. We also looked at the effect. So in addition to UV, we can also pass to UV PAR, which we expected to be a little more accurate than the other calculation that was previously done. That didn't actually seem to be the case. So the TUV PAR that's being passed from the atmosphere on a global level, so you can see in this profile, it's a little bit less. There's some interesting spatial patterns too when you compare the two methods. So high latitudes have a lot more PAR when it comes from TUV. The tropics generally have less, but there's some strange patterns here. We're still kind of exploring why this is the case, but for the time being, we actually kind of stopped using TUV PAR until we figure out exactly what's going on here. So again, preliminary stuff. That radiation change also leads to a very large increase in MPP, which is another reason why we kind of stopped using this for now. But I will move on to my conclusions. So generally, there's a low sensitivity to pre-industrial UV radiation in this 4P2Z configuration. And MPP does seem pretty resilient to increased surface UV radiation, probably because it's only in the top 25 meters. We didn't expect to see such a large increase just below 25 meters. But we're still developing this function, and there's some future work and other potential applications that we're going to add on to this. So we're hoping to add a function of shell thickness in coccolithophores. So, calcium carbonate shells might be able to offer protection, so we could modify that damage function depending on the thickness of the shells, which might be important for ocean warming and ocean acidification. And this all ties into the asteroid impact scenario as well. Thank you.
And up next is Brett Rosca. I don't actually know how to operate it.
All right, hello everybody. My name is Brett Raska. I help support the land. I help to support the land DA activities within the DART group. I'd just like to give a shout out and thanks to all the co-authors who help support this work. A lot of this is their work. CLM DART and the ensemble common filter system. So it's a Bayesian approach. So using prior information, usually queried from Earth system models, in this case, giving an example with CLM, and then we're taking observations, in this case, remotely sensed observations, and fusing those together to give the most likely analysis to go with the best ecological forecast going forward. So delving a little bit more into the details, how do we do that? Generally with the CLM DART, we generate the ensemble spread with CAM-DART reanalysis, so this samples the uncertainty in the atmosphere. We confront that with CLM, and that gives us spread within the CLM simulations. We use CLM history files and restart files, the output files, to map this the model space back onto observation space. So in the case of above ground biomass, if we were simulating that, we use the more basic fundamental variables of dead stem C, live stem C, and give it the location, which allows us to compare it directly to the observation. So that's called the forward operator in this case. So we compare the two and we update those, and where the analysis, the posterior actually ends up depends on how certain we are between the observation and the original prior. And the next key step is we use that observed variable update, those increments. We regress those on all the unobserved state variables that are strongly related. In this case, I give a list of the important ones related to biomass. Notice it's not just carbon pools, also nitrogen pools as well. And so at the end of the day, we end up with an updated analysis or forecast, and then we iterate this to the next time step and keep going forward. So what are some applications? So carbon monitoring is a big one. So assimilating in observations of biomass and leaf area to the western United States to correct the simulated carbon fluxes. We also do this on a more refined, high-resolution domain in the Southern Sierra Critical Zone. This work's being led by a graduate student, Louis Koenig. So in that top right plot, I'm just showing the mismatch between CLM simulated GPP, normalized GPP across the elevation gradient of the Southern Sierras, and also mismatch in the phenology and the timing as well. So it's comparing it against FluxCom GPP and also a Tripome SIF, which is a proxy for GPP. So potential, a lot of analysis there, but potential for DA for that region as well. We've applied something similar to the Arctic domain, again, assimilating biomass and leaf area, reducing both biomass and leaf area in that case. This analysis is more extensive, so looking at the impact of energy fluxes, canopy height, and albedo on that adjustment as well. And also sort of a newer project that we're supporting, this is over the East Africa tropical domain. In that case, they're using CLM. I want to use CLM and DART to basically verify the restoration process. So kind of hard to see with the colors, but in the green colors are areas where we want to restore the forest. So the way to validate that is through bottom-up land surface modeling approaches and through observations, and they want to leverage solar-induced fluorescence as this example to constrain the carbon cycle. So we could also apply this to hydrology in drought monitoring systems. So in this case, assimilating in observations of surface soil moisture. This is a European Space Agency project. So in the top left, this is kind of showing the before and after, the increased correlation using the ERA 5 benchmark sort of as validation there. The colors are not showing up really well, but you get the picture. So it's updating and bringing the soil moisture much closer to the benchmark, not only at the surface, but also in the subsurface as well. So showing improved correlation with the in situ soil moisture observations at the different sites within this domain as well. So that has implications for the carbon cycle as well. And then also a drought monitoring system that, helping support, this is over the India subcontinent. So again, using CLM as sort of the basis for the land surface modeling, bringing in observations of soil moisture, terrestrial water storage, and leaf area. And so on the bottom right, they're just showing some preliminary results of using CLM with satellite phenology and just comparing the surface soil moisture against the validation product of GLEAM and showing some pretty promising results in terms of the spatial distribution. So those other different projects I've highlighted just are updating the state or prognostic variables within CLM, but we know we're limited by what state updates can do. And so just to illustrate that, here I'm just showing a seasonal cycle of leaf area across the globe for a certain plant functional type, and just showing here the difference between the free CLM run and the observations in green and the assimilation run is here. So that's what we want. We want the assimilation run, the forecast, to be closer to the observations. But the true test is when you deprive the system of the observations and run the forecast well into the future. How well do we do? And so at 2006, we deprive the system of observations and see where the forecast, the extended forecast goes. That's this orange line here. And in this case, it's actually returning back. It's attracted back to the free run. So in that case, that indicates to us it's not an initialization problem. There's something more fundamental with the model structure, model parameters. Same with the lower slide as well. So another way to get at this is an assimilation case across the Arctic domain, showing seasonal cycle of GPP, and with CLM simulation, showing the free run on the top, how distinct and different it is from kind of the FluxCom GPP, a validation machine learning product. And so this line right here is when we assimilate observations of above ground biomass and leaf area, getting more consensus. But the best consensus is when we include both assimilation and including parameter updates as well. So this is kind of like a hand-tuned change in parameters that actually have a light or a temperature varying light saturation curve in this case. This was implemented by people at the University of Arizona, so a combination of the two. And so just an example of parameter estimation within Ensemble DA, and this work was led by Moha Garanti, a member of the DART team. And so this case was assimilating in chlorophyll observations, vertical profiles within a Norwegian ecological model. And so on the left, just showing the number of parameters that were estimated in this case. So essentially you're using an approach, generically called state augmentation approach, which treats parameters similar to how you would a traditional state variable. So in this case, just showing two distinct different outcomes. So in the top parameter silicate to nitrate, you kind of get what a kind of more expected result, or what I think of when I think of parameter estimation. You start off with your initial nominal value. Here, you look at the ensemble spread of the analysis of that parameter, and the black line is the mean. And so it's coming to a consensus. It's converging to a single parameter. So you have some confidence in that. But for more difficult parameters that maybe convolve more processes, mortality, for example, this is evolving in time. And so you have to be aware of that when you're doing this assimilation. Perhaps you need a more stringent prior constraint, or maybe try to isolate the observations more on that parameter state that you're trying to update. So to extend on that, so we're also working on additional site level parameter estimation runs, and this is a project using the Marble MOM6 configuration and a 1D column. And so the goal here is to estimate parameters at the different sites, different biogeochemical regimes as shown up here on this plot. And then once those are estimated, evaluate how they do on a global scale. So this is being led in part by SciPark student Robin Armstrong. So bringing this back to projects that I'm more involved in with the land parameter estimation, there's the CIF model intercomparison project. And so I've mentioned this before. So CIF has a strong empirical relationship with GPP. A lot of land surface folks are very interested in using this as a constraint. So to kind of test how we're doing with the different models, the group one within this project, we're running a bunch of different models at different sites from Alaska to Florida at evergreen forests, just kind of benchmarking how we're doing at simulating CIF. In group two, which I'm very interested in contributing to, is also doing parameter estimation and state estimation with Orchidae, our CLM DART, and cardamom. So one of the steps that had to occur to get this to work is to create a forward operator converting CIF, leaf CIF to canopy CIF. So this is work led by the University of Virginia. And so these plots right here are just showing that the approach used within CLM CIF here, this is the escape probability approach within the canopy, compares favorably with a radiative transfer model of scope CIF. So 1-to-1 for deciduous forests. It's a little bit more challenged in more sparse canopy forests, such as Niwot Ridge. And in the bottom, I'm just kind of kicking the tires on the simulation, just kind of showing and comparing GPP with CIF there. So it looks okay, it needs more testing, and so we're testing that now. 2 minutes. Okay. And so going a little bit over time, but Some of the methods that I had to implement was to apply a bias correction to the CAM6 reanalysis. So anybody who does site level simulations know you can't use a gridded product alone to do site level simulations. So one of the things I had to create was to use the site level information to adjust the CAM6 reanalysis. So here I'm just showing at Niwot Ridge the improvement that's showing within the meteorology and the improvement that shows within the leaf area. So that puts us in a good prior condition to do DA. The other thing that I'm doing is creating software to basically query flux tower network information. And this is the Ameriflux full set data set. So this will give the user the ability to query in gap filled, non-gap filled, partition fluxes, and brings in multiple uncertainty estimates, which is critical in DA. So in terms of the partition fluxes, this gives you the ability to do a simulate in GPP, which you can isolate that information on photosynthetic parameters, for example. And then also, this is probably the most thorough propagation of uncertainty for eddy covariance data, including both the random, the U-star, and partitioning methods as well. So just closing, the last thing I'm going to show here. And so and this is, Jeff Anderson presented this at the parameter estimation meeting earlier, but if you have bounded parameters, in this case a hard zero bound, and you're confronting that with observations on the far left, does it respect that when you introduce the observations? Is that bound respected? So in this case, the observations on the x-axis, the parameter, say, is on the y-axis, the gray is the known distribution, and the green is our sampling of that. And so when we do a traditional linear regression update, are the bounds respected? Is it capturing the nonlinearity of the joint prior distribution? The answer is no. When we do the update, it's not respecting the known distribution in this case. And so the new quantile conserving regression filter that Jeff talked about, that's the cyan colors there, does a better job of estimating the bounded quantity update, and also if there's nonlinear relationship in the joint prior distribution. And so in interest of time, I'll just put up my summary slides there and take any questions. Thanks.
Thanks, Brett. Questions? Can I ask a question? So how is the sort of information flow of your parameter estimation going back into the sort of default parameter values in CLM, or is there? How are you thinking about that?
So yeah, we've implemented that sort of approach in different models. I haven't implemented that as well, but it's a case where we'd have to manipulate. In the case of state updates, we manipulate the restart files directly, reinsert them back into CLM. For the parameter case, we'd have to generate multiple parameter files to reinsert those in each one of the ensemble members to basically get that sort of distribution. Yeah.
Brett, thanks for the presentation. I have a question about the state update. In the soil pools where CLM is assuming a fixed C to N ratio in some pools, do you have to tell DART about that so that it doesn't break the fixed stoichiometry assumptions of the model?
So the updates will roughly follow that in the sense that it obeys like the correlations between the observation and how that correlates. So in the sense that C and N are fixed, it should come along for the ride. I will mention we have not had success updating the soil carbon pools with above ground biomass in leaf area because we do not get good correlation with that. And so in order to update the soil carbon pools, we'd probably have to look into like direct soil carbon observations to update those. Yeah.
Thanks.
All right, thanks, Brett. Up next, we have Yi Yao, who's going to talk about irrigation.
Good morning, everyone. So my name is Yi, and I'm doing my PhD with my supervisor Wim Thierry in the University of Brussels in Belgium. And I changed a bit of my titles because I realized yesterday that I didn't answer the question I mentioned in my title. So today I was just mainly talking about the implementation of irrigation techniques and the creation of projected irrigation techniques shares datasets. Yeah. Okay, so firstly, I want to talk about the motivation. Actually, with global warming, we have more and more heat waves. Just this year and last year, we already have these heat waves across Europe, Australia, and India. So we are, and you may ask, we are talking about irrigation and why you are talking about heat waves now. Actually, irrigation may do have impacts of the heat waves. So actually, both observation-based and modeling-based study already proved that irrigation has a cooling impacts. So some people think that maybe the irrigation could be a solution to the heat waves, especially for these very populated areas. And of course, some people may disagree. They think that, well, you're always talking about temperature. What if we also include the impacts of moisture? So there was a study has done 3 years ago. They think that if they include the impacts of moisture, then like they calculated the metric wet bulb temperature, and then if actually irrigation increased the wet bulb temperature. Wet bulb temperature means that irrigation may have negative effects on the heat waves. So we really want to know what is the impacts of irrigation on the heat waves. That's why we launched a MIP, and we call it Irrigation Impacts Model Intercomparison Project. We call it IRMIP. The objective is that we want to see how the irrigation expansion have affected the heat extreme events in 20th century. And the simulation period is from 1901 to 2014. And we had only 2 simulations. The first one, we call it Trans-Ir, means that we have a transient irrigation extent. And for the second one, we call it 1901-Ir, because in these simulations, irrigation extent is fixed at the level of the year 1901. So as you can see here, this is irrigated land from 1901 to 2014. And this is the distribution of the irrigation expansion. So far, I can only show the results from CSM2. And please note that this CSM2 is CSM 2.1. And before going to the maps, I want to show you how did we analyze this. So we use the probability ratio, which means that we have the probability for one event, for example, TSA. This means that the events that TSA, which is air temperature, exists 95 percentile during the reference period. And then we calculate also the probability during the experience period. Then if the PR is over 1, it means that the event happens more likely. And if it's less than 1, then it's happen less likely. So we have 3 comparisons. The first one is we set the ref as a Trans-Ir 1901 to 1930. And we have the experiment period as the Trans-Ir 1985 to 2014. Then we compare these 2 periods, then we think that this can represent the impacts of all 4 things, so everything. And then we also have another comparison for this 2 period for the 1901-Ir. And we think that this is the impacts of the all 4 things, except irrigation expansion. And finally, we want to compare these 2 simulations, and we can assume that this represents the impacts of the irrigation expansion. So firstly, let's say at the 2-meter air temperature for the TSA 95 percentile. As you can see, we can see a very small cooling impacts over India. But if we check the 99 percentile events, then this impacts is a bit stronger. And then we go a bit more extreme for the 99.9 percentile event. You can see that the irrigation expansion has a very, very very, very strong cooling impacts. It looks cool, but there's nothing new because we just redid what my professor has done a few years ago. But this time, what is new, we also check the wet bulb temperature. So I will show you all these three maps for 95, 99, and 99.9 percentile. As you can see here, if we include the impacts of the moisture, then these impacts become unclear. And also, before we already showed that in India, they have the study that the wet bulb temperature may be increased by the irrigation, but here we didn't have this. And what's the reason? I don't know, but we think one of the reasons could be the representation of irrigation in CESM 2.1. So irrigation in that's the version actually is very idealized. We have crops and we apply waters. And when should we do it? It's when the available soil water is less than the threshold. And how much water should we do? We just apply the deficit between the target and the available water. And the water is applied on the canopy, which means that there is no interception. And we go, let's see what we have done in the CESM 2.2. So basically, actually, irrigation can be very different. We can have drip irrigation, we have the flood, we have the sprinkler, and also for rice, it's very special, we have the paddy irrigation. And what's the difference between them? If we simplify them, actually you can see the difference can be where we apply them and how much water we apply and whether we pump the water. So based on this, we developed another 3 different irrigation techniques. And we set the default irrigation as the drip irrigation because it's quite efficient. So as you can see here, and then we want to know if it increases the ability of the model or not. So firstly, we did a single point simulations. We select 3 different sites, one from Nebraska, another from Castellano in Italy, and the last one is from the Mass in Japan. And for this, why did we choose these 3 sites? Because on the one hand, they only have 1 growing season. That's what we have in our crop model in CM. And also, they represent 3 different irrigation techniques from sprinkler to flood and to paddy. And we did 3 different simulations. The first one we called the no-ich, means that there's no irrigation activity. The second one is a control, which means with the original irrigation module on. And we did evaluation based on the evapotranspiration data we got from the sites. I mean, I didn't do it. I got it from the FlexLate. And here, as you can see, for Nebraska and Castellano, actually there's no big difference. But for Mass, the rice parties, you can see that during the no peak regions, our new module really increased the ability of the model to reproduce the ET patterns. And this is what we have done for the single point simulations. And of course, we want to do it. We also want to do global simulations. So from the Jonas Jagemer's work in 2015, he collected data from different sources and he generated a map for the irrigation techniques share. And based on this map, we want to implement it. We want to implement something similar in the CM. And there's one problem here is that for each irrigated column, we only have, for each irrigated crop, we only have 1 column, which means that we can only allow 1 irrigation technique for 1 crop. So we simplified it, and for every crops, we have a different map, and which you can see here. And then we do the global simulations based on the FAO Aquastat data. We have this observed irrigation water withdrawal, and from the control simulations, again, is the original irrigation module. You can see that there's a very obvious underestimation here. And when we turned on our new irrigation module, okay, thanks. We have our, actually, you can see the model's performance has been increased a lot. So we think that our irrigation module substantially improved the model's ability to simulate the irrigation technique, water withdrawal. And this is the paper here. And then our next step is that we want to detect how irrigation will affect heat extremes under future scenarios. And then I realized there are two issues for us. The first one is that there's no projected irrigation techniques shares in line with SSP and ICP scenarios. And the issue two is that this newly developed irrigation module cannot fully address this question, which means that we need to do some more development, which has been done. I don't think I have time to go to detail, but we just checked which variable should be related to this irrigation text fraction. And we found that we have the GDP governance, urbanization, the gender inequality index. And also for hydroclimatics, we also found that the precipitation has not very strong, but they have some correlation with these techniques shares. And finally, for all these GDP governance variables, because they are highly related with each other, so we did a PCA, and then we choose the first variables to represent them, which already explained 80% of the variance. And then we applied this framework, and we give them a default irrigation techniques update speed, and based on the two variables, we give them the we update their speed every 5 years based on the data availability. So these are some results examples, and this is for India also example. And okay, so what I'm doing now is that I want to expand the safety columns in the model again. For each irrigated column, we have three different columns, which means that the drip irrigation, sprinkler irrigated, and also flood irrigated. And for the right, we have a very specific poor irrigated irrigation. So for the take-home messages, first thing that the impacts of irrigation on heat extreme may be different if we include moisture. And second one is the newly developed irrigation module really helps the model to increase the ability. And we are working on, maybe actually it's already done. We are expanding its ability again. And third time is that the third message is that a project irrigation techniques shares has been created. If you're interested, please feel free to send me an email. And the last one is that if you do model development, please think carefully what questions you want to address in advance. And finally, I want to thank my group members from Biogeochemistry CESM group, and they all do very, very fantastic good work. So feel free to follow them on ResearchGate to see what they're doing. And also here, I want to express my thanks to all the colleagues from UNCAR. And finally, I have the time. And yeah, very special is Sean. I don't know if he's here, but I don't know how does he look like. Thanks.
Questions for you?
Hi, E. Can I ask a question?
Whoever's online, yes, second. We have somebody standing here in front of the mic first.
Okay, sorry.
Thanks. So I realized that your implementation is based on water needs for the plants. And at least like for Europe or for Germany, I'm aware that especially in case of heat waves, there are restrictions to water because you have this sectoral conflicts. And if water is needed like for private households and for industry, there won't be any water left for irrigation. So do you take that into account, or how can that be taken into account?
I didn't. But this guy, Sabine Tahanou, the last one in our group, he's working on this. Actually, he's implementing the water use for different sectors, and he defined an order for these sectors. So, I mean, and he's preparing the manuscript. I hope it will be published soon, and then you can check.
Question from online?
Yes. Hi, E. Yeah, I have a question about the target, the soil water target for each different, because we know there are so many different crop types, how do you actually assign the target water use for different crop types? What are those data from? Yeah, thank you.
A very good question. But actually in CM at this moment, there's no difference between different crop types. But I think it must be very interesting if we can collect more data and implement it in the CM. Maybe the models can be improved again.
Okay, thank you.
Thanks, Yi. Next, we have Amy Liu. We're talking about influence of model behavior and photosynthesis.
Hello. Wait, is this good? Okay, great. Hi, I'm Amy. I'm a graduate student working with Abby Swan, and today I'm going to be talking about, as Charlie said, quantifying the influence of small behavior and photosynthesis. And I've had the pleasure of working with a number of collaborators listed above. And to start off, we know that plants have these stomata on leaves that regulate gas exchange with the atmosphere. So this is an open stomata, and this is a closed one. And a more open stomata corresponds to higher small conductance, while a closed stomata corresponds to lower small conductance. So these changes in small conductance can drive changes in both carbon and water fluxes. And these changes can impact the carbon and water cycle, which can then affect water availability and the risk of extreme climate events like droughts, heat waves, and floods. So as Maurice Leroux showed in 2019, we learned that surface properties can affect climate, so an increase in evaporative resistance can increase surface temperature. And in CLM, the small conductance is represented by the Medlin model. So here we have the Medlin model where GS is small conductance, G naught is Medlin intercept, so what the small conductance would be if the small were completely closed. DS is vapor pressure deficit, CS corresponds to carbon dioxide concentration, AN is photosynthesis, and G1M is the Medlin slope. And the Medlin slope is essentially a fitted parameter based on leaf level observations. So this is a plot from the Medlin et al. 2011 paper where we have small conductance on the y-axis, and every point we see is a leaf level observation colored by the plant type. The Medlin slope is essentially just the slope of that fitted line against these points. And if we look at a spatial distribution of the Medlin slope, we can see it's quite varied throughout. And that's because it's comprised of a lot of plant functional types. And Lin et al. In 2015 show here in this plot that there's quite a large variability across different plant types for Medlin slope. So this is a plot of estimated Medlin slope based on field observations where we have the estimated Medlin slope on the y-axis and temperature on the x. And again, every color corresponds to different PFT. And yeah, there's a huge range across the different colors and within one color. And this can lead to large variance in carbon and water fluxes. And in CLM, one Medlin slope value is used to represent each plant type. So for example, if we take the broadleaf evergreen tropical tree, it has a low Medlin slope value of 1.7 and a high of 9.11, but this default value of 4.45 is the value used in CLM. And so this really begs the question, what happens if we use a different slope value? And if you haven't guessed by now, we're focusing on the Medlin slope parameter. And I want to point out that the Medlin slope is inversely proportional to photosynthesis and also inversely proportional to water use efficiency. So if we change the Medlin slope parameter and all else in the Medlin model remains equal, we should expect a decrease in photosynthesis with an increase in the slope parameter. So yeah, we're varying the Medlin slope, and we're starting off with a default Medlin slope value that's used in CLM and taking a high and low value of it based on the Lin et al. 2015 data set. And remember the spatial plot I showed before for the Medlin slope values, that's actually of the default values in CLM. And this is a scatter plot of how we're perturbing the Medlin slope values for each of the PFTs, where the empty circle is the low Medlin slope, the solid square is the default value, and the diamond, empty diamond is the high. And since we pull from the Linnell data set, we can see that there's quite a bit of a range of the Medland slope. And in addition to the Medland slope, multiple other factors can affect small conductance. So we're also going to take a look at land-atmospheric coupling, since atmospheric feedbacks can modify temperature and precipitation of impacts of land surface change, as well as comparing dynamic leaf area with a fixed leaf area, since leaf area changes the relationship between water sufficiency and the total fluxes of carbon and water. And yet on top of all that, we're running low and high Medland slope versus the default Medland slope. So for this talk, we're going to compare two configurations. They're both going to be at pre-industrial carbon dioxide. One configuration is going to have a coupled atmosphere with a dynamic leaf area, and the other one's going to be an uncoupled configuration with a fixed leaf area. And we're going to call these two configurations complex and simple. And this is, oh, and by the way, we ran a lot more other runs. This is a summary of all of them, but they're mostly not going to be discussed today. Going back to our two configurations, this is how we're going to do the comparison. So walking through one example, we're going to take the simple high Medland slope case and find the difference of that from the simple default Medland slope case. Do the same thing for the complex configuration and compare the two differences. So here's what we found. So in the simple configuration, comparing the high to the default Medland slope, we found that photosynthesis decreases across the globe. It's brown here corresponds to a decrease in photosynthesis, and a green corresponds to, is it? Oh, okay, it's not green. Well, gray corresponds to an increase in photosynthesis. We lost the red. And we see that pretty consistently with the complex high Medland slope case, as well as just like a stronger response, photosynthetic response. However, if we look at the simple low Medland slope case, we see that photosynthesis response varies pretty regionally. There's green and, or in this case, gray and brown everywhere. And if we compare it to the simple case to the complex low Medland slope case, we see that, again, there's still regional responses, but the response sign or increase or decrease in photosynthesis changes. And if we normalize the difference in photosynthesis by the change in Medland slope, the photosynthesis changes outside of the tropics are a lot more comparable. I just wanted to point that out. So it's kind of hard to qualitatively see where the sign changes besides clearly the Amazon. So we wanted to create a plot that would really clearly show us where we see these photosynthesis sign changes. So this is what we came up with, and from this plot, you can ignore the color for green and pink right now, or the colors, or green and gray is not really a color, but we can see that, so where there's color or where you see color is where there's a sign change. And we see here that the differences in the sign of photosynthetic response for the low Medland slope cases between the simple and complex configuration are largely clustered in the Amazon, Central North America, and the Boreal regions. And so trying to understand why, we're going to zoom in on the Amazon first. So in the simple low small slope case, the photosynthesis increases as expected in the Amazon. I've pulled the plot we had earlier showing the expected relationship between the small slope parameter and the photosynthesis. However, if we couple the atmosphere and have a dynamic LAI, so in the complex case, we see that photosynthesis unexpectedly decreases in the Amazon. And we're going to try and answer why. So we're going to show a flow chart of schematics. And on the left here, we're going to have a bar graph of the differences of different variables between the low and default Medland slope cases, where the simple case will be, okay, the lighter color, and the complex case will be the darker color. And on the right here, we're going to have the schematic. So we see that photosynthesis increases for the simple and decreases for the complex low Medland slope case. If we take a look at small conductance, we also see pretty consistent decreases in both cases, so we have a small closure. Transpiration also decreases as expected with a small closure. If we look at heat fluxes, they also change as expected with a decrease in latent heat flux and an increase in sensible heat flux. if we look at soil water stress and soil liquid water content, we see that having an increase in water use efficiency decreases the soil water stress and increases water availability. So far throughout comparing the variables so far, we see that between the simple complex case, the changes in the variables are pretty similar. And here I want to say, we think that the increases in water availability is why we see increases in photosynthesis for the simple low melon slope case. But that doesn't really explain why we see photosynthesis decreases in the complex case. So the last two variables I want to look at are surface temperature and vapor pressure deficit. And we see that in the complex case with a coupled atmosphere, we see larger increases in temperature and increases in VPD. And we think that because there's such a much larger change in surface temperature and VPD, we see decreases in photosynthesis. We're past the thermal optimum for photosynthesis. We think in Amazon, if we increase temperature by that much, and the increase in VPD might cause atmospheric water stress for the plants. 2 minutes, thanks. And then, so now since we looked at Amazon, we're going to now move more north to Boreal Canada and walk through the same process. So in the simple low case, contrary to the Amazon, we see that photosynthesis unexpectedly decreases for Boreal Canada, and that's pretty interesting, and we want to figure out why. And in the complex low melon slope case, photosynthesis increases as expected. So it's like a swap of sign change between the Amazon and Boreal Canada. Again, photosynthesis decreases for the simple and increases for the complex low case in Boreal Canada. And we also see small conductance decreases, so small closure with the low melon slope case. Transpiration again decreases as expected with small closure, though not as much as the Amazon, which is to be expected. And heat fluxes also change as expected. There's not much changes in water availability. But if we move on and look at the surface temperature and VPD, we see that in a complex case, again, we see a large increase in temperature and VPD. But we think in Boreal Canada, this increases the photosynthesis instead, because before we increase the surface temperature in the complex case, the plants might not be at the thermal optimum for photosynthesis. And since now we're increasing the temperature by so much in the complex case, we see an increase in photosynthesis. So to quickly summarize everything, we saw that in the high melon slope case, cases that decrease in photosynthesis is pretty consistent. In the low melon slope cases, the effects on photosynthesis are pretty regionally dependent. And if we have a coupled atmosphere, which we saw in the complex case, this enabled their climate to respond differently. So we saw a much larger increase in surface temperature in the coupled atmosphere case. And we also saw that photosynthesis is sensitive to the temperature changes depending on region, as we saw comparing between the Amazon and Boreal Canada. And that's it. Thank you.
Yeah, thanks. Next is Sabina Eggerer, who I believe is online. Here, sorry.
Do it a little bit differently.
Welcome. I'm Sabine Eggerer, coming from University of Munich. So before I start, I have to do 2 disclaimers, because I was just asked on Monday by Will to present here because there was a free spot. So I just jumped in and I put this together kind of in a rush, so just to lower the expectations. And also, I never worked really with CLM before. But I'm planning to do it because I will stay now here for 2 months at NCAR, working with Lawrence on this issue of comparing climate mitigation potential of afforestation, reforestation, and bioenergy plants. And so I will present some thoughts and plans which I have for the next 2 months here, and I also present part of the work which I've done within CDR Terra. So CDR Terra is a large national project within Germany on carbon dioxide removal. It's led by Julia Pongratz at LMU Munich, so those are all of my co-authors there. And so it includes a wide range of CDR options actually, so spanning from agroforestry, direct air capturing, up to like storing carbon and materials. So you can check that out. But for our work, we are like focusing on afforestation, reforestation, and bioenergy plants and modeling. So to motivate that a little bit, there is a nice overview by Stefanie Rohr by a paper from 2021, and that shows, yeah, like all the options where carbon can be stored in forests, agriculture, yeah, and also on the demand side. And you see that these land-based mitigation strategies are included in nearly all future IPCC scenarios, especially the ones which are more ambitious, like, yeah, lowering temperature below 2 degrees. And there's a quite high potential of these methods to store carbon up to 30%, which is needed to achieve the 1.5 degree target. And as you see here in the plot, reforestation, BECCS, and also reducing deforestation have the highest potential, although I have to say this study is based on a sectoral analysis and also on integrated assessment models. And as I said before, I'm working with land models, like the land part models of ESMs, so which is kind of a different story. And I just figured out actually in the morning that this is a quite important point, that it's not really well reflected in all the CMIP6 simulations, because partly BECCS, like bioenergy plants, are represented as first-generation bioenergy plants, like maize, for example, and they are not as productive as, for example, other second-order generation bioenergy plants, such as miscanthus. And I think this is an essential point, because you will see, if you compare those numbers to the results from ESMs, that those numbers are much lower. So this is also a claim to include those land-based CDR options more there. Yeah, just a quick overview. So I just briefly talk about the two methods, then how they are at the moment implemented in the two models, then yeah, some previous studies and current work I'm doing, and also planned work for here. Yeah, so the potential of those two methods, as I said, those numbers differ a little bit from before because they are more based on the ESM. So it's about 3 gigaton of carbon or CO2 equivalent per year. And also you see those wide range here, like spanning from close to 0 to 6. And also the area needed has a really wide range. And yeah, I think we're all aware of also those co-benefits and side effects. Biodiversity, yeah, afforestation can recycle water and improve air quality, and there's always, for both methods, like also for bioenergy plants, this conflict for land use and for food. Yeah, so also for bioenergy plants, you see that the spread is really wide, and this is also partly because some of the estimates include fossil fuel substitutions, for example, others do not, so it depends on how far they are included there in those numbers. Okay, sorry. So how are the two methods implemented in JSBach? So this is the land model I'm using currently, and CLM, although this is put together quite quickly, so you probably know best how it is implemented in CLM. So in JSBach we have 4 tree PFTs, whereas you have 8 tree PFTs, and in the current version of JSBach there are no forest age classes, for example. So there's a later version, but in our one, yeah, in ours, there's also no forest management, for example. So yeah, in that term, we are quite limited. And so there's also no dedicated PFT. So I know from other models, for example, LPJML, they're using forest plantations, and then you, I guess you end up with higher productive forests there because they're just like intended to produce, like to store carbon and to produce material. And then the wood harvest in both models is used from the LOH2 data, like the mass-based wood harvest. And then in Scheelsbach, we have a PFT, so a dedicated PFT for bioenergy plants for Miscanthus and also for Panicum. And there, oh, I guess I mixed that up. So there you have, so in Scheelsbach, you have 59 to 71% of the above ground biomass harvested, whereas in CLM it's 70%. And yeah, we also don't have agricultural management, so there's no fertilizer, no irrigation used. But even in CLM, where I think it would be possible to use that, there's really low fertilization for switchgrasses and none for Miscanthus, and also no irrigation is needed for that kind of plants. And yeah, I also have to say that those bioenergy plants, they are, in Scheelsbach at least, they are not in the official CMIP6 version. So it's more like a side branch, which was done by a PhD student some years ago, and we just digged that version out and made it alive and advanced it a little bit. So it was not used in any of the studies, and also not in CMIP6 so far. So I think that could be an essential point also going forward to CMIP7 here. And yeah, then there's some open issues, and I especially want to raise the first point on land use transition. So it was shown in a paper by Di Vittorio from 2014 that there's actually a kind of a loss of information regarding afforestation. So he showed that only about 22% of the afforestation signal from IAMs ends up in the CMIP6 version. I think that was based on CESM also. So, so this was then back then in the CMIP5 models, but I also had a look at CMIP6. Like even there, there's really little area for afforestation, reforestation. And as I mentioned before, like many of the CMIP6 model do not include like this dedicated bioenergy plants, but they rather use maize or whatever crops they have in their models to represent that. Yeah, what I mentioned before, like there's limited forest management in Scheelsbach. And I don't know, I guess I just skipped the previous studies. There were just 2 major previous studies on afforestation and bioenergy plants yet. And then there was one very interesting study from Cheng et al., which compared afforestation and BECS for the US. Okay, and then to the current work I'm doing in Munich. So there, in this study, I compared the 2 methods, and I want to answer this question: which of the 2 methods is more effective in storing carbon away? And then when you answer this question, you end up with this, you can simply answer the questions by it really depends. And then we identified several measures on which it depends. So it depends a lot on the level of fossil fuel substitution, depends a lot on the area, depends a lot on the time scale. I guess I missed one, but however, so we set up this simulations using the LOH2. Oh, time is running out already. Okay, so setting up the LOH2 area for bioenergy plants and comparing this area for bioenergy and afforestation. And yeah, I guess I have to hurry up a little bit on this. But yeah, just to show you like this different indicators and potential we find here. So what you would expect if you don't have fossil fuel substitution, and you see like on the upper end, oh, the colors are really different. So it's like the brownish indicates that bioenergy is more effective, and then blue indicates that afforestation is more effective. So you see, if you have no fossil fuel substitutions, of course, afforestation has a high benefit, and then on the other way, if you have full fossil fuel substitution, then bioenergy plants will be more successful in 2100, but it really depends on the area. So on the upper left, you see the year when actually bioenergy plants become more effective, because on a long time, they have an advantage if they are stored away. So if you use fossil fuel substitution, and then also it depends really on the level of fossil fuel substitutions. And you see those spatial differences. So they indicate areas, for example, in South America, where bioenergy plants are kind of suited better, and we want to dig a little bit deeper in that. So looking at evapotranspiration and latent sensible heat fluxes to identify why they have an advantage in certain areas. Okay, I'll skip that. Just to take home messages here. So effectiveness really much depends, especially on fossil fuel substitution and also the carbon capture and storage capacity. And the carbon sequestration is mainly driven by the vegetation carbon in the trees and not so much in the soil carbon. Although comparing with other models, JSBACH always underestimates soil carbon. So that might have to be evaluated in other models. And then also, I also did simulations with climate forcing SSP 370, and there you see that in that case, afforestation would have a higher potential because they have more CO2 fertilization in that case, so they have an advantage here. Yeah, and then as we saw before, there are some areas where afforestation, reforestation is more beneficial and others for bioenergy plants, and I have to identify exactly what's the cause there. And what I'm planning to do here, so I want to compare the two models, of course, in terms of biogeochemical and also biogeophysical effects. And I think the point which I already raised before, which would be more important, is to identify in how far they, those two carbon dioxide removal methods are underestimated in current CMIP6 models and also simulations. Because as we heard yesterday, the CMIP6 simulations are still highly used in many communities. So I think it's important to get that right there. And yeah, I mean, it's still open, and I'm happy to discuss further ideas and suggestions.
We're going to talk a lot over the summer, but I'm curious about your statement about the afforestation or reforestation not being correct in the CMIP6 models, because I thought we had addressed that, and so maybe it's not a fair question to you, but we were seeing initially, right, as we developed LUH2, that many models were not getting the reforestation, but we tried to resolve it, and we were hoping models actually adopted what we did, but now I don't really know whether they did. But I thought we didn't seal them. I know we didn't seal them wherever Peter is. So,
at least what I saw for JSBACH, it's quite a small area still, like also compared to what the IAM output is. So, I really want to dig in deeper there because I'm not fully aware. But if you follow the model chain from like what IAM output is, and then what I get for JSBACH input. So if I look at this output, it really differs. I'm not sure about the other models actually. Maybe maybe that was corrected for CLM. I don't want to make a claim there, but I think we can look at this in more detail.
Thanks. We have Jyoti Singh, who is online. Oh, Rosie
Hi.
actually has her hand up. Rosie, do you want to ask your question?
Sure. I was just wondering about this business of the path dependency of the carbon sink from afforestation and BECCS, and you said that the sink was high in SSP 3.7, and I wondered if you tried like any very aggressive mitigation scenarios, or if you plan to do so, to sort of think about like, you know, whether countries are sort of like putting themselves at risk of being in forest carbon debt under a kind of very high CO2, sort of like a high CO2 removal circumstance.
So you wonder if I plan to have some high or large area CDR and calculate that potential?
No, some like using sort of climate scenarios that are very aggressively mitigating, sort of getting to sort of negative emission territory.
I didn't plan to do it yet. So like one of my colleagues, Yanis Moustakis, is having one afforestation scenario where he, like, I don't know, based on a number of assumptions, coming up with afforestation area of 900 megahectares. So I guess that would be kind of aggressive.
Okay, cool, thanks.
Rosie, just real quick, at Scenario MIP meeting next week, I'm going to propose that we do that in the next generation. So test some really aggressive scenarios. So we'll see what they say.
Go, Dave.
Can you stop sharing so that we can get things to work in the room? And then once we have everything working, okay, great. Great. So yeah, Jyoti, you can start sharing now.
Okay. Can you see my screen?
Just go full screen. Perfect. Great. Thanks. Yes, our next speaker is Jyoti Singh, who will talk about the effect of tropospheric ozone on plants.
Hi, everyone. So this presentation is about evaluating the impact of tropospheric ozone on plants with improved new ozone damage parameterization in CLM5. This work is done in collaboration. Oh, okay. Can you hear me now properly? Is it okay? My sound? Can you hear me? Hello? Okay. Okay, I'll try to go loud. So this work is done in with collaboration with Danica, Lily, Alan, and Manuel. I'll just start with the basic introduction, that how ozone is formed, and then how NOx, VOC, and SO2, they react with sunlight to form ozone, and then it is taken by the plant leaves through the stomata opening, and as the ozone, it gets into the substomatal cavity and mixed with the aqueous solution, it forms reactive ozone species, which then damages the cell membrane and leads to reduced net photosynthesis, stomatal conductance, and hence carbon assimilation. In CLM5, the ozone damage parameterization is implemented. There are two ozone damage functions, but the one I'm talking about is implemented by Danica, and it is implemented which is the ozone damage influences photosynthesis and stomatal conductance independently based on the cumulative uptake of ozone, which is dependent on ozone concentration, time of exposure, total time of exposure, and the stomatal conductance of the plant. It is for three broad plant functional types: broadleaf, needleleaf, and crops and grasses. So this is a table from Danica's paper, and this is the function called ozone mod.f90, in which the ozone damage parameterization is implemented, and it is implemented for crop, broadleaf, and needleleaf. So I'll just move to the next one. And this slide is basically to show what is the correlation found between cumulative ozone of uptake of ozone and how it changes the photosynthesis and stomatal conductance under the chronic exposure. So this is basically the same figure that I just extended. So Danica used the data from 1970 to 2011, which is from literature, and then I built upon the data, adding more data from 2012 to 2022. And so basically, this is the reason to have more data and build the same function was to see if the correlation between the change in photosynthesis and a cumulative uptake of ozone is improved or not. Because Danica found really the correlation was really poor, and with even the more data, the correlation was still poor. This is for photosynthesis. This is for stomatal conductance across all the crop types, wheat, soybean, and rice. And the next one is for trees. And for trees as well, the correlation coefficient was really poor, except for tropical evergreen trees. It was better for it. It was good, in fact. So then the next step was to think that how can we improve the correlation of can we improve the correlation by including more predictive variables, because currently the only predictive variable is cumulative uptake of ozone. So we did the same, and this is a graph from the study which I presented in the last working group meeting held in this year of February. And this is basically a regression of change in photosynthesis due to chronic ozone exposure, and this graph particularly is for rice. And it has 4 plots, and each plot is for how the photosynthesis is changing under various ozone exposure, because the data is from all over the world for all the rice types and different ozone concentrations. The only difference in this graph is the predictive variable. What are the predictive variables that are used to predict the change? So in the first graph, the predictive variable is cumulative uptake of ozone, which is the one which Danica used to implement the function. The second plot is with COO and also the ozone concentration. The third one is with the ozone concentration, controls stomatal conductance on the plant, and the total time of exposure of ozone. And the last one is COO, ozone, control stomatal conductance and time. And we found that the correlation coefficient was improved from 0.015 to 0.86, which is great. And it was improved for all the other graphs, like for graph number 2 with 2 predictive variables, the correlation coefficient is now 0.649, and the third one is 0.77. So it was really great. And we chose the fourth one because it has the largest improvement. And this is the next one just for stomatal conductance, and we found the similar improvements in change in stomatal conductance as well. This is just a table that I made just to show that how, because the plot was just for rice, and this is to show how the relationship is improved for all the plant types. And this is for photosynthesis, change in photosynthesis. And you can see the red one is just with one predictive variable, which is cumulative uptake of ozone. And the R square is really poor here, like 0.01, 0.012. And in the last category, where the predictive variables are 4, which is including stomatal conductance, ozone concentration, and time, R square has really improved tremendously. Not for all the categories. Maybe if you take all trees and temperate deciduous trees, the R square is not improved much, but for all the other categories, R square has improved really well. So the next thing was how to implement these parameters that we found from the observations into the CLM5 crop model. So this is really very preliminary results. I just started working on these like in past 2 weeks. So this is not very concrete, but it will definitely lead to a better implementation idea and approach. So the text experimental setup was for a single point, and it was for the time period of 2011 to 13. And the dominant PFT, or the only PFT, was spring wheat, and the ozone damage parameter, the new ozone damage parameterization is compared with the without ozone simulations and the one which is originally there. And there are 3 concentrations that I took for these test: 100, 70, and 40 ppb. And there are 2 equations. They're just to have an idea that how we are implementing the damage function in the model. So the first one is the original, which is in there. So this is basically I'm just showing for the photosynthesis. So a photosynthesis coefficient is derived or computed, and there is an intercept slope that is it is constant. It is there in the damage function, and there is a coefficient of which is multiplied to cumulative uptake of ozone, and CO is the predictor variable that predicts this coefficient or the slope. And the next, the new ozone damage parameterization has four predictor variables. So there are 4 coefficients and 1 intercept. And using these values, a photosynthesis coefficient is computed. And again, the variables are variable, of course, but the coefficients are constant. And this is, I'm going to show for just wheat. This is just, I will not go into details. This is just the values that I got from the parameterization and that I'm going to use in the implementation. So x1, x2, x3, x4 are the 4 variables, and these are the values of the intercept and the 4 slope of the 4 variables. So this is the result that are for 100 ppb concentration. Now, well, there is now we can take daily hourly ozone concentration from atmosphere due to the new addition by Adriana Foster. But in this run, I'm just taking a constant value of ozone, which is 100 ppb. And the first one is 24. There are 3 plots. One is for photosynthesis, accumulated 24-hour photosynthesis. The second one is total leaf area index, and the third is GPP. And the blue color simulation is without any ozone taking consideration. The orange one is ozone damage on, and the third one is a new ozone damage function. As you can, I mean, this is 100 ppb, and so I might expect that the drop will be a lot, but there is a sudden drop in photosynthesis and also in GPP. So I'll have to look into it, that what the reason is for this sudden drop. So the next thing that I look is how the ozone uptake, how ozone is taken, or the ozone flux in sunlit leaves. The second one is sunlit leaf stomatal conductance, and third one is canopy transpiration. So compared to photosynthesis, there is no sudden drop, or at least not as, the drop is not as large as compared to photosynthesis. And the reason, this is what I found in the analysis, is the sudden drop in the photosynthesis is when the stomatal conductance of the plant, increases with the growth of the plant. And I think the reason for this might be because in the observation data set that we use to create the parameterization do not represent, the stomatal conductance value of the crop growth. So so different plants have different stomatal conductance. So we have plant categories, but there is no growth categories for plant. And so this might be a reason that the stomatal conductance, when stomatal conductance within the growth phases, different growth phases of the plant is changing, it is, changing the photosynthesis and stomatal conductance drastically. This is, I'm showing it just for the 3 concentrations, 100 ppb, 70 ppb, and 40 ppb. And again, in the left plot, the down left plot, it's a photosynthesis, and there is again a sudden drop in photosynthesis in all the 3 cases. For 100 ppb, it might be like, it might be a case because the concentration is quite high, and so will be the cumulative uptake of ozone. But I did not expect this for 40 ppb. It is not as sudden as 100 ppb, but still the dip is really huge. So I think the reason might be that in the parameterization, stomatal conductance, the variable stomatal conductance is not, is not doing a favor or not predicting well. So I might have to look for a parameterization, because I have other parameterizations which do not include stomatal conductance. So I would like to try implementing that parameterization and see how it will affect the photosynthesis and stomatal conductance. So some key findings or some findings from these preliminary simulations are that the new ozone parameterization is not very sensitive to changes in ozone, which is not I expect, because if you have more variables that, especially if you have ozone concentration as well as a variable, it should affect the photosynthesis and stomatal conductance more. And the decrease in photosynthesis is very large compared to stomatal conductance. One reason might be the model's time frequency and the reason I'm saying that because we are implementing we are calculating the coefficients at early step. When we derived the parameters, it was mostly on daily basis or mostly on daily basis. So we also had to maybe fine tune the parameter based on hourly data. And the one more important thing is define the upper and lower limit of the coefficient, not only one, because it will also impact, because it was just for single point simulation. But when I did some global runs, the model was, there were errors saying that the values are nan or something else. The reason might be because the coefficient values are like, they are producing unrealistic values. Yeah, so with that, I will that I'll be taking any comment, feedback, or questions. Thank you.
Can't see if there are any questions online. If so, maybe. One raised hand. All right, whoever raised their hand, could please ask.
Yes, yes, maybe have a stupid question. I mean, for this ozone damage, why don't you investigate the regression between the cumulative ozone concentration or between the stomach and the conductance? Because you are lacking of data, or I mean, yeah, maybe this is a question for Duncan as well. For when you apply the ozone damage to the photosynthesis, why you don't consider to derive regression between the ozone, either its ozone concentration or cumulative ozone concentration, and the stomach conductance instead of stomach conductance, photosynthesis.
I'm sorry, if I got your question correct, you are saying that why don't you derive a relationship between photosynthesis and stomatal conductance?
No, stomach conductance and this cumulative ozone concentration.
Oh, so you want me to derive a relationship between stomatal conductance and CuO?
Yeah. Why don't you do that? Because you're lacking of data of the stomach conductance.
So in the new parameterization, there are 4 predictor variables. I'm using stomatal conductance, CuO, total exposure time, and also ozone concentration. So I am using that. What I was trying to say was that in the parameterization function, when I was deriving it from the data set of literature, it was representative of different plant types. So we classified different plant types, but it is not probably representative of the stomatal conductance at different crop phases. So we might also need to look into having a data and deriving maybe the ozone damage function based on the different crop growth stages. So that's why if the stomatal conductance is increasing or decreasing suddenly during the crop growth phase, this new ozone damage function is capturing the damage wrongly, because again, it is not built on a better representative data of crop growth phases.
Okay, thank you.
All right, great. Thanks again to our speaker and to all of our speakers. And Abby, our co-chair, do you have any words that you would want to close the session with or start the discussion session with? Sorry to put you on the spot.
Sure, I guess I'll just say thanks, everyone. I'm sorry I couldn't be there. I would love to hear discussion on this last session or just discussion generally about directions of the BGC working group. I really appreciate everybody participating, and I think we can see that there's a sort of wide breadth of things that fall somewhat under the biogeochemistry working group because they involve having to couple many parts of the system together, which doesn't exactly fall under any of the other working groups. So thanks everyone for the conversation today, and looking forward to the upcoming discussion.
Great. Yeah. So to that point, floor is open for discussion. Dave standing up.
You know, we had several talks, right, during this session that sort of thinking about CMIP7 and what we're going to do for CMIP7. So, you know, I guess those conversations are just starting to, well, they've been ramping up and they're now becoming more significant. And I'm not sure what my point is here, except for that I'm going and Ben's going and Peter Lawrence are going to Scenario MIP meeting next week. And it is an opportunity for us to push for a few things that we think might be important in scenarios. So maybe I can just say, if anyone wants to talk, either say something now or the rest of the meeting, you know, if you have something you'd like me to bring up at scenario meeting, I can try to do that. As I kind of implied to Rosie, that one thing, you know, two things. One, emissions-driven scenarios, I think that Ben already proposed, and Ben said he's been spearheading with other people that, and so we'll just support that idea that we need more emissions-driven scenarios, as much as it's going to upset Keith. But I do feel like we have to at least have the capability in CSM3 to do emissions-driven. And the other thing that I'm planning to try to promote is actually related to the work that Sabine showed, is you know, some alternative mitigation-based scenarios, which was we kind of half baked it into CMIP6, but it wasn't done very well. This time, try to do something more intentional and say, at a low emission scenario, the target we're trying to get to, you know, what are the consequences of different decisions in terms of, you know, our naturally based solutions, reforestation or bioenergy. So I'd like to see a simulation that helps us kind of probe that, but it might be a little narrow. So if we can think of ways to expand that a little bit, that might be more attractive to people. But I feel like was a big missing piece from CMIP6. So those are the two things I'm going to try to bring to that meeting, and if anyone else has a comment.
Maybe can I just ask a clarification point? In terms of emissions-driven scenarios with things like bioenergy, I mean, do we have all the pieces in place to do that right now? Like, because, you know, a lot of, as I understand, the emission-driven stuff is sort of driven by these kind of global emissions things, and rather than, you know, the actual.
Yeah, I mean, we have, you're right, as a point, there is a step we would need to take, because we do have bioenergy crops, right?
Right, but do we have the CCS part of it?
Right, yeah. So we would have to add the CCS and the fossil fuel substitution part to an emissions-driven scenario. So we did that in the paper that we're trying to get published now, you know, after the fact, post-fact, made those calculations. But yeah, we'd have to make that online. So yeah, good point. I kind of forgotten about that.
Okay.
Dave, can you push for more time? The timelines are, I find, terrifying.
Sure. Wim just asked for less time, and so you're in the wrong meeting for that. But yeah, I will, and you know, we'll see what Gyokan's timeline was. He showed, not Gyokan's timeline, the timeline Gyokan showed on Monday was quite aggressive, right? And then we got an email, a bunch of us, saying that the scenarios will not be ready till 2026. That email came in on Monday afternoon, I think, or Tuesday morning. So I'm going to find out next week. But yeah, obviously we're always pushed for more time, and we rarely get it. So.
Should we take an incredibly biased sample of hands of who wants more emissions-driven scenarios in CMIP7? Actually, I was expecting to be more unanimous now. Now I'm curious. So because I can't possibly think of a more biased sample design than to sample the biogeochemistry working group.
Can I make a comment on something Dave said?
Please.
Just a reminder that thinking, and I know that you all are thinking about this, but somehow designing these experiments that are exploring natural climate solutions to make sure that we're doing them in at least a coupled atmosphere. It sounds like you're thinking also about how do you fully do them in an emissions-driven context, which makes a lot of sense. And I know that those are harder and more computationally expensive, but I just think we're really not getting the full picture of what's going on if we're not at least coupling the atmosphere when we're changing a lot of plant cover on the surface.
Thanks. I guess I have another, so to the last point that I was asking before about the, do we have the pieces in place to do these, sort of process-based, emissions-driven mitigation scenarios? So the the straight bioenergy part's straightforward. The BECS is like a slight modification. What about on the ocean side in terms of things like ocean alkalinity? Like how if we assume that this if Ben is successful, right, or if this effort to get a much greater emissions-driven and mitigation-focused part of CMIP 7 is in place, like will we be able to do other types of actual process-based mitigation scenarios, and what would be required if not?
I don't know. We haven't really explored these experimental configurations. In the experiments that I'm familiar with in CDR-MIP are not particularly challenging to implement. So adding an alkalinity flux, for instance, is not challenging to implement. But beyond, I don't know what other sorts of model experiment configurations people are dreaming up.
Right. I guess the other would be sort of enhanced weathering and land-based alkalinity, and it seems like that requires that alkalinity transport from the land through the rivers to the ocean to do properly, which I guess we're a long way off from.
We'll do it with all the spare.
Yeah, exactly.
People time we have.
Yeah, totally. Yeah, it's gonna be awesome. Yeah.
Yeah, just to mention, there's not only CDR Terra, there's also CDR Mare, and they are also planning some ocean alkalinization simulations within MPI ESM.
All right. Yeah, Rosie.
Just to say, I was in a meeting last week with a bunch of European system modelers, Happy Center and IPSL and ICON, and they were all, it was kind of about, getting emission-driven capability ready for nitrogen and methane and closing all those cycles and all the different models. And Colin Jones made a big play about asking for more time to get those things up and running. So yeah, he seemed pretty serious about that at that meeting. And also, harking back to Abby's, linking together Ben's and Abby's points, these emission-driven scenarios kind of going to put the biogeochemistry in the firing line in terms of model calibration, right? If it's all wrong, then it's kind of going to be mostly our fault. So yeah, we kind of really need to think hard about how to get solve these spin-up problems. Obviously, I have no insight into the ocean issue, but something something we thought about in the context of some proposals was getting this sort of machine learning spin-up to work for mimics and so on. And yeah, do we need to be thinking harder about that if we want to be having emission-driven calibration activities? That's kind of a rhetorical question, but you know,
Yes,
just put
you
that out
do. Can't think any harder. We're all thinking too hard already.
I mean, yeah, Rosie, right, and we had that proposal, but you know, at least we're in good shape right now if we don't use mimics, which I would prefer if we did, I think, for the permafrost carbon feedback question for one reason. But if we don't use mimics, we don't get to the point we can use mimics, then, you know, we do have the matrix working. So we can actually spin up the land pretty fast right now, which is, you know, that may be a short period window when we can actually do that as we move the model forward. So we can take advantage of that right now. And hopefully, you know, that won't be a problem. So I think it's from the emissions driven, it's going to be the ocean that's going to be the difficult challenge in the near term, unless we switch to mimics.
I'm not quite sure I understand the distinction being made here between the need to spin up in a concentration forced situation versus an emission-based scenario. I mean, if you want to be able to look at the carbon cycle response, if you're drifting at a concentration versus if you're drifting in, I'm not sure why it's being portrayed as something that's inherently harder in emissions-based scenarios. That in concentration, it's hard to look at the carbon cycle as well if it's drifting. And the only difference is it feeding back to the climate system. But if you're looking at the carbon cycle, you want to spin it up, whether you're concentration or emission.
Yeah,
I guess I'm saying that drifting isn't going to be the only problem. In emission-driven mode, it has to be right. Like the ocean compensing has to be correct to get the historical transient to work in emission-driven mode. I think. Does the problem not become harder at all if you have to do it lots and lots of times with different parameterizations?
I'm not sure what I'm not sure I follow. I mean, that applies to the land model too.
Yes. But we're kind of used to that.
It's a little bit of a question whether we calibrate in offline or in coupled, and the difference between the two of those. And we saw an example today where it makes a difference, right, from Amy's talk. You know, so if we don't have to calibrate, if we can get away with calibrating offline and be close enough, which is I feel like we're probably going to have to do. But just to say, Rosie, I think, or actually answer Keith, I mean, I was conflating two things, right? Abby's request for an ensemble of emissions-driven simulations versus just one. And you're right, we got to spin up either way, concentration-driven or emissions-driven. And we know how to do that. We will do it at least once for CSM3. The open question is, can we do it 10 times or more, right?
Right.
Yeah.
Someone should work on that.
Anybody else online? All right. Thanks, everybody. This has been, ambitious, great, and also slightly depressing. Thanks. Bye.
Okay, good afternoon, everyone. Welcome to the Paleoclimate Working Group meeting. Welcome the in-person participants as well as people joining online. And I want to welcome you on behalf of the co-chairs. That's me and Samantha Stevenson sitting here, and also Ran Feng, who cannot be here today. And I want to remind you that in this meeting, to people's opinion, some logistics about the format of the meeting. So we have a total of 15 minutes for each talk. So 12 minutes for talk and 3 minutes for questions. And you will see a warning at the 11-minute mark. So at that time, please wrap up your talk and leave time for questions. And for in-person participants, please walk to the microphone right in the middle of the room. And for remote participants, please type in your questions in the chat, and someone is monitoring the chat. Here is this agenda for today's meeting. You can see we have 2 sessions. There are a lot of exciting talks, and I really look forward to each one of them. And please enjoy every talk. And unfortunately, Ran cannot join us today. And you can see here, we added a discussion there, replace her time for her talk. What is the time now? Okay. Maybe I will stop sharing. And okay, let's get started maybe with the talks. The first one is a talk from Mingming Fu. The title is Revisiting Western US Hydroclimate During the Deglaciation Using Eye Trace.
Hi, everyone. So pleasure to be here today. So title of the talk today is Revisiting Western U.S. Hydroclimate During the Last Deglaciation Using Eye Trace. And I'll begin by giving a little bit of background on the climate of the Western U.S. during the last glacial maximum. So it's been known since the 19th century that the Western U.S. sustained very large lakes during the last ice age. Here on the right is a figure showing the extent of Lake Lahontan and Lake Bonneville, which were huge, and they covered large parts of northwestern Utah and northwestern Nevada. So water budget analyses have indicated that lakes of this size required about 70 to 140% higher levels of rainfall in order to be sustained. And the cause of these wet conditions kind of became more clear with the advent of climate modeling. So, of course, over the western U.S. during ice ages, the largest driver of regional climate change is the large North American ice sheets. Here on the right is a figure showing the ice sheet topography from the I-6G reconstruction. So you can see the 3-kilometer thick Laurentide ice sheet covered much of Canada as well as Chicago and New York. And modeling studies generally indicate that this led to a southward shift of the North Pacific storm track, which brought more winter rain to the western U.S. and therefore explains the presence of these lakes. However, if we look more closely at the paleo evidence, there's a more subtle feature in the proxy record. Here on the left is a figure showing the timing of the lake high stands over the western U.S. This is adapted from McGee et al. 2018. So as you can see from the legend, almost all of the lakes reach their maximum size well after the LGM, generally between 15 and 18 Ka. And some previous compilations have indicated that perhaps the lakes in the northwest sector reached their high stand at a later time compared to those in the southeast, but some of those basins have been redated and generally looks more uniform now. But in any case, the most salient feature is that their largest size is achieved after the LGM. So this is interesting because one might naively think that if the ice sheet is the cause of the wet conditions, maybe it should have been wettest during glacial maximum, but this turns out not to be the case. Going forth, there have been a few studies that have addressed this issue. One publicly available modeling study of the last deglaciation is the Trace 21K simulation, and this was interpreted by Laura and Ibarra 2019, and as you can see from the left, this simulation basically shows monotonic drying since the LGM, so it's not capturing this wet interval around Heinrich Stadial 1. Another study, which was more idealized, suggested that perhaps freshwater forcing from HS1 could have played an important role. And indeed, I find that freshwater forcing and weakening of AMOC is important, and I'll elaborate more on that very shortly. So for this study, I'll be using iTrace, which is a recent simulation of the last deglaciation. So to just briefly point out the key differences between the older trace simulation and iTrace, the model version was updated from CCSM3 to isotope CESM4. The model is run at a higher resolution of approximately 2 degrees rather than 4 degrees in the older simulation. And one of the larger changes might be the update of the ice sheet reconstruction from ice 5G to ice 6G of Peltier. And on the right is a figure showing the intermediate ice sheet topography used in iTrace. Okay, so now I'll dive right into the results. On the right is a figure showing the evolution of precipitation in the upper panel and P-E in the lower panel averaged over the Great Basin over the course of deglaciation. So the gray curve is the older trace simulation, and the blue curve is the iTrace simulation. So immediately we see that in contrast to the prior study, the newer iTrace simulation actually resolves a robust peak in both P and P-E at 16 Ka. So if we compare the 16 Ka conditions to LGM, annual mean precipitation is actually 20% higher, and P-E is 39% higher. So this tells us that iTrace is doing a much better job at reproducing the wet interval at Heinrich Stadial 1 and compares much more favorably to the geological evidence. So next, we can take a closer look at the change in the P-E patterns during the deglaciation. So here on the right, I have 6 panels. On the upper left is the CESM1 P-E for the pre-industrial. So we see it does a pretty good job at reproducing observed patterns of P-E. Then on the upper right panel is the difference in P-E between LGM and pre-industrial in iTrace. And we see you get wet conditions over the western US, albeit with drier conditions over the northwest. So this is a common feature of climate model simulations of the LGM, and it agrees with the pluvial lakes in this region. So now the lower 4 panels are differences from the LGM. So as we can see in the 18 Ka time interval, we're getting a bit drier than LGM, and then as we go to 16 Ka, all of a sudden we see this very strong wet signal all over the Great Basin as well as along the California coast. Then as we go to 14 Ka, we get a reversal and much drier than LGM conditions. And then as we go to 12 Ka, which is the younger Dryas, then there's a return to LGM-like conditions. So that's to say there's pretty big fluctuations. You're going from wet to a bit drier to very wet, dry, and then seemingly back to wet conditions. But because the largest signal we identify at 16 Ka, and it's next we're going to basically investigate why we see such a strong wet signal during this time interval. So the way we can do that is that iTrace provides these stacked forcing experiments, which means that the ice sheet boundary conditions, the orbital conditions, greenhouse gas, and meltwater forcing are applied iteratively. And I plot all 4 curves on the right. So as you can see, the meltwater forcing is pretty important because there's a large difference in P-E between the simulation that has the meltwater forcing and that which does not. So the meltwater forcing at 16 Ka is actually raising the P-E by about 0.2 millimeters per day. But the orbit and the CO2 also turn out to be important because if you compare to the yellow curve, which is without the orbital forcing and without the CO2 forcing, adding those two boundary conditions is actually raising the P-C by about 0.15 millimeters per day. So it's not just the meltwater flux, but also the orbit and the CO2 are also playing an important role here. So because we have these stacked forcing experiments, we can do this clever linear decomposition by taking differences of pairs of these experiments. So by taking the full 16K simulation and subtracting the one without meltwater forcing, we can estimate the contribution of that forcing factor and so forth for greenhouse gas, orbital forcing. And then if we just take the 16K simulation with only evolving ice sheets and we subtract the LGM, that's the contribution of the waning of the ice sheets. So we see that consistent with what we saw before, the meltwater forcing leading to a very strong wetting signal over the western United States. Then the greenhouse gas and the orbit playing also a role in making this region wetter, but with a smaller amplitude. And finally, the ice sheet retreat in isolation is leading to a strong drying tendency. So we can also better understand why we see these rainfall patterns by doing the same decomposition instead for the zonal wind, the wintertime zonal wind at 500 hectopascals, or U500. So the first forcing factor is the meltwater, which is leading to a very dramatic southward shift and strengthening of the North Pacific jet. Then for the greenhouse gas forcing and the orbit, we see this dipole pattern with deceleration over Canada and acceleration to the south. So these two factors are also pushing the jet equatorwards, whereas the ice sheet forcing alone is leading to the opposite signal and pushing the jet towards the pole, which also makes sense because basically you're removing the topographic obstacle. So another way we can then try and understand why we see these atmospheric circulation patterns by taking a look at the zonal mean surface temperature differences. So here in the blue curve is the total difference in the zonal mean surface temperature between 16 Ka and LGM. Again, we can decompose this into its individual components. And as we expect from the meltwater forcing, this is leading to a shutdown of the AMOC and reduction in the northward heat transport of the ocean. So therefore, it's leading to large-scale northern hemisphere cooling and southern hemisphere warming, as we see in the red curve. The effect of the greenhouse gas forcing and the orbital forcing is leading to a strong polar amplified warming signal in the high latitudes, and the effect of the ice sheet forcing is kind of small. So this is basically, the meltwater forcing is causing a steepening of the meridional temperature gradients in the mid-latitudes, which is basically accelerating the jet by thermal wind balance in this place. And then, whereas the other two forcing factors are basically reducing the meridional temperature gradient and decelerating jet on the poleward side of the North Pacific jet. So all of this seems to make sense, but perhaps the one thing that needs a bit of clarification is the orbital forcing. So the orbital forcing is causing some polar amplified warming because the 16K conditions were characterized by higher obliquity compared to LGM, and this is leading to more insolation poleward of 45 degrees and less insolation to the lower latitudes. Okay, to sum up what I found, I suggest that several changing boundary conditions between the LGM and 16Ka conspired to cause the lake expansions. So the presence of the North American ice sheets led to a southward deflected storm track and wet LGM conditions. The polar amplified warming caused by obliquity and CO2 forcing helped maintain this jet in its position despite the ice sheet retreating. And then finally, the meltwater forcing led to a further shift and strengthening of the North Pacific jet, and this led to the expansion of Great Basin lakes. Afterwards, the ice sheet retreated, and then this led to the onset of arid conditions. With that, thank you for your attention.
Thanks, Mimi, for the great talk. Do you have questions? First in the room, maybe?
Great talk, Minden. I'm curious, you had mentioned that the precipitation required to sustain those lakes during this period was about 70 to 140% more, right? Or 140% increased from specific values. Do you see, can you find that precipitation in your simulations? Because it looks like the precipitation signal is slightly shifted west of the study area.
Just to be clear, that was 70 to 140% higher than pre-industrial to explain LGM conditions. And people think you need about 20% more than LGM to explain Heinrich stadial 1 conditions. So I don't know if in the Y conditions, yeah. So basically in this upper right panel, we see that the LGM is wetter over this domain. Seems to agree with proxy evidence.
Okay, do we have questions from online? No? Go ahead, CJ.
Hi, great talk, Miming. I have a question about the setup of iTrace. It's okay if you are not familiar with that, but my question is, does the model have prescribed a giant lake in the Great Basin during this period, and does it have a lake effect?
Not entirely sure. Maybe Jen would know better. But I don't think it does.
Oh, okay. Because in some proxy record papers, people say that, because the presence of the lake and then the eastern side of the lake would have more wetter conditions because of the lake effect.
Yeah, it can basically re-evaporate and keep raining out. Is that the idea?
Better.
We still have more time for questions. Okay.
Hi, Miming, great talk. Sorry, I'm not a paleoclimate guy, but my question could be very silly because you mentioned about like this iTrace model, it has like isotope in it. But when you talk about like this giant lakes over Western US, you are using like proxy records. Are you actually comparing any of the model like isotope signal versus observations?
For this study, I only used the physical climate variables in iTrace, so I didn't use the isotopes, but
you mentioned about this like meltwater forcing that is very strong. And if the isotope is working correctly, you are going to see a very large depletion of the isotope signal. That is what I guess.
I'm not as familiar with the isotope record over this region, but I think others are working on this, so yeah.
Some thought it might be interesting to compare the model isotope versus the observations.
So in the interest of time, let's move on to the second talk of this afternoon. It's by Chijun Sun. Okay, I will let you read the title of your talk.
Okay. Everyone for giving me this opportunity. I'm Chijun. Some people know me as CJ, but I go either. Okay, yeah. So, Miming just told us all about these interesting findings about hydroclimate change during the last deglaciation. And in this talk, I'm going to explore a little bit about the global ocean or changes in the global ocean circulations that's leading up to these dramatic climate events. So I'm going to focus on these events called Heinrich events. Heinrich events are these climate events associated with the discharge of icebergs from the Laurentide ice sheet into the North Atlantic. And the ice-rafted debris, or the IRD layers, are found all across the North Atlantic in the sediments, and they are the indicators of these Heinrich events. And in this figure here, these blue bars are correlating these individual Heinrich events with proxy records of changes in the Atlantic meridional overturning circulation, or AMOC, and also a Greenland ice sheet record. So apparently, there is a close association with these Heinrich events and the weakening of the AMOC, as well as cooling in the northern hemisphere. So it was initially thought and also done in model simulations that adding lots of fresh water from the melt of icebergs would collapse the AMOC and cause all these changes. But now we have come to realize that these Heinrich events actually occur during these much longer Heinrich stadials. In this figure here, in the middle panel, in the black curve, it is basically a chemical signal of these Heinrich IRD layers. And in the bottom, the green curve shows a proxy reconstruction of the AMOC change during the last deglaciation and beyond. Basically, you can see that the AMOC started to slow down about 1,000 years ahead of the onset of Heinrich event. And it is hypothesized that this early weakening of the AMOC would have suppressed the deep convection over the North Atlantic and caused subsurface warming in the Labrador Sea. And this subsurface warming would gradually erode the Laurentide ice sheet from its marine grounding line and lead to further iceberg calving events and the peak of Heinrich events. Well, but the mechanism for this early weakening of the AMOC is still very much unclear. There's some hypotheses. Some researchers have proposed that there's these European precursor events ahead of Heinrich events. Basically, this figure is showing, at the bottom, is showing a record of debris from European ice sheet. And you can see when it's compared to the red curve at the top, and it's slightly earlier than this Heinrich event. The idea is that the early melting of the European ice sheet would release some amount of fresh water in the North Atlantic, and it would suppress the deep convection by some extent, and then cause the subsurface warming in the Labrador Sea and cause the Heinrich event. And these are some reconstructions of the British-Irish ice sheet based on geological evidence, and you can see that there's a rapid retreat of the British-Irish ice sheet right ahead of Heinrich event 1. So this is some good hypothesis. Well, recently, this series of papers reporting IRD events from the northeastern Pacific caught my attention. So basically, these events are associated with the melting of the Cordilleran ice sheets that's routed into the northeastern Pacific. And these authors named these events CQ events. On the right-hand side, you can see that over the last 4 Heinrich events, there's always a CQ event associated with it. It has been hypothesized that these CQ events are actually our climate response to these Heinrich events, but a more recent improved chronology, as shown in this figure here, these CQ events actually occurred about 1,000 years ahead of Heinrich events. So there's some pretty good faith relationships between CQ and Heinrich events. And I'd like to understand if there's a physical causal relationship behind all of these. And for the rest of this talk, I'm going to show our new simulation results and also propose a new hypothesis that's linked CQ events and Heinrich events. So here's our experimental design. We run our freshwater holding simulations on CESM 1.3, and we focus on CQ event 1, which occurred between 19 to 17,000 years ago. And we're going to use the iTrace 19K boundary conditions to best approximate the mean climate state when CQ1 occurred. We ran 2 sensitivity tests with 0.2 sphere drop and 0.5 sphere drop of fresh water added to North Pacific region for 400 years, and that's equivalent to 7.5 to and 18.8 meters of global sea level rise in these simulations. When you compare it to a reconstruction of global sea level change, it is well within the range of these reconstructions. So there's nothing crazy in our experimental design here. At last, we also added passive dye tracers into the same region as we put fresh water, just to track how the fresh water is mixed and transported in our simulations. So here's our results. So basically, in both simulations, we observe a weakening of the AMOC. Right? The AMOC is weakened by 11% in the 0.2 sphere drop simulation, and weakened by 25% in the 0.5 sphere drop simulation. This is interesting because it suggests that the AMOC can be weakened by the CQ event alone without any additional freshwater input directly over the Atlantic Ocean basin. So here the dye tracers allow us to see how it happened. Right? And you can see that these dye tracers were initially added to the North Pacific. It's quickly transported into the Indian Ocean through the Indonesian through flow, and then into the Atlantic from the south of Africa, and eventually it made its way to the North Atlantic. If we quantify the dye tracer concentration north of this red line, and we can see in the figure on the right in red curves, the North Atlantic start to see these freshwater and dye tracers starting in about model year 50. And it is exactly the same time when we start to observe a weakening of the AMOC in these simulations. So this suggests that the transport of freshwater from North Atlantic from the North Pacific to the North Atlantic is responsible for this weakening of the AMOC. But the important question is, could this trigger the Heinrich events? Does it cause a subsurface warming? Well, the answer is yes and no. So in these simulations, which shows changes in temperature, changes in the mean zonal temperatures in North Atlantic at depth, you can see that there's some subsurface warming in both simulations, and of course the response is stronger in the stronger forcing simulations. But the subsurface warming only extended to about 45, 50 degrees north. It doesn't go all the way to the Labrador Sea. If we compare it to a more traditional North Atlantic hosing simulation, you can clearly see that the warming signal would go all the way into the polar region. So this difference is important because if we don't warm up the subsurface Labrador Sea, it does not trigger Heinrich events. But we further look at the spatial pattern of the subsurface temperature change. Although we don't see a subsurface warming in the Labrador Sea, but we see a subsurface warming in the northeastern Atlantic off the coast of the British Isles. This is actually consistent with the subsurface temperature proxy record showing an abrupt warming right before the Heinrich event. And actually during the Heinrich event, there was a cooling. And this unique simulation result agrees with the proxy record. This sort of support that our simulation of the CQ event 1 is valid, right? And so we further find that subsurface warming is located between the subpolar gyre and the subtropical gyre. And if we quantify the strength of the subpolar gyre and compare it to subsurface warming, and we find that both AMOC and the subpolar gyre weakened over the time of our simulation. And so we think that the subsurface warming is jointly controlled by a weaker AMOC and a weaker subpolar gyre. Especially for the subpolar gyre, the weakening of it would transport less heat away from this region in the mid-latitude and cause the heat to accumulate in this region and cause the warming here. So just a quick summarize up till now. So we see these Cordilleran ice sheets discharging event into the North Pacific, and this caused the CQ events. And this meltwater is transported to the North Atlantic and weakens the AMOC and also the subpolar gyre, and it would cause a subsurface warming in the northeastern Atlantic. Now I promised you a hypothesis. Here it is. So we hypothesized that the warming in the northeastern Atlantic off the coast of the British Isles could melt the British-Irish ice sheet from its marine grounding line. And it would produce a little bit of fresh water into the North Atlantic and then eventually cause more warming and more AMOC weakening and eventually eventually melt the Laurentide ice sheet from its marine grounding line. Well, finally, here is a figure that's sort of summarizing the sequence of these events. And you can see that at the top panel, it's a discharge of the Cordilleran ice sheet, which shows the timing of CEQ events. And you can see that it consistently occur a little bit slightly earlier than those discharging events of the European ice sheets. Right? And at the bottom of this figure is the Heinrich events, right, and in red, and Heinrich events always occur last. So this sequence of events basically supports our hypothesis, and this opens a door for new discussions about the cause of these Heinrich events and the deglacial climate change. So with that, I'm happy to hear what you think about this. Thank you.
Thank you, CJ, for the great talk. Do we have questions? Maybe I share first, and then.
I have two quick questions. One is when you set up this simulation, whether you lower the sea level or not. The other question is now you run your synthetic experiment for 400 years. What if you run it, like, say, 1,000 years? Even for the 0.2 sort of simulation, maybe you can see a stronger weakening of the AMOC.
Question, Aishu. So for first question, we branched our simulation from the iTrace 19K time slice. So it has the boundary conditions resembling the reconstruction of the topography and ocean sea level. So it is accounted for in our simulation. And the second question or suggestion, I think it's great to extend the 0.2 sphere drop simulation. So in our 400-year simulation, we already start to see stabilization of the AMOC and lots of different climate parameters, but with large variability. So I think it would be interesting to run it longer, just to see how it would change. Would it eventually homogenize the global ocean surface and doesn't weak AMOC anymore or whatnot? But for the sake of the CEQ event, if we just hose it for too long, that would be just too much fresh water. That's unrealistic.
We have a question from online. Maybe Kara is next, and then Honghai.
So assuming that the mechanism that you have here was correct and you have melting of the British ice sheet, would that produce enough meltwater, like hosing in the North Atlantic, that you would actually get then discharge off of Laurentide ice sheet for Heinrich events, or is this insufficient?
That's an interesting question. But I mean, if you add fresh water into anywhere in the North Atlantic, it will always slow down the AMOC more effectively than what we did for the CEQ event. And I guess it depends on how much water you add it to, and maybe that can be constrained by geologic records. But also, I think different models have different sensitivities to the freshwater forcing. So it's an interesting and important question, but pretty difficult to tackle at this point, I think.
Yeah, I have a question about your result that's showing the spreading of the fresh water from North Pacific all the way to North Atlantic, the subpolar North Atlantic, right? You use this passive tracer to show the timing, which coincides with the weakening of AMOC, but have you checked the salinity anomaly, which I think is a more direct measure of the fresh water amount in the ocean?
Yeah, thanks for the question. Yeah, we look at the salinity change in the simulations, and the salinity, of course, it decreased, and the signal is stronger from the South Atlantic and going towards the North Atlantic. But eventually, because of the effect of weakening of the AMOC, the North Atlantic is cooler, so there are probably like more sea ice that could play some additional feedback role in there, and maybe can produce more meltwater when sea ice melts. Yeah, but we think that the transport of fresh water is a primary cause of the weakening of the AMOC, and we think the dye tracer provides strong evidence for that. And I guess it's most clear. It's clearer than just using the salinity because there is large interannual variability in salinity and doesn't really tell us the impact of the fresh water we added to the North Pacific.
Yeah, can I ask a quick follow-up question about fresh? Yeah, just as the fresh water makes its way from South Atlantic to the North South Polar Atlantic, I would imagine that should also affect AMOC in some way, rather than just when the fresh water reach all the way to the South Polar, then you see the slowdown of AMOC. Have you seen any changes in the AMOC when the fresh water?
The interesting question. We did notice that the AMOC actually started to strengthen a little bit before it weakens. Maybe that's something that's related to what you mentioned, but we haven't looked into the detail of that. Thank you.
Okay, our next talk is virtual.
Can you hear me okay?
Yes, we can, but give me 1 second, please.
No problem.
Okay, Joseph, I'm going to spotlight your camera and then you should be ready.
It sounds great. And then can you all see my presentation okay?
Yes. Please take away, Joey. Thank you.
Yeah, hi, thanks for having me today. My name is Joey. I'm a first-year grad student at the University of Connecticut, where I work with Clay Tabor. And today I'm going to talk about a question that I think is pretty interesting, and that is, did the Western Arctic ice sheet collapse during the last interglacial? Oops. So why do we care about the LIG? Well, for our purposes, we care about the fact that the sea level was about 1 to 5 meters higher than pre-industrial. And so with sea level potentially 5 meters higher, this requires some contribution from both the Greenland and the Antarctic ice sheet. And in fact, some proxy signatures that we're going to look at today allow for the possibility of the West Antarctic ice sheet collapse. That's the rapid retreat of the West Antarctic ice sheet. And those proxy signatures we'll look at are water isotopes, mineral dust, and ocean sediments. And so the key motivation here is to understand Western Arctic ice sheet collapse during the LIG using CESM and looking at these different proxy records. So our methods, we're using the water isotope enabled CSM, so ICSM 1.2, and currently we're at 2 degree horizontal end and atmosphere and a 1 degree ocean. Our PMIP boundary conditions have a solar configuration right at 127 Ka, and greenhouse gases just a bit less than pre-industrial. But crucially, we have 3 different Western Arctic ice sheet topographies. We have a pre-industrial ice sheet that we're using for both our pre-industrial control run and for our LIG simulation with the pre-industrial ice sheets. We also have a partially collapsed and a collapsed ice sheet that we're using just for LIG simulations. So we're going to compare all these different simulations to see how we can reproduce the proxy signals that we're looking at. So a tale of 3 proxies, and our first one is water isotopes. So I'm talking about water isotopes. I'm talking about ice core delta 18O. So this figure over here from Masson-Belmont et al. 2016, they looked at 6 different ice cores in Antarctica that went back to the LIG. So during the Holocene, through the deglaciation, you have this smooth plateau kind of through the LGM, and then it sort of transitions kind of smoothly to a plateau during the interglacial, during the warm period. That's different from the LIG, where we had kind of a plateau at the penultimate glacial maximum and then a smooth transition up to the interglacial. But then there was this really large anomalous peak and kind of shoulder through the interglacial at the LIG. And so what we're going to look for in our simulations is that we have this anomalously enriched isotope signal in the LIG. So what does our modeled delta 18O look like for now? So here it is. This is the anomaly in delta 18O for the LIG compared to the pre-industrial. And so with the pre-industrial ice sheet, delta 18O doesn't really change a whole lot, maybe a slight enrichment. But when we start to change ice sheet topography, it gets pretty different. So we have this big enrichment signal over the Antarctic Peninsula and parts of East Antarctica, and also some depletion inland. So ice sheet topography definitely matters a lot here, but what does it look like when compared to the proxy record? So this plot here, again, is using data from that Masson-Delmotte paper for those 6 different ice cores. And each column is an LIG simulation for a different ice sheet. So the pre-industrial partially collapsed and collapsed. And what I've done here is taken the anomaly from the ice core minus CSM. So it's ice core, LIG minus pre-industrial minus CSM, LIG minus pre-industrial. And you can see right away that the collapsed records are the closest to 0. So they reproduce the collapsed ice sheet reproduces our delta 18 node signals the best. So here are ice core locations, and all of these are within 1 per mil. And I'll note that for the time being, we're just at 2-degree horizontal resolution. So this, like Taylor Dome and some of these other locations, might actually change a little bit when we branch to a higher resolution. So why does it change so much? I think the majority of the signal is just a lapse rate signal. So where you decrease elevation, and this is our elevation anomaly. We decrease elevation, we get higher temperatures, and just spatially that appears to match where we're having our enriched delta 18 nodes. So I think that explains the majority of the signal. I think there's potentially some other stuff happening as well, but that's most of it. So as some of you might know, you can simulate water isotopes during the LIG in a couple of different ways. And so I think it's important that we have some other proxies to corroborate our argument. So next, we're going to look at mineral dust. So the same ice cores that we get our delta 18O from, we can also get a dust record from. So this is a figure from one of our collaborators, Sarah Ahrens, and she looked at dust in Taylor Glacier, kind of across the Ross Sea from West Antarctica. And first, we're going to look at the Holocene dust, so these blue dots. And the geochemistry here closely matches South America and Victoria land, which is kind of local to Taylor Glacier. But when we look at the LIG, it's pretty different. So you actually get dust geochemistry that much more closely matches the West Antarctic Rift system and gets a little bit farther away from South America and Victoria land. So there's a change in geochemistry, potentially some subaerial exposure here. But adding another figure to the mix, this is from Austin Carter, who's actually Sarah's grad student and another collaborator. Allen Hills is a location right next door to Taylor Glacier. And I'll say that I don't have it included here, but the geochemistry signal is pretty similar at Allen Hills. I like this figure because it shows the size distribution of the dust. So you can see you have much finer dust through the PGM, and then you get into much coarser grained dust during the LIG. And so if it's coarser grained, that suggests that it traveled a much shorter distance to get there. So we have locally sourced dust. It changes in geochemistry from what we see during other times. So we're going to look for a change in regional circulation that can potentially explain this difference to the Holocene. So looking at the possibility for regional dust transport, this figure is quivers are the winds and the coloring is the speed. And this is just pre-industrial. So kind of business as usual. We have winds kind of going from the far part or the bottom part of the Western Arctic Peninsula, sort of around the Ross Ice Shelf and towards Taylor Glacier and Allen Hills. We know that we don't get dust from the Western Arctic Rift system too much in these locations during the pre-industrial, but also the location of the rift system kind of runs along the tip of West Antarctica and sort of along the far edge of the peninsula. In some areas like the Ellsworth Mountains are where we expect these volcanics to come from. So we don't think that this can explain it quite yet. And then when you look at the LIG with the pre-industrial ice sheet, the winds really don't change a whole lot. But that's a different story when we start to collapse the ice sheets. So you can see with the partially collapsed case, when we remove the Ross ice shelf, we get really strong winds kind of going over where the ice shelf used to be towards Taylor Glacier and Allen Hills. And so that would be necessary to deliver those large dust fragments from West Antarctica there. But I don't think that with the collapsed ice sheet, we're really picking up a lot of stuff from the far edge of West Antarctica. I think that's only really happening with the fully collapsed case over here on the right. I think we have these really strong onshore winds coming from near the Ron-Filchner ice shelf area that could potentially pick up some of that volcanic dust from the Ellsworth Mountains and that sort of area, and then also strong winds going over the Ross Sea to those ice cores. And so I think that only in the fully collapsed case do we really get the necessary change in winds to deliver those larger dust volcanics to those ice core locations. So that's great. And our final proxy we're going to look at today is ocean sediments. So what can the ocean tell us about the Antarctic ice sheet? Well, I think it all comes down to the Antarctic circumpolar current. So this is the major zonal transport in the Southern Ocean. For our purposes, we're going to talk about it being driven pretty much just by the westerly winds, as shown here on the right. and by buoyancy forcing, typically the ACC in this diagram from Chapman et al. 2022 is kind of situated at a Southern Ocean front. So that's at a large density gradient. So it's driven kind of by density gradients or buoyancy forcing and the westerly winds. And I wanted to add a note. The ACC is a pretty major carbon sink. So it's mixing a lot of carbon to the ocean floors through mixing and that sort of thing. And so I think it's pretty important to understand interactions between the ACC and the ice sheet for future climate warming scenarios. So looking at our sediment cores, I'm going to draw your eyes to the bottom panels here. We have 2 locations, and these were both collected as parts of separate IODP expeditions. And then this record was compiled by one of our collaborators, Aidan Starr. And so this star is a record from the southern tip of Africa, the Igualis Plateau, and the triangle is a sediment core from the Drake Passage. What we're interested in here is sortable silt, and sortable silt is a proxy for current flow speed, and so this is just going to be our speed of the ACC during that time. And the interesting thing for the LIG is that you have this antiphase behavior between the Igualis Plateau and the Drake Passage. We see the Igualis Plateau kind of slows down during the LIG, and the Drake Passage speeds up. And in fact, this antiphase behavior is true for pretty much every Pleistocene interglacial, but not all of them. And the fact that it's not true for all of them is what I think makes it interesting for climate studies. And so for the rest of this, I'm just going to talk about the Drake Passage. This is another sortable silt record from Toyos et al. But each one of these shaded areas is kind of like a warm period where they saw an increase. A lot of them are interglacials, but you see that some of them have a really fast flow speed and other ones not so much. So some of them, they have a really fast flow speed to the Drake Passage and not so much. And so why is there this difference between interglacials, some of them with a fast flow speed, others not? And I think that the secret there lies within the ice sheet. So what does the model say? Well, no matter what, this is looking at integrated zonal velocity anomaly in the LIG compared to the pre-industrial. And no matter what, we get a faster ACC through the Drake Passage. So with the pre-industrial ice sheet still there, but when we collapse the ice sheet, the ACC moves a heck of a lot faster. And so that's interesting. When you collapse the ice sheet, you get a faster ACC. Maybe some of these interglacials have a collapsed ice sheet and others don't. Now, why is this? So I said there's 2 major drivers to the ACC for our purposes. One of them was the westerly winds. I don't think they're playing a major role here. Here I'm showing you the zonal wind stress anomaly compared to the pre-industrial, and it's actually, there's less stress on the ocean due to the westerly winds around the area where the ACC is speeding up. In fact, our winds kind of slow down during the LIG and slow down even more when we collapse the ice sheet. Instead, I think it's due to buoyancy forcing. So I think that no matter what during the LIG, the ocean's going to heat up a little bit, as the records tell us. But when you collapse the ice sheet, you have more exposed ocean, and the ocean can then absorb more heat. And when the ocean can absorb more heat, you can have a sharper density gradient with depth. So this is a cross section near the Drake Passage. Again, the anomaly. Yeah, the anomaly compared to pre-industrial. And in the collapsed case, we have a much sharper density gradient with depth through the Drake Passage than we do with the pre-industrial. So tying it back, in these Pleistocene interglacials where we have a really fast ACC, that's going to potentially be a collapsed ice sheet, more open ocean conditions in the Southern Ocean, and ones where there's still an increase to the Drake Passage, but not quite as much. That could potentially be a more pre-industrial-like ice sheet. So our conclusion, ice collapse seems to match a couple of different proxy records, water isotopes, mineral dust, and ocean sediments, but at the very least, it makes a big difference in regional atmospheric and oceanic circulation. And looking ahead, we have a lot of work to do. So I need to continue to spin up the model. We're only about 500 years in. We're doing some vegetation changes. We're going to also do some freshwater flux in both the Northern and Southern Ocean. We have a bunch of different time slices, and we want to add passive dust tracers to get back at our dust geochemistry signal. So that's all I have for now. And if there are any questions, I'd be happy to take them. If not, here's my email if you want to ask any questions later on. Thanks. Yeah. You mean like remote response away from the ice sheet, or? Yeah, I haven't looked too far. I did look at the SST signal a little bit, and currently in our simulation, I actually do see some warming the more I collapse the ice sheet in the North Pacific and North Atlantic. But we're only 500 years in, so I'm a little bit nervous about looking too much at the ocean signal, but I haven't looked a ton at the other remote responses yet.
Okay, thank you. We can move on to the next talk. It's in person. It's by Feng Zhu. Oh, okay, thank you.
First, yeah, no problem.
All right, good afternoon, everyone. My name is Feng Zhu. I'm a postdoc here at UNCAR in the Paleo group. Thanks for this opportunity for me to share this study on volcanism. And also, this work was actually mostly done during my PhD journey at University of Southern California under the guidance of my advisor, Julian, and with the help of my co-authors listed here. So, due to the importance of ENSO to the global interannual climate variability, whether large volcanic eruptions can trigger ENSO or El Nino events has been hotly debated since the 1980s. And models tend to suggest El Nino-like response in the year following eruptions. But is it borne out by observations? Well, most triggering-based observational studies support a strong link. For a strong linkage, for example, D13 here. Close of. Okay. So D13 here suggests a strong linkage. They mention that they claim there's a robust response, ENSO response to large volcanic eruptions. However, a recent coral-based observation study by D20 suggests a much weaker linkage. They claim that the relationship is statistically insignificant. So the question is, how should we understand these seemingly divergent conclusions? Are there obvious contradictions between trees and corals? We revisit this question leveraging the LMR Paleoclimate data simulation framework. So it's essentially a Bayesian architecture and it's offline common filter. So here the model simulations provide the prior state as well as the covariance structure. So it's spatial. And the process models translate this prior state from the climate space to the process space so that we can compare this prior to our real observations and calculate the difference, which is called the innovation term. And this term will later be utilized by the common filter and be propagated spatially to update our prior and get the posterior or our reconstruction. So for example here, suppose we'd like to reconstruct the temperature at the green point marked by this star, then the process records within a certain distance will be involved. It's essentially a combination of those process records and the weight of each record will be determined by the spatial covariance structure provided by the model, as well as the error estimate of each record. And now, looking at the very first beginning, so for the first several hundreds of years, we actually don't have observations. So the reconstruction will be essentially just our prior estimate, and that's the prior distribution provided by our model states And then after that, once we got observations, they will be fed into the steps later by the common filter, and we get, so that prior distribution will be updated by the policy records, and we get those wiggles we see here, and so on and so forth. We reconstructed the time series of the whole time span, and it should be noted that the temporal variability comes purely from the process. The models provide only the spatial structure. So now to verify if there are any contradictions between trees and corals, we use PDA to reconstruct to get two reconstructions, simulating corals only and trees only, respectively, using the process used in those two previous studies. And to test if there are some potential volcanic signal, here we superpose the time series segments around each event and compute the composite mean, which is so-called the superposed epoch analysis here. So the horizontal axis shows the years relative to the eruptions. The y-axis shows the linear thermal fall value, and each dot here denotes each event, and the solid line represents the composite mean. And the significance levels are computed by bootstrapping those non-volcanic years. So here we see a consistent but insignificant El Nino response to large eruptions in both reconstructions, which suggests that the difference in proxy type does not lead to the different conclusions. So what else could be the cause? So we notice another fundamental but often overlooked factor, which is the criterion for event selection. So in Lee 13, they used the volcanic explosive index, VEI, which measures the volume of the erupted tephra. So this is essentially a geological index. And in D20, they used the volcanic stratospheric sulfur injection, VSSI. It measures the mass of sulfur injected to the stratosphere, which directly affects the amount of shortwave radiation that enters the climate system. So a very recent eruption is a good example of this index. So based on this geological study, the Tonga eruption has a VEI around 5 to 6. So it means that it's a pretty large eruption. So we should expect a large climatic impact, right? No. According to this modeling study, they think this eruption doesn't inject enough sulfur into the stratosphere. So it's still not strong enough to have significant impacts on the climate. Therefore, we believe that VEI, this index, bears a less direct relation to climate forcing. So now the question is it the different criteria that leads to the different conclusions? Before moving forward, we also notice the pros and cons of each proxy type. So the corals are close to the target region, the tropical Pacific. However, they are discontinuous, leaving the gaps in our reconstruction. The trees, on the other hand, although being continuous, they are far away from tropical Pacific. Therefore, this reconstruction is essentially based on the teleconnection, which could be non-stationary. So PDA offers the opportunity to fuse these different processes to overcome the cons of each process type and yield the optimal reconstruction. So here we perform the reconstruction with PDA again to get our best estimate and reduce the superposed epoch analysis based on different event selection criteria. So here, if we select the events based on VI, then we see consistent, significant El Nino response to large eruptions in both reconstructions. However, if we exclude the post-1850 events, we see that the significance is remarkably decreased. So which suggests that the analysis is actually dominated by the modern events. So there are actually evidence showing that for at least these 3 modern events, the volcanic eruptions is actually behind the initiation of El Nino events. So that cannot be the cause, cannot be the trigger. So there could be some potential coincidence there. And now if we select events based on VSSI, then we see consistent but insignificant El Nino response to large eruptions in both reconstructions. So to summarize a bit, in both reconstructions, we see significant response with a less defensible event selection, but we see insignificant response with a more defensible event selection. Now, what about climate model simulations? Here we look at those PMF3 simulations as well as CESM last millennium ensemble. We see that only CCSM4 shows a pretty strong response at the year of eruptions, and it's not really the case for most of the other models. However, we know that volcanic eruptions will generally cause a cooling on surface temperature, so which can weaken this absolute SST signal here. So that's why a relative SST is proposed to highlight the impact of volcanism on ENSO relative to the tropical mean cooling. So if we perform this analysis based on RSST, we see that the signal is boosted in most of the simulations. Although it's not entirely consistent across all the simulations, we see some simulations still show some insignificant response. Okay, now in this study, we see that paleoclimate data simulation enables 2 functionalities. One is the comparison between different processes, and another is that we can optimally fuse different processes within a consistent dynamical framework. And then the good news is that we did not see real contradictions between trees and corals, but the bad news is that we still lack convincing observational evidence of the ENSO response to volcanism. We also know that our study does not suggest to exclude the possibility that there could be some potential linkage, because absence of evidence is not the evidence of absence. Recent modeling studies suggested that multiple factors can actually affect the ENSO response to volcanism, including the location, intensity, and season of the eruptions, as well as the preconditioning of the ENSO state. And given this large number of degree of freedom, I think the last millennium is just not enough to provide enough sample size. We have only 20-ish large events during last millennium, so we need a really longer process records to provide more samples. And to enable the RSST-based analysis, we also need more process sites so that we can conduct reliable climate field reconstruction. And with that, I'll be happy to take any questions. Thank you.
For the great talk, do we have questions? Go ahead, Alex.
So I noticed that the comparison between the corals and the tree rings, there were like 10 coral sites and like hundreds of tree ring sites. Is like how many, like a sampling difference at all, do you think that has any effect on the reason that they disagree?
Oh, so here the corals are basically comes from the Ocean 2K and also the Palmyra site, which is essential here. So we keep only those long records so that the scales here we see over the instrumental period can faithfully represent the scale going back to time. So we also exclude many modern records here, so that won't be confusing. And for trees, although this figure here shows that we have the NADA, MADA data set, we have lots of sites, but in the end, we are actually using the 6 best predictors from this Lee-13 study. So only 6 records are really used, and they are considered to be the proxy, direct proxy of the Nino 3.4, according to this Lee-13 study. Thanks for the good question.
Have more questions? Let's move on to our last talk for this first session. It's from Alex Thompson. Is there a way to remove the banner?
No, I think this is fine. Thank you for having me. My name's Alex Thompson. I'm a postdoc at WashU in St. Louis. Today I'm going to talk about using paleoclimate modeling to understand and contextualize modern extreme precipitation. So in St. Louis, we certainly remember, but you may also remember last summer we had a very extreme precipitation event in July that started on July 26th in St. Louis with scenes like this around the city. You can see that this floodwater is nearly breaching these cars. People needed to be rescued from their apartments. This occurred throughout the city from record-breaking extreme precipitation. But then the same storm moved on 2 days later to eastern Kentucky, where we saw equally devastating events. Here is a picture from the aptly named Hazard, Kentucky, where you can see this river is greatly overflowing its banks. So these 2 events in St. Louis and eastern Kentucky, but also a couple around that same time, led to a lot of press on this 1 in 1,000 year event. So there was a lot of discussion in the media about whether these events had a frequency of 1 in 1,000 years, or you could think of that as 0.1% in any given year. So what does that actually look like in the observational record? So this comes from the airport in St. Louis. It's a observational station that has been active since the late 1800s. And here what I'm showing is called RX1 day, or the annual maximum daily rainfall, so the single day every year that has the highest rainfall amount. And so here you can see in 2022, it was about 2 inches higher than the previous record in 1915. So basically, like outside of anything we had seen before. So this very high record-breaking event. But it's kind of interesting to think about a 1 in 1,000 year event occurring with, and understanding that from only 100 years of data. So the way that we do this is we can take this RX1 day data set and fit an extreme value distribution curve to this, and basically find that place way out in the tail where we can find 0.1% of that area to the right. So that's basically how we would statistically find this type of 1 in 1,000 year event. But coming from the paleoclimate side, this assumes that the range and variability of this 100 years of data is the same going back 1,000 years. So I want to highlight, you can see up here this red dot for the 2022 event. If we had assumed this range going back 1,000 years before, we are falling outside of that range as we move into the future with more extreme precipitation, right? So there's a lot of uncertainty in these types of calculations of return periods that are really important for understanding how to adapt our infrastructure to future extreme events due to global warming. And so here's just kind of one example of that uncertainty. So what we're looking at here is an estimate from NOAA that it comes from that data from the airport in St. Louis. And here what we can see is that for 24-hour rainfall duration, this is what's called the average recurrence interval. So on the x-axis is the years of the return period, and on the y-axis is precipitation depth. So basically what we can see is that that day last year in St. Louis was about 8.64 inches of rainfall. And so that falls, largely within this 90% confidence interval. But what I want to point out uncertainty-wise is that confidence interval is about 7.36 inches or 18.7 centimeters. So that is a really, really large confidence interval that, it really doesn't give us a lot of information in drawing conclusions about these types of rainfall events. So I am trying to reduce the uncertainty with a new method and approach that uses a CESM last millennium ensemble, specifically these 4 members that go from 850 to 2100 CE, to take the observational data this rainfall that we have observed, but fill in anywhere from 850 to into the future with CESM LME. So a couple of research questions before we get into the method and results. So by taking this, what I'm calling a blended data set, so it's blending observations with the models, I want to first just calculate what is this updated 1,000-year rainfall amount for St. Louis and Eastern Kentucky. So then we can look at what was the return period with this updated data set for the rainfall from this storm in July. And so I think something that is also kind of cool and powerful about this type of blended data set is that we not only can kind of look at this specific event, but we can look at how this return period will change under different temporal scenarios, right? So the kind of standard thing that we would use to understand the context when this event occurs is what I'm going to call pre-2022. So it's shown by this black line where pretty much all of the available estimates of data prior to this event. But we can also break this out into a pre-industrial, which I'm going to call pre-1850, or a post-industrial, which I'll call post-1850, and try to see how the frequency of this type of rainfall and extreme event might change in a time largely free from human industrial influence and in a time where human industry forces global climate. So I'm not going to have time to get into all the details of the method, but I do want to show just kind of spatially how I'm constructing this blended data set. So I'm using the NOAA Applied Climate Information System, which is a host of stations that have a period of record for some of them going back to the late 1800s. So what I'm doing here, and we'll focus on St. Louis first, is all of these different dots are stations that recorded rainfall during this event that was their maximum rainfall in 2022. Right, so these are basically the stations recording the extreme rainfall of this event. You can see this kind of pattern of the storm and the really, really blue dots in St. Louis where we got hit by the really extreme rain. And then the same over for Eastern Kentucky, where you can see some of these blue dots where they had the really, really intense rain that caused some of this flooding. So I'm taking the period of record for each of these stations and then filling that in for the past and into the future with the center grid cell for St. Louis and for Eastern Kentucky. So that creates some very large, kind of overwhelming figure like this that basically takes our observations right here and bias correcting CESM, filling in with a bunch of these different ensemble members and different methods to construct this. So I can take this data set and look at these different temporal periods to understand the historical context of this storm. So first, to look at that first question, what is this updated 1,000-year rainfall amount? This curve is kind of similar to that NOAA curve that I showed before, where we're looking at the return period now on the y-axis here, and then the amount of rainfall in that large region on the x-axis here. And so what we can see is that for St. Louis, we calculate some number at 5.06 inches, which doesn't really mean anything for our purposes here. But what I want to point out is that the 90% confidence interval here is about 0.2 inches. And over in Eastern Kentucky, very similar that 90% confidence interval is about just shy of 0.3 inches. And that is really important because this is a much smaller 90% confidence interval by about 97% smaller than these single station calculations that is basically the current estimate. So anywhere that you see NOAA talking about these types of return period curves, that's kind of the uncertainty that we're working with currently. So with this method, we get about 97% uncertainty in St. Louis, about 80% less uncertainty in Eastern Kentucky. So then moving on to the July 2022 storm return period, we can look first at St. Louis, and we can see this same kind of curve. We're going to look at it from a different angle here, now going from the x-axis up to find the amount of rainfall that occurred in this storm and what that return period is. So what I'm showing here is actually by updating this blended data set, we still find about a 1 in 1,000 year event for the St. Louis rainfall, about a couple hundred years of uncertainty on either side. But this is still largely a really, really high-end, infrequent rainfall event. That is not necessarily the case for the Eastern Kentucky rainfall. So here, instead of a 1,000-year event, as was widely reported in the news, we find that this event was actually somewhere more like a 1 in 250-year event with about 100 years on either side of that confidence interval. So this, this is giving us a greatly a different perspective on this type of extreme precipitation event. Using this pre-2022 distribution of time. We can also see how that July 2022 storm return period changes between these different temporal regions. So here we're focusing just on these blue and red dots for this return period. So if we just look at the pre-industrial, a storm with this amount of rainfall in St. Louis would be about a 1,500-year event. But moving into the post-industrial period, this is like a 280-year event. So still a high-end precipitation event. We're not likely to see this again in the next couple of decades. But in that post-industrial period, it's about 5 times more likely than in that pre-industrial period. We can also look at Eastern Kentucky for this, where the numbers are not quite as high, but a 235-year event in the pre-industrial period now is something like a 92-year event in the post-industrial period. So this is about 2.5 times more likely to happen in this post-industrial period. So just to conclude on this, we're working on this new approach to understanding modern extreme rainfall, and I think it's really exciting that we can use these types of paleoclimate modeling in the last millennium. Ensemble, I know for some of you maybe isn't so paleoclimate, but to understand how we can update this type of context. And just as a case study, we've been able to apply this to the rainfall that occurred last year in St. Louis, largely confirming some of these updates or some of these data sets on 1,000-year event, but greatly updating our perspective for Eastern Kentucky. And then we're able to take these types of temporal scales and put numbers like a 2.5 to 5 times more likely that this type of event would occur in the post-industrial period. So with that, thank you for listening. I will leave you with a picture of my daughter getting her first earth science lesson in the aftermath of this storm.
Thank you, Alex. Do we have a question? Please go ahead.
Said that those ensembles went to the year 2100. I was wondering, well, what scenario was that? And if you separated out sort of 1850 to present versus present to 2100 to see how those return intervals would change in the future.
Question. So those are RCP 8.5 that go out. I have not separated it out yet, but those types of numbers that are like 2.5 to 5%, I would guess doing that exercise, those would grow because, as we're seeing getting towards the back half of the century is really where a lot of those high extreme events are occurring in some of these ensemble members. So it might be a worthwhile exercise to see I don't want to make the boundaries too small because we're really looking at like the rainfall distribution. This isn't necessarily, this isn't necessarily a year by year type of prediction kind of thing, but that's why we're looking at like a pre-industrial period and a post-industrial period. So it might be interesting to kind of try like at least the last 100 years or something to see what that return period is and whether it's even less than that 280. Yeah, right, exactly. So yeah, thanks.
I think we have time for more questions.
Alex, great talk. I was wondering, do you notice any difference in the return period during like medieval anomaly or the Ice Age?
Looked at that, but maybe we can talk after this and try to look at that because that'd be really interesting to see. I think one thing that's cool about this method that I want to talk to as many people as I can about is just the power that it gives us to understand some of these different time slices and trying to understand like since it is the last millennium ensemble, it has a lot of that stuff in it, like volcanic eruptions and that, to see, if that has some kind of impact on something like this that has a lot of more internal variability and, trying to understand that extreme precipitation in the tail is kind of hard to get at sometimes, but, there's a lot of cool things that we can bring to it from there, so thanks.
Thank you.
Since we still have time, maybe I can ask Alex one question. So looks to me that you are combining the model data with the observations. I'm wondering, maybe I missed the detail. What kind of validation have you done regarding this product? Thank you.
Good question. So I'm bias correcting the model for the observed period of record. So I'm doing that for several different iterations of data quality. Basically, part of the way that I get this confidence interval is by cycling through different limits on where that data, how much allowable missing data there is to try to get this period of record of that data. And then for each of those, I'm bias correcting the model. So it kind of gives us this range of uncertainty in terms of like that mean and standard deviation of the model to that.
Let's thank Alex again, and we will move forward to our discussion session because we still have like 7 minutes left. And I think it's great we have time, and if you have questions for any of the previous speakers, you can ask questions. And if you have questions, you can also type those in the chat box. Since we know people, okay, no one is asking. Okay, go ahead.
I'm not sure who to direct this at. I guess Alex and a couple of the speakers mentioned quantities within the CESM or simulations that were things that depend on resolution, right? So like we saw this in the ice sheet case or like in the lake case where there's some, where we're thinking about precipitation and water balances within lakes that are, in regions where there's fine topography that's maybe not well represented by the model. And that's true in places like the Midwest as well. So I was wondering if any of the speakers would mind reflecting on how fine scale processes that maybe aren't in the CESM might be expected to affect their results.
Mine might be a little different than the others because I actually have a plethora of data to use. But the resolution of CESM played into a large role in the design of my study because you know, as a 2-degree resolution, I got very lucky with the spatial structure of that storm. If you recall, the extreme rainfall in that storm largely fit within that grid cell. It wasn't quite as good in eastern Kentucky, where it kind of was like in the northern quadrant. And you know, for our intents and purposes, this started as a project just to kind of see what we could get. So at this point, this was as good as we could do resolution-wise. I think it would be really interesting to try to run this type of analysis with greater resolution, which then the trade-off is then we don't have as great of a paleoclimate record, right? And so I think just, you know, from my perspective, it plays into how we design the question and how we ask that question of what are we trying to get out of this type of study.
Thanks, Alex. I think Mimi also mentioned in his talk regarding this resolution. Do you have any comments? Sorry for putting you on the spot.
Well, the entire iTrace is also at 2-degree resolution, so the Great Basin is only a couple of grid cells wide. So, yeah, it could be an issue, and it does mean that the model is probably not suitable for studying relative timing of different lakes between different sectors of the Great Basin, because it's just all within one pixel basically. But I think it should still be okay for understanding large scale patterns, but certainly could benefit from higher resolution.
Thanks. We have 3 more minutes. Does anyone have any comments to add? Maybe we can stop early and enjoy the break and come back later at 3:30 p.m. Mountain Time. So thank you, everyone.
Right. Hope everyone had a good coffee break. Guess we might as well go ahead and get started because we're a couple minutes behind schedule. So we're just going to keep going with our second session of the afternoon. So same deal, 12 minutes for talks, 3 minutes for questions, and then get a 1-minute warning with the friendly orange sign. So if we could go ahead and get our first speaker up, that's going to be Greta Schum, talking about snowball Earth and refugia. How to play the thing. Cursor is not on. Thanks.
Thank you all for being here. My name is Greta Schum, and I'm going to be talking about an unconventional use case for CESM, thinking about snow on the Earth, glaciating the entire. We're going to be thinking about it in terms of sort of a theoretical climate of any Earth-like planet. This is work that's being done at the University of Washington with my collaborators there, as well as the University of Utah and Oregon State University. So let's get started. So the motivation for this work is that we know that 2 snowball Earth events took place on the Earth in our history, and this would be about 700 million years ago. And we know that photosynthetic eukaryotic life survived these events, so it's an intriguing mystery as to how that life survived that would have had to depend on sunlight and liquid water. Also intriguing from an astrobiology point of view. So if we think about the Earth system and how it can be stable in many different climate states, the snowball Earth state is actually an energetically stable form of the Earth system and an Earth-like planet elsewhere in the universe. So if we're going to go out looking for Earth-like life elsewhere in the universe, it behooves us to think about how it could exist on a snowball climate. So this is what it would look like, theoretically. So the snowball climate is characterized by the global oceans freezing all the way to the equator. This is a photo taken by Steve Warren, the PI of the project, on a blue ice area in Antarctica. You can kind of think of this as what the oceans would look like, so they'd be completely frozen. There's 2 graduate students standing on the ice, proving that life can exist in extreme circumstances. And this ice would actually not be sea ice as we think of sea ice in the Arctic, but it would actually be glacier ice flowing on thickness gradients, so generally flowing from the poles to the equator. And this dynamic is called sea glaciers. So how might you maintain life on the surface of a snowball climate like this? One option is that you might have hotspots, so things like modern Hawaii and Iceland that maintain liquid water or maintain warm temperatures through volcanism. The problem with hotspots as a way to keep life alive is that these would be small, isolated places, and they would move around, so you'd have to have migration of algae, or the little microbes that we're talking about, over long distances, and that's not super sustainable. Another option is that you might have sunlight penetrating thin ice. A model or a simulation of this was done by Chris McKay in 2000, where they used broadband solar radiation to see how, or they modeled solar radiation as a broadband spectrum and see how far light would penetrate through ice in a snowball climate. But if you use a spectral model for solar radiation and actually account for the variation in how different wavelengths of light penetrate ice, this actually doesn't work so well, and you end up with a really thick ice in a snowball climate that sunlight would not be able to penetrate through. Another option is to have a water belt. So this has been proposed and promoted by Dorian Abbott, and you might have, say, not a complete closure of the global oceans, but actually maintain some liquid water at the tropics. The problem with this is that if you actually account for the high albedo of modern analogs of sea glaciers, this is also really hard to maintain, and also for the purposes of that theoretical snowball climate that exists somewhere elsewhere in the universe. It's kind of more intriguing to think about this hard, difficult bottleneck for life. So another option is that you might have ice living, or microbes living in the ice surface. So you might think of this as algae living in sea ice. We have modern microbes that live in ice where surface temperatures only reach above freezing for a few days of the year, so this is a reasonable way for life to exist. The problem with this is that previous work modeling snowball Earth only reaches maximum at the warmest time of the year, the warmest part of the globe, in the afternoon, the warmest time of the warmest day, negative 30 degrees Celsius, so this is not warm enough for life to survive. Finally, one final possibility for how life could survive is in narrow bays. So this is something like the modern Red Sea, where you have land surrounding an enclosure where ice would be flowing in, but get ablated before it could reach the end of that bay, keeping the ice at bay. So this is what it would look like. You can see that there's desert land surrounding something like what you can see here in white and blue as a modern analogous Red Sea. And if the surrounding land were net sublimating, you would also be protected from land glacier invasion. So this kind of configuration of the land and ocean protects you from both sea and land glaciers and allows you to have open water, especially if the desert land were low albedo. And this works because as surface temperatures reach high values, the ablation of the sea glacier actually works better. And this has been shown in Campbell et al. 2011. So this is our sort of motivating theory for how life could survive, and we want to ask, could narrow bay-enabled refugia exist on the surface in a snowball climate? And to do that, we're going to use CESM to simulate this hardest bottleneck for life in a snowball climate. We're going to make it as hard as possible for life. We're going to use a fully frozen ocean, low CO2, high albedo sea ice, etc. And I say sea ice because we're going to be using the sea ice model, but as I said before, this is not really sea ice as you might think of as freezing of seawater, which has an albedo of about 0.5 in the broadband. It's actually this blue glacier ice. And at the top, so at the surface where actually sunlight is going to be seeing this ice, it's going to be firn ice, which has an even higher albedo, something like 0.7 in the broadband. And you'll notice that this is actually higher in the visible and lower in the near IR. So this is our general configuration, which is a bit unconventional. We're going to be coupling CAM5 to CEIS5, and in CEIS we're using the CCSM shortwave formulation in order so that we could prescribe the albedo of the sea ice to be higher than it would be in the model otherwise. We're going to use only thermodynamic sea ice, so Bits and Lipscomb thermodynamics, and we're going to couple it to this simplified land model called SLIM, the Simple Land Interface Model, which was built by our collaborator, Marisa Legou. We're going to use this model to apply properties of the land surface that the atmosphere cares about without having to ascribe any certain land type to them. So we're going to use a uniform land surface albedo of 0.4, evaporative resistance, and uniform roughness just to make the land look the same everywhere. We've also, you'll notice, turned down the solar constant to make it cold, and we've also turned off lateral heat flow in the ocean to make sure that this freezes over. Since we don't really know what the continents looked like during the Neoproterozoic era, we're going to use this random configuration of continents that I just chose. And I just want to give a huge shout out to David Bailey for helping me get these simulations actually running because it was not a normal configuration. So after some trial and error, we actually get the global oceans to freeze over in just 20 years, which is fantastic. And we actually ran this simulation out for about 100 years to make sure this wasn't just a transient, freeze over and then it becomes unfrozen after a while. And that allowed us to establish the right conditions for a snowball climate in CESM. So now we're going to sort of explore this climate space to see what land surface albedos and what CO2 levels would allow for these so-called refugia to emerge. And just to give us some context to how we choose what land surface albedos we test. So land albedo is a very varying thing, unlike ice albedo, and it depends upon what land type you have on the ground. But one thing that does affect land surface albedo is the existence of plants with roots. So roots are very good at breaking up soil particles and making them have a smaller grain size, which increases the albedo of your soil. So it's conceivable that you might have pretty dark land without land plants, especially in deserts. So this is a picture of a stony desert, for example, which doesn't have those those roots breaking up the particles, and it's as low as 0.15 in the broadband. You'll notice that the albedo structure of land surfaces has a different pattern, interestingly, where it's lower in the visible and higher in the near infrared. So we're going to sample around from 0.2 to 0.4 in the broadband of land surface albedo. We're also going to sample across CO2 space, as I mentioned. So here I'm showing you the different combinations that we use. We didn't simulate every single combination, but we can see in the green boxes which ones we did run. We actually ran these simulations starting with the same configuration that I showed you, except for these modifications. We ran the simulations for 20 years, and we also made a few modifications, like setting the albedo of the land surface be visible at a lower threshold for snow, because this snow is not going to accumulate on plants or anything like that. It's just going to be on bare ground, so it's a different setup from what's normally in CLM. And so when we run all these simulations, we get these global mean temperatures, global mean surface temperatures of about -40 to -30 degrees Celsius in the annual mean. So it's a very cold climate. And also, if you're curious, we used the CAM's portable offline radiation tool, or PORT, which allowed us to diagnose exactly what the global radiative forcing is that's associated with moving through these climate spaces. So if you go from 10 ppm to 200 ppm, that's about an 8.4 watts per meter squared forcing. Whereas if you lower land surface albedo from 0.4 to 0.2, that's a global radiative forcing of about 5.1. Of course, this is going to be concentrated over land and bare land at that, but yeah, that's just a comparison between these two types of forcing that we used. So one initial result is that nowhere on the globe reaches a global mean surface temperature that's above freezing in the annual mean. So I'm showing you 10 ppm, 50 ppm, and 200 ppm at the highest albedo that we used. But if you lower land surface albedo to 0.2 in the visible, 0.25, and then, or sorry, 0.2 in the broadband, 0.25, and 0.3 in the broadband, you can see that there are places that reach above freezing in the annual mean, interestingly, around the Red Sea, at these isolated places. So at this point, we can kind of make an assumption that we're using a 2-degree simulation that's not going to actually represent the flow of sea glaciers and anything like that. So we're going to kind of characterize places that have land or surface temperatures that reach above freezing, either in the annual mean or any time of the year, really, as places where you might have a habitable grid cell. So if you had a narrow bay where ocean water could access that spot, you might be able to host liquid water there. So I'm going to characterize this as like the amount of land that reaches above freezing is that's the habitability of that simulation. So if we look at maximum temperature, and these are in monthly means, so this is the warmest month of the year, I'm showing you the places that reach above freezing at just some time in the year. That doesn't mean that they're in the annual mean above freezing, but they reach above freezing. This allows us to kind of bring back a previously thrown out way for life to exist, which is the living on sea ice theory. So in these places, if a narrow bay existed, you might have the production of sea ice in that narrow bay, but it would reach above freezing at some time in the year, so you could imagine life living in that spot and being able to survive just off those few days of the year that it gets above freezing. And this is possible because we actually end up with a lot of land that's actually bare, so unsnow covered. You might have been asking, well, don't you have ice sheets everywhere on a snowball Earth? We end up with actually a lot of land that's actually exposed to the atmosphere without snow cover. And this is because the snowball Earth atmosphere is really, really dry. We know from Clausius-Clapeyron, as you reduce temperature, you actually make it harder for the atmosphere to basically hold water. And this is showing you a plot of potential evaporation calculated from the Penman-Montieth equation over land and just as a function of latent heat flux over the ocean, since you have infinite water over the ocean. So this is telling you that if you had water to evaporate, this is the balance of water that would be evaporated versus the supply as precipitation. So anywhere that you see as brown, that place is net sublimating. So we can answer our first sort of question, which is, Could narrow bay enabled refugia exist on the surface of a snowball climate? And we found that open water refugia are possible at low land albedo and high CO2, and ice surface refugia in narrow bays could be possible at low CO2 and bright bare ground. So we're also just going to explore the comparison between these two types of forcing quickly. I'm showing you the general spatial pattern of where we get land above freezing at some point in the year. So this is T max above freezing, forced by CO2 versus forced by land albedo. And you can see that the land albedo is actually more effective, even though the global radiative forcing is less. As a zonal mean, this is kind of the same thing that I showed you, and you can see that the impact of forcing by land albedo is actually stronger, even though the global mean radiative forcing is lower. And if we look at this sort of as an apples to apples comparison, I'm showing you radiative forcing on the x-axis below with the corresponding CO2 level holding albedo constant versus holding CO2 constant. You can see that the effect of albedo changes are stronger. We also parse this out into the direct effect and the indirect, and they're about at parity. And I just want to leave you with the thought that I'm not necessarily competing these two forcings against each other, but showing you that between both of these different mechanisms, snowball Earth is actually a pretty habitable place, and you get a lot of land that reaches above freezing. So with that, I'll just leave my conclusions up, and thank you for listening. Happy to answer any questions.
Okay, I see the last point there is continental configuration would influence habitability. So I'm curious if you've considered running alternative configurations of the continents, like a supercontinent, or just thoughts on that, or other boundary conditions that you think could be an interesting sensitivity study.
That's like one of the main conclusions of the study, is that continental configuration would definitely change the answer. And if you had a clustering of continents, for example, versus like a spread out continent with lots of rifting, that would change the answer. The problem is that the continental configuration of Neoproterozoic era is very unconstrained. And the only thing that's really constrained is like the distribution of zonal land that's at any latitude. So we didn't think it was necessarily adding a lot to the conversation to go run this in a Neoproterozoic configuration, although the Meredith et al. Newest reconstruction, which has a continuous, really nice, very like self-consistent reconstruction, is really exciting. And so I have made a landmass of the like 720 reconstruction, and I would like to run that. It's a little bit difficult, especially in the weird configuration that I made, but I have made a supercontinent as well. And so just running those as a little bit of like a context will be really useful, I think, when we publish it. So, thanks.
Great, excellent. So next up we have Zhang Zhu, talking about a hot climate this time.
Yeah, I can take it over. Thank you. First, I want to thank Greta for the great talk. And Snowball Earth is cool, and hot house climate is also interesting. So, as you can see, this is about simulating the Eocene hot house climate using CESM2. And I think as paleoclimatologists, we believe that information on the past climate change is very valuable for us. And one way is to assess the climate sensitivity in climate models. This can be simply done by performing paleoclimate simulations. For example, the early Eocene, so that's a greenhouse climate, the global mean temperature is thought to be 14 degrees C above the pre-industrial climate, and the CO2 is around 1500 ppmv. And the cold extreme is the last glacial maximum, and the global mean temperature is around 6 degrees C colder than pre-industrial with a lower CO2. Next, I want to use CESM2 to quickly show you an example. And I know many of you may have seen these results multiple times, so I will go through this rather quickly. Here we are looking at the climate sensitivity in different versions of CSM, and CSM2 is over here, so it has much higher ECS than any previous model. And using paleoclimate constraint, we can assess the high ECS. So here we are looking at the early Eocene, so hot house climate. We put Eocene boundary condition and different levels of CO2 into the simulation. And in the case of CSM2, you see that model simulates a very, very warm climate, much warmer than the proxy records. And on the other end, we can use CSM2 to simulate the last glacial maximum. And you can see here, the amount of cooling, that's the x-axis here, is much greater than the proxy suggestion. So combining these together, we suggest that the high ECS is unrealistic. And we can move one step further, trying to identify the potential issue in the model. So we work closely with the answer model working group, the model developers, and we identify the potential issue in the model. The first one is this unphysical limiter on the cloud ice number. The second one is the problem in the microphysical time step size. So with the default time step, the cloud feedback does not converge. So after correcting those issues, we developed the paleoclimate calibrated CESM2. So that's the cyan line here. You see that we are simulating a more realistic last glacial maximum, and the climate sensitivity is also much lower. And importantly, this configuration also simulates the modern climate, including the 20th century warming. So the performance is overall as good as the other standard CESM2 ensemble members. We have 3 shown here. So far, so good. The next question, actually, you may wonder is, can the paleoclimate calibrated CESM2 simulate the early Eocene climate? Unfortunately, the answer is no. You can see here, we are looking at the global mean surface temperature with, we think, realistic early Eocene boundary condition. So here we use 6 times pre-industrial. That's about in the middle of the proxy suggestion. Let's start from the red line. That's the CESM2 Eocene simulation, again with 6 times CO2. You see that after initialization, the model quickly run away. And if you look at the top of atmosphere radiation, it increases with temperature, so the model is not converging. And how about the paleoclimate calibrated configuration? That's the cyan. You do see an improvement in terms of the overall stability compared to the standard CSM2. However, this improvement is not good enough. So after several hundreds of years, the model similarly developed this runaway behavior. So as you can see here. And this is a little bit disappointing, and it tells us that there's likely still problem in the model. That's what we want to address next. And one hypothesis is that perhaps there's problem in radiation. This is based on published papers listed here. So in this paper, they point out that the lookup table in the radiation code, which is RRTMG, used both in CSM1 and in CSM2, is very narrow. So that's the gray range here. So if in the model simulation, your temperature fall within the gray band, then you are good. You will have pre-computed gas absorption coefficient for long wave calculation. However, if your temperature fall outside the range, then you are in trouble. The gas absorption coefficient the radiation code gives you is not realistic. So here in this paper, Kluft et al., they actually use idealized temperature profiles. So with constant relative humidity, those are moist adiabat profiles, and they can focus on the long wave radiation only here and compute the ECS. And what they find is that compared with the more accurate line-by-line calculation, that's the darker line here, the parameterized radiation RRTMG overestimates the climate sensitivity for warm temperatures. And this warm temperature overlaps somewhat with our Eocene simulation. So this made us to hypothesize that maybe we have a radiation problem in the model simulation. Luckily, Pincus et al. Developed this new radiation code based on the old RTMG. So the new code is called RTE plus RTMGP. And it has a much wider lookup table, and it should solve the problem in the radiation code. And I repeated the Cleft et al. Calculation. So here, the line-by-line code, I used PyRes, that's the black line here. And the red here is the RTMG. You can see that I reproduced their results showing that there's a problem in the radiation here. And interestingly, when you use the newer radiation code, that's the RTMGP, the computed climate sensitivity agrees much better with the line by line. So basically confirming that the lookup table may be problematic for very, very warm climate simulation. And remember here, we only use idealized profiles, and also this benchmark is only done for long wave only, so we really need to run this new radiation code in a realistic early Eocene simulation. So that's the purple line here, and you compare the purple against the cyan. The only difference between them is the radiation code. And you see that the new radiation code, although it is thought to be more accurate, it does not solve the runaway problem. So the simulation runs away even earlier than the simulation with the old radiation. So it suggests that likely there's some compensating error in the radiation. For example, we need also carefully benchmark the shortwave or carefully look into the radiation processes associated, for example, with aerosol, with clouds, etc. This exercise is still very helpful. It's reassuring that radiation is, because it's a fundamental aspect of the climate modeling, and it's probably okay. So next we focus on the cloud-related schemes. So here we perturb the physical parameterizations between CAM6 and CAM5. Based on the fact that CESM2, CAM6, that's the red line, run away under Eocene condition, and CESM2, when you use CAM5 physics, you have the brown line here, so it's much more stable. And then we test individual cloud schemes. What we find is that when you switch the cloud scheme off, so you use the older version of moist turbulence and shallow convection scheme, so that's the UW scheme, and you see that we immediately stabilize the hothouse climate simulation, so you get the blue. And this simulation tells us that there's likely a problem in the turbulence and shallow convection scheme. Again, we work closely with the atmosphere model working group people, and we performed a bunch of testing. And what we found that if in the paleoclimate configuration, if we increase the club C8 parameter by 20%, we can quickly stabilize the simulation. So you compare the green against the cyan. The only difference is the tuning of this club C8 parameter with the minimum tuning of other inconsequential parameters to bring the pre-industrial climate back into balance. And you may wonder, what is this club C8? So that's a damping coefficient in front of the third moment of turbulence vertical velocity. And in the club framework, a stronger damping reduces skewness and promotes stratocumulus-like clouds. And we hypothesize that in CESM2, a GCM framework, a larger club C8 delays and weakens the disappearing of low clouds. So this is sort of related to the fundamental, very basic physical processes identified in large eddy simulation. So they suggest that the radiation and thermodynamic, again, fundamental processes can cause this nonlinear breakup of stratocumular stack. Of course, this is large eddy simulation, and we are looking at the global GCM, but we think we may capture some flavor of this fundamental physics, and we are still working on understanding the details. And here is a summary. Standard CESM2 run away under the realistic yields and condition. That's the red line. And the paleoclimate configuration improved the simulation, but not good enough. So that's the cyan. And we find that this runaway problem could be related to the cloud. Maybe cloud has a too strong drying effect on low clouds, and in particularly under warm conditions, leading to the model runaway. With this increased cloud damping, and we were able to stabilize the early yields and simulation. And importantly, you can see that we can also, the new configuration can also simulate the last glacial maximum, and it further decreases the ECS from the paleo-calibrated version. So this is 4, and the newer one is 3, right in the middle of the IPCC report. I think this is a good example to show that past climate information can help us to assess climate models and also to help develop the cloud parameterizations. I will stop here and thank you.
Any questions? The Zoom participants, please feel free to ask questions in the chat also. Yes.
Curious, in the runaway runs you did, what is the ocean look like? The circulation like? So the don't have any stabilized. Looks like runaway almost like a one-dimensional model, but the ocean, you have a full 3D ocean there, right? And did you look at the ocean circulation? Is that?
So in the baseline simulation, we don't have like a overturning anywhere. We only have wind-driven circulation. That's because we have very, very warm conditions, and we have fresh cap over polar regions, so which inhibited deep water formation. And to go back to maybe what you are asking, I think the ocean circulation will make an impact. For example, if you have strong ocean circulation, which may delay this runaway or reduce the magnitude. But this is a big radiation imbalance at the top of atmosphere. Could be 4 or 5 watts per meter square. It's a huge imbalance.
Basically, the circulation quickly overwhelmed by the radiated effects. It didn't take too much. All right, thank you.
Yeah, thanks for the question.
So how would this change the standard CCSM2 projection for future sensitivity to some of the scenarios?
That's a good question, and I want to thank you for the question. I want to stress here, we are looking at extreme climates with extreme forcing. So for example, the LGM forcing could be -6 watts per meter square. For LGM, for the Eocene, the forcing could be even larger. So to answer your question, for the future warming projection, the forcing is relatively smaller than what we are looking at here. But overall, in terms of global mean temperature, the difference could be 10, 15%, around that.
Okay, that's something. Thanks.
I'm just curious, is this new calibrated model can simulate the meridional temperature gradient between tropics and high latitudes?
Yeah, thanks. This is a great question. So as long as the global mean temperature is comparable, no matter which model you use, CESM4, CESM1, CESM2, they give you similar meridional temperature gradient. It is interesting.
So right now we have CESM1, 2, and also the calibrated. Which one would you recommend to apply this model to, for example, Miocene simulation?
I think for the paleo-calibrated CESM2, we may not be ready because I really want to understand the physics in the simulation to really make sure this is the correct way to do we really need to work with the model developers and to make sure this is the correct way, or we can ask the question, do we have a better way to do that? Thanks.
Hi, great talk. A very quick question. Have you tried only club mods without paleo-calibrated? Then you could test whether you need both the paleo-calibrated and the club mods to stabilize it, or maybe one is enough.
That's a good question, and I haven't done that, but I guess for eosin, the club modification may be more important, and for LGM, the microphysics-related treatment is more important. This really stresses the importance of using multiple climate states to help with the model assessment and the development. Thank you.
Great, yes, a good discussion. I think we do need to move on to the next speaker, though, who is Kara Hartig. I hope I pronounced these right. Who will continue with our theme of high CO2 climates.
So my name is Kara Hartig. I work with Elliot Zipperman at Harvard, and I'll be trying to give you sort of a physics process-based understanding of why wintertime continental temperatures never seem to drop below freezing in much warmer climates. I'll also add, already on the first slide, I have to make an adjustment. It's been a while since I thought about my simulations in terms of multiplications of CO2. So I was thinking my simulation is 4 times modern CO2 level, which in the conventional wisdom is actually an 8 times CO2 scenario. So we're looking at like very high CO2 levels around 2000 ppm. So just make that adjustment anytime you see that number. So here I have a visualization from the modern climate of the sea ice maximum versus sea ice minimum in the Arctic, just to give you a sense of like how important some of these like wintertime dynamics and especially sea ice can be to what's going on in this region as we move on. So for context, we're going to talk a little bit about the Eocene as an example of a paleoclimate case. So in these much warmer climates, the coldest wintertime temperatures tend to be very strongly suppressed. And the evidence for this comes largely from fossils. So on the left-hand side, we have an Eocene-era crocodilian fossil and a palm frond fossil. These two species not only need fairly high mean average temperatures, but they also are almost entirely frost intolerant. So they can't manage temperatures below freezing that last for more than a couple of hours at a time. And this gives us a really strong constraint on the cold tail of a temperature distribution. Now, if we then consider what we have as a modern temperature distribution in these regions in the interior of North America, and we just think about shifting this temperature so that the new mean matches what we know to be the cold month mean in periods like the Eocene, it would leave this really long tail into these cold temperatures that we know were strongly suppressed in the Eocene. So what we're trying to understand here is why this cold tail tends to like scrunch way up towards the mean in these much warmer climates. So to do this, we're going to be comparing the coldest continental air masses in wintertime in a pre-industrial scenario versus a warmer climate scenario. So I have here just showing the prescribed sea surface temperature and sea ice configuration that we're using for these two climate scenarios. In both cases, I'm starting with an F2000 CLIMO comp set, just so that we're doing like the minimal changes between these two cases. Then I'm getting an SST and sea ice from the pre-industrial era and a pre-industrial level of fixed greenhouse gases for one case. And in the other case, I'm taking an SST and sea ice from the year 2300 and an extended version of this like maximum emissions SSP5 8.5 scenario. So we're driving them with 2 different prescribed sea surface temperature and sea ice cases. And in this warmer case, we're also working at just over 2000 ppm of CO2. So again, this is roughly an 8 times CO2 scenario that we're looking at. So here we start with this temperature distribution just to understand whether or not we're actually seeing this narrowing of the temperature distribution. So I have here the wintertime temperature distribution over the interior of North America in the pre-industrial case in blue and the year 2300 case in green. And we see that indeed our temperature distribution is both warming and becoming narrower. So the DJF mean temperature has increased by about 20 degrees Celsius from the pre-industrial to the warmer climate case, and the coldest air is suppressed. So this 5 percentile marker is increasing by about 1.3 times of the increase in the mean. So we're seeing some suppression of the cold tail of this distribution. Now, to try and understand what the actual cause is of these temperature changes are, I like to think about temperature change as sort of two interrelated processes. So one of them is the external forcing. So this is diabatic temperature effects like radiation, moisture, clouds that might be acting like local to the continent itself and in source regions. The other effect is source regions. So air over North America is coming from other places, so we also need to be thinking about how the properties of the air in those source regions is changing, and even how the geographical distribution of the source region itself might be moving from one place to another. So we're going to be talking about both of these ideas, both separately and together, to try to understand what's driving the temperature change in the cold tail of these temperature distributions. So the first component that we're going to talk about is changes in the source region. And this is really about the availability of extremely cold air in these two scenarios. So I don't necessarily say that this is an unexpected result, but we do see a huge reduction in the availability of below freezing air in the source region for North America, which is the Arctic and high latitudes. So in the pre-industrial case, often in many of these regions for almost the entire winter, we have below freezing surface air temperatures that are occurring very frequently, whereas in our warmer climate case, we've dramatically reduced the availability of this below freezing air, particularly over the Arctic Ocean itself, which is now no longer covered by sea ice. So we have this hole in the availability of below freezing air over the Arctic Ocean and a dramatic reduction in like land-based below freezing air availability. And I've included this magenta contour just to give you a sense of where the sort of lower end of this below freezing temperature availability is. And this is driven largely by changes both in the greenhouse gas concentration and Arctic amplification, as well as the direct positive surface sensible heat fluxes that we're now getting off of the Arctic Ocean since the ocean surface is exposed. So this is meaning that in our source region, we are like having a lot less frequency of availability of this below freezing air. And I'll also note that this is actually sort of a conservative estimate. So if your air parcel is coming from the surface and staying along the surface into the mid-latitudes, this would be pulling those air masses. But the dry static energy is actually increasing with height in this region. So if you're sourcing your air mass from any higher in the atmosphere, then you get additional warming as it descends towards the surface. So this is really like the coldest you could possibly get would be pulling from these regions here. And in fact, if your air is sourced from higher up, then it tends to be warmer than this shows. So now we want to think also about these diabatic processes and diabatic temperature changes. So once we take these air masses out of these cold regions and we're moving them into the mid-latitudes, do we have further temperature effects that are acting on those air masses to then result in the cold tail of the temperature distribution? So to get to this, we work with backwards trajectories. So we sample events from this cold tail of the temperature distribution in both cases over the interior of the continent. Then we do 10-day backwards trajectories offline with the high split software. And then we can look at the actual temperature tendency due to distinct physics processes along each of these trajectories to try to understand which of these physics processes are driving most of the diabatic temperature change. So here I show the trajectories on the left-hand side from our cold air outbreak case and on our right-hand side from our warmer climate case. And there are some changes in the climatology. So we see that in our pre-industrial case, almost all of these trajectories are coming directly off of the Arctic Ocean itself, whereas in our warmer climate, we're seeing some more of these cold air masses coming off of the Pacific Ocean, and part of that has to do with the fact that our Arctic Ocean is now a much warmer source than it used to be. So to get cold air, we can start pulling from a larger geographical region. But one of the things that I found kind of remarkable about this was that there are some changes, but like we're still getting a pretty significant percentage of these trajectories off of the Arctic and the Arctic Ocean itself. So there haven't been like a complete reorganization of where these source regions are. Now, the next thing that we can look at is what's happening to the vertical distribution of temperature in these two cases, because one of the really important climatological changes between the pre-industrial and a warmer climate is the loss of the near-surface temperature inversion. So here we're looking at the vertical temperature profile on the y-axis as a function of the distance along the trajectory that we're traveling, and I've composited over all of the trajectories in both cases. So on the left-hand side, we see that temperature actually increases for like a few hundred hectopascals as you go up in the atmosphere and then begins to decrease again, which means that your coldest air is really being trapped close to the surface here. In the warmer climate scenario, we now have a
monotonic decrease of temperature with height, which is allowing our cold air outbreaks to be sourcing air from higher up. So we see that in these white lines on the left-hand side. This is showing the average and the plus and minus 1 standard deviation distribution of our trajectories. So you can see where in this temperature inversion they tend to be traveling. And in the warmer climate, our trajectories are now able to source from significantly higher in the atmosphere than they used to because of this loss of the temperature inversion. Now to look at some of these diabatic temperature effects, one of the big advantages of working with a model instead of reanalysis to study this kind of thing is that CAM actually outputs the temperature tendency from individual physics processes. So I can look at the temperature effect from just long wave, from just short wave, from gravity wave drag, and from these moist convective and latent heating type processes. So what we found in this particular case was that the direct shortwave heating is negligible, as is the gravity wave drag. So the two terms that are really driving diabatic heating of these air parcels are the moisture term and the long wave radiation term. So I have the distribution of the total contribution across all trajectories shown in the top two panels on the right-hand side. The top left-hand panel is the effect of long wave radiation, and the top right-hand panel is this moist processes, which is a combination of all of our convection processes and our latent heating. And what we see in this case is that the long wave cooling is competing with heating from moist processes and convection to give us the total temperature tendency along these trajectories. And going from our pre-industrial to our warmer climate, the long wave tendency actually gets slightly cooler, so we have more cooling from long wave in that case, whereas the moist processes are giving us about the same average effect in each trajectory, but the distribution has now shrunk. So to try and understand why we see more intense long wave cooling in our warmer climate, we identified what we think is probably a cloud top radiative cooling effect. So in our pre-industrial climate, on the left-hand side, again, these are vertical profiles, but in this case, vertical profiles of the long wave temperature tendency, and then the white contours over top of it are showing the cloud liquid water content. So in the pre-industrial case, there's very little cloud cover in these regions, and we see that there's not a whole lot of vertical change in the long wave radiative cooling effect, whereas in the warmer climate, we have a much higher occurrence of liquid clouds, and there's actually a peak in the long wave radiative cooling that occurs around the top of those clouds. So our trajectories are starting up in the region where we tend to have a fairly high long wave radiative cooling, and then they move downwards as they go into the mid-latitudes. So we're seeing that some of this presence of these liquid clouds and the cloud top radiative cooling is helping to cool these air parcels as they travel. And that's one of the effects that's helping to offset the warming that we get from moist processes and convection. So to summarize, we find that indeed we do see, at least in CESM2, that the cold tail of our temperature distribution is being suppressed as we move into these warmer and more equable climates, that the exposure of the Arctic Ocean surface has dramatically reduced the availability of below freezing air in the high latitude source regions like the Arctic, partly due to an increase in surface sensible heat fluxes off of the exposed Arctic Ocean, and that while diabatic sources are largely the same between these two climate scenarios, the increase in liquid clouds over these high latitude and mid latitude regions has intensified the long wave cooling in the boundary layer, which has actually led to slightly more diabatic cooling in our warmer climate than we saw in our pre-industrial climate. So that's what I've got so far. I'm happy to take any questions.
Questions? Yes, please use the mic.
I'm just curious, how the slope of asymptotes changes from when you increase CO2 or drop it in CO2?
How does the what change?
The asymptotes. You mentioned that in the warmer climate actually may source the cold air at a higher altitude.
So
I'm just related question, what are the asymptotes? Because they tend to move along the asymptotes, constant potential temperature surfaces, right?
So
steeper or the...
So the sort of climatological temperature and dry static energy distributions are that in the pre-industrial climate, because of this near surface temperature inversion, there's a really, really steep increase in dry static energy with height as you go up towards this temperature inversion. And then it continues to increase, but less dramatically once you get above the temperature inversion. Whereas in the warmer climate, we see a more sort of constant increase in dry static energy with height, but it's still increasing. In terms of moving
from the high latitudes to the mid latitudes, the isotropes tend to be fairly flat at the high latitudes and then start to dip towards the surface. And we do see that, roughly speaking, the trajectories are kind of following these isotropes as they move down. So they tend to be traveling sort of on like a level with the isotrope at the high latitudes, and then they descend as you move into the
But
mid
in
latitudes.
terms of vertical lapse rate temperature in the mid latitudes in the full-time CO2 runs, do you see significant change relative? Just look at vertically how fast the temperature drops in the warmer climate.
Yeah,
relative to the pre-industrial run.
So in the pre-industrial climate, the temperature is increasing with height, and then it starts to decrease again. And in the warmer climate, the temperature is consistently decreasing with height. So we're closer to a dry adiabat in the warmer climate.
Versus inversion versus no inversion.
Yeah.
Okay,
yeah.
thank you.
So we have about 7 minutes in the schedule before the next talk because Ron Fung is not able to join us today. So I guess what I can do is go ahead and put up the discussion questions that we had prepared for the end of the session. I've lost my mouse again. Okay. And we can just see if people have initial thoughts on that. And if we don't get to the whole discussion, then we can revisit afterwards. You said that was where exactly? Oh, go ahead. All right, great. So these are the questions that we prepared to just kind of prime the discussion, but if you wanted to discuss other topics, please feel free as well. But what we were curious about is whether you all considered yourselves more paleoclimate dogs, favoring more standard or coarse resolution approaches, or a paleoclimate cat, who might be more in favor of doing more ultra-high resolution approaches. And then along those lines, in general, there's been a trend, as we've seen over the course of this workshop, towards increasing model resolution generally. So as a paleoclimate community, how do we go about leveraging that trend? And for paleoclimate applications, do we still need to retain the capability to have a coarser resolution model with greater throughput? So, any thoughts on that initially?
So based on the project that I presented earlier, I think there is a lot of promise in some of the higher resolution at resolving certain types of questions, like if we're gonna try to look at the paleo weather or stuff like that. But I'll give a plug more for the coarser resolution too, in that a lot of the other work that I do is looking at kind of more broad regional types of large-scale climate patterns. And in that, I think the types of simulations that are afforded by the coarser resolution in terms of like transient simulations or larger time frames that we can simulate are still very helpful paleoclimate-wise, because when we're looking at those large-scale simulations, we don't necessarily need that extra computation cost that gets us that really fine resolution. So sorry, that's not really for one or the other, but just kind of to say the benefits of both.
Great, you got the vote for both dogs and cats. Anyone want to weigh in on that? Oh, yeah.
I will also be a cat dog and say that I don't think there should be a team on one side or the other. I think the sweet spot is probably everyone finding a way to leverage coarse resolution simulations for everything they can, really, and using strategically high resolution simulations for what they need. And the sweet spot is really finding the proper way to leverage both of those things for your question. And probably we should always be kind of demonstrating how coarse resolution is not adequate for our question before going to a high resolution approach.
That's a good point.
I think especially in a paleoclimate context, we maybe particularly benefit from having coarser resolution models because we often don't have great constraints on a lot of the input parameters. So to me, there's a huge advantage to being able to run many, many ensembles that explore a larger parameter space for some of these like boundary conditions and forcing that we don't have well constrained, and having like a single super high resolution realization of a climate that is based on a lot of maybe like guesses and best estimates of what some of those constraints are might not be a very accurate representation of our best understanding of the like range of variability in these climates.
Sampling a broad range of uncertainties as a paleoclimate community, that's for sure.
I want to apologize because maybe you've already covered this question, but I guess the question that I know I've seen a Zoom meeting where this was kind of discussed, but when you want to have a model that runs for 1,000 years or something big like that, and then you have a coarse resolution ocean, how do you kind of decide that the coarse resolution ocean is transporting the heat correctly? Because I'm aware that there are some simulations that sort of suggest that when you resolve the ocean mesoscale instead of parameterizing it, the ocean heat transport can actually go in the wrong direction. And when you're looking at how that ocean heat transport will determine, where the ice is and how the land ice is sort of sloughing off into the ocean and so on. Is there some kind of clever way that you could do short-term simulations at higher resolutions to convince yourself that the coarser resolutions are actually sort of not doing the wrong thing, and then you kind of get the wrong impression from your 1,000-year simulation?
I guess I'd say I don't think we have covered that yet, and it's an excellent set of points. Does anyone weigh in?
Also advocate the do some high resolution runs because well, I'm a dynamist, so there's probably a greater interest in the rule of dynamics in the climate sensitivity. Particularly when I saw the runs with CESM, the run quickly blows up, and I just wonder with a different resolution, the results could be maybe different. Maybe a range of runs, a low resolution, middle range resolution, and some high resolution runs, just to make sure that we didn't underestimate the rule of dynamics too much. All right.
Yeah, just like I just want one really quick point is that like oftentimes like the low resolution and the high resolution runs don't perform equivalently, so it's like the question of like how to test the performance of a low resolution run giving a high resolution run might not be as clean a comparison as you would hope. But yeah, okay, so it sounds like people have lots of great thoughts on this, and I know this is kind of awkward, and we were hoping to have the discussion as one condensed block, but given that it's 4:30 and we did have a couple more talks scheduled, maybe we can come back to these points at 5 o'clock. So I guess if you have more points, please bring them up, but unfortunately we have to just take a quick break to hear more great science. Okay, oh my God, I am so bad at this cursor, I'm sorry. There we go. Okay, so next up, who's next up? We have Xiaoqing Liu talking about the Miocene Canadian archipelago. And you. Great. All right. Great.
Hello. Hi, everyone. My name is Xiaoqing. I'm a postdoc working at Purdue University, working with Matt Huber. Today, I'm going to present a model study to explore the influence of opening the Miocene Canadian archipelago gateways on the intertropical convergence zone. This work is supported by NSF, and we thank Nico Harold for conducting these simulations. So the intertropical convergence zone, the ITCZ is identified as the tropical belt of deep convective clouds as the maximum in the 10 mean precipitation. Here I'm showing you the tropical precipitation from the observation. The color scale shows the precipitation, and this vector showing the surface winds. This red line is the precipitation maximums, the ATCC location. So we can also see that the surface winds are converging in the ATCC. And so the shifts in the ATCC location affects the rainfalls in many equatorial regions. So we care about the variations in ATCC location in future warm climates, and the past warm climates can provide us some insights. So the time interval I'm looking at is the Miocene is between 23 and 5.3 million years ago. And here showing is CO2 concentrations from some proxies. And the CO2 levels is between 300 and 600 ppm. And here this red shading areas is the middle Miocene climate optimums. Is global mean surface temperature normally relative to pre-industrial is around 7.6 degrees C. So it's a warm time interval. So we want to explore how the ocean's role in setting the mean location of ATCC, especially how they opening or closed the Canadian archipelago gateways and the influence on ATCC. So you may wonder when was the Canadian archipelago gateways was opened. Actually, there's a few studies. And here is the only paper I found related to the Canadian archipelago regions. It's from the geological record. But even for this paper, we don't have any evidence to show when sea was opened, how the sea gateway changed during the Miocene. So our understanding is quite limited. So for the Miocene simulation, the MIOMAP, we can see here, for the Canadian archipelago gateway, most models use the closed CA. Only one model uses open CA, so no one studied this gateway change influence. So our question is, what is the influence of opening the Miocene Canadian archipelago on the ATCC? So we use CCSM4 and conduct 2 experiments, closed and open CA. The target time interval is between 20 and 14 million years ago. It's from early to mid Miocene. Here shows the resolution, and we use CAM4. The paleogeography forcing is from Harold Hilbert Mueller 2011, and the CO2 levels is 400 ppm. And we ran the simulation for more than 2,000 years. We use the last 50 years for the analysis. So the only difference between these 2 experiments is just whether CA open or closed. It's only 1 degree Celsius difference. So when CA is closed, it just isolates the Baffin Bay and the Labrador Sea from the Arctic Ocean. So let's look at the results, how the ATCC location changed. Here I'm showing you the annual and annual mean and the summer mean and the winter mean precipitation. The colors showing the precipitation. And this yellow crosses represent the meridional location of the maximum precipitation in the tropics at each longitude. It's the ATCC location. And these blue lines here this part shows the zonal mean precipitation. The blue lines is just mean latitude of the maximum precipitation. It's the mean location of ATCC. The top panel is from sea open, the middle panel is from sea closed, and the bottom is their difference. So from their difference, there is no consistent trend. In the precipitation increase from sea open is seen in the equatorial Eastern Pacific regions. In terms of the ATCC location, we can see that it shifts northward when sea is opened. In addition to the mean latitude of the maximum precipitation, we also analyzed the other indices of the ATCC location shown in this table. Here is the latitude of the tropical precipitation maximum And also the latitude or tropical precipitation maximum in the northern hemisphere, southern hemisphere, the tropical precipitation centroid, and the approximate precipitation median. In this column, here is the mean latitude and of the maximum precipitation at each longitude. At each longitude, I just showed in the previous slide. So we just look at this maximum and the centroid median and mean value. We can see that the LECZ moved northward when the Canadian archipelago is opened, no matter it's annual mean or summer or winter. So you may ask why the LECZ shift northward when the sea is open. So we analyze the energy budget across the equator. Here, this figure shows the top panel shows the Hadley cell, the same function of atmospheric overturning circulation from sea open and sea closed, and also the zonal mean precipitation. This red line is just the boundary between the anti-clockwise and clockwise circulation. So from this red line, kind of see the sea is open, this LECZ location shift northwards. The bottom panel shows the northward heat transport from top atmosphere required ocean and atmosphere heat transport in the black, blue, and orange line. All the solid line indicate the sea open, and the dashed line is from closed sea experiments. So from this figure, we extract the annual mean heat transport across the equator. And from this table, you can see that the atmosphere heat transport across the equator in the open sea case is not southward, and the closed sea case is northward. This is why the when sea is open, the LECZ is in the shift northward in the northern hemisphere. So this southward atmosphere energy transfer across the equator when sea is open, it must be balanced by the more net TOA radiation in the northern hemisphere right to southern hemisphere, or it is balanced by more ocean heat transport, more northward ocean heat transport. So we first look at the top of atmosphere energy budget in the northern and southern hemisphere. So just to focus on the net TOA radiation, you can see that actually the southern hemisphere gain much more radiation relative to the northern hemisphere. So this indicates that this atmosphere and the more southward atmosphere heat transport when sea open, it must be balanced by more northward ocean heat transport when sea is open. So okay, I'll skip this one. So let's look at the annual mean northward ocean heat transport. Shown in this figure, the black line is from the Pacific Ocean, red line is from Atlantic Ocean, and the orange line is from the Indian Ocean. The solid lines is from sea open, and the dashed line is from sea closed case. So you can see that when a sea is open, this northward ocean heat transport in the Atlantic Ocean, the red line is increased, and the northward the ocean heat transport in the northern Pacific is decreased. So from this figure, we can see that the increase in the northward ocean heat transport when sea is open is mainly contributed by the Atlantic Ocean. So we know that the Atlantic Ocean heat transport is related to the meridional overturning circulation. So we analyzed the meridional overturning circulation. Here shows the Eulerian meridional circulation. The left one is total ocean, the middle one is Atlantic Ocean, and the right one is from Pacific Ocean. The top panel is from sea open case. Middle one is closed sea, and the bottom is the difference. So you can see that the Atlantic meridian overturning circulation is strengthened when sea is open. So why the AMOC is stronger in when sea is open is related to the increase in the formation of North Atlantic deep water. Here, just look at the Atlantic Ocean shown here. We can see that. I don't think they changed. My slide is something wrong here. Here, this panel is from the Atlantic Ocean. And you can see that when sea is open, the Atlantic surface and deep water much younger, so it means much more NADW is formed. So we further analyzed what controls the increase in NADW formation, and here I show you two transects. Let's look at the cross section. I don't have time, so maybe just look at the this one. Here shows the temperature, salinity, and potential density vertical profiles. So we can see that the temperature increased in the North Atlantic surface, subsurface water, and the salinity also increased. So the much more NADW is formed when sea is open is mainly contributed by salinity. Okay, here is from another transect. It has the similar results. So in summary, compared to the closed sea, the open sea immersing leads to an increase in the formation of NADW and consequently strengthen the AMOC. So the influence of this in the atmospheric energy transport across the equator moves further southward to compensate, resulting in a northward shift of ITCZ. Okay, thank you.
Hi, I noticed in one of your figures, it seemed like you were getting an active PMOC. Maybe
Yes.
it was in one of, was it the one with the closed strait? And that seems like a kind of a very interesting and remarkable feature. Did you look into that?
You mean here, right?
Yeah, on the right panel
Yes,
in the middle,
yes.
right?
Yes. I don't know why, but actually once when we change the C, when the C is open, once the A mark is changed, the P mark also changed.
Oh, so you don't really know why, but you did notice that. Thank you.
No problem. Okay, thank you.
Okay, so that brings us to our last formal talk of the session. We've got Sofia Makarevich. Sorry, I'm butchering everyone's name today. Okay, so now we'll be hearing about plants transforming Earth's environment. Should be exciting.
Hi, I'm a project scientist in the Paleo group at NCAR. This is the name of an annual review paper that I had the chance to contribute to during my postdoc at UC Davis, with all these collaborators with tons of variety of expertise about plants. So our group is motivated by this idea that we know vegetation exerts a really important control on climate in the modern day, but we also know that plants have evolved a ton throughout time. And so the links between how plant evolution has influenced or also responded to climate change is unclear as we move back in time. Earth system models are still the best tools we have to study the role of plants in the coupled Earth system and vegetation-climate interactions over time. And the way that Earth system models like CESM represents vegetation is generally in this way of modern plant functional types. So they're broad groups of modern functional groups of plants. And so if we had sort of an availability of plant functional types that represented different stages of plant evolution, then we could use those in our deep time paleoclimate simulations. But we don't have those available to us. So typically what we do is use a modern set of plant functional types that most closely represents the plants of interest. And so while this is probably a valid assumption back to a certain extent through time, maybe the whole Cenozoic, as you move further back in time where plant evolution is more and more different, this assumption that modern plant physiology and structure is a worthy assumption when it comes to plants in the past, it becomes less and less valid. And so our group has sort of used these 3 different tools to reconstruct time-appropriate vegetation-climate interactions through time. That's sort of our goal anyway. And so we use the fossil record, this ecosystem process model called Paleobgc, and also the community earth system model to do this. And so I'm sort of going to explain that general framework that we use to approach this problem. It's called the trait-based whole plant functional strategy, and that's a mouthful, but each component is necessary in this term. So basically the trait-based part is this idea that we can actually measure primary plant functional traits from fossilized materials. And so ideally, if you were to characterize something like plant water movement through a plant, you'd be able to look at fossilized components of the leaves, the seeds, the stem, the bark, and the roots, and infer the ways that water, for instance, moves through that plant. So for instance, you can actually measure the stomata on fossilized material in both the size and the number of them, and infer something like maximum theoretical stomatal conductance. And then another example is fossilized stems can be used to look at sort of those water conducting elements. So in this example, it's a tracheid, and you can look at pit area per tracheid to look at sort of the xylem limitations of water movement on that paleo plant. And so, of course, you can't look at any individual primary functional trait on a plant and infer whole plant performance, so you have to use models to integrate those functional traits. And so we use, the first kind of level of complexity we use is this model called Paleobgc. It's a process-based ecosystem model based on Biogeochemistry, but the cool thing about it is that the parameterizations in it are modified to use those primary functional traits from fossils. So far, I think the goal is to have every single organ of the plant represented, but for now, there's leaves and stems. And so if we're interested in something like plant water use, if we integrate all these different primary functional traits to an integrated plant functional trait like water use efficiency, we can sort of reconstruct the different water use strategies of all the paleo plants on a given landscape, if you have enough data to do so. So that's something that Paleobgc can provide. And then we can pull from modern ecological concepts like the CSR triangle to categorize these paleo plants on that spectrum. For instance, as a more competitive plant with fast resource use and growth, as opposed to a stress tolerator plant that's more drought tolerant and slow resource use and growth. And so, I'm going to kind of show you this general framework and how CESM comes into this process with this case study, the first paleotropical forests. So these forests dominated about 300 million years ago across the Paleotropics during the late Paleozoic Ice Age. These are like the iconic Carboniferous coal swamps. And so just for some additional context, they were across the paleolatitudes on the supercontinent Pangaea. And this kind of ecosystem is a really useful case study because these are some of the most well-studied plant fossil assemblages. So we have a relatively high amount of measurements of these plant fossils. And so here is sort of a schematic of the major paleo plants on that landscape. And let's say we were to look at the fossil record alone, we can actually kind of infer that certain plants like these lycopsid trees were more dominant in wetter environments based on the fossil record and geologic evidence. Whereas other plants like these cordytalians were more dominant in seasonally dry parts of the tropics. But if we actually want to kind of understand a more quantitative process-based reason why these plants were dominant in these different environments, we need modeling context. So in order to run something like Paleobgc that I talked about before, we need a CESM simulation, for instance, to provide time-appropriate atmospheric conditions. So I ran this simulation with this paleogeographic reconstruction of the late Pennsylvanian. And in this particular simulation, it was CLM4 and CAM5, and I used that traditional approach to modeling vegetation, which is choosing your closest living plant functional types available in the community land model and prescribing them across the surface. And in this simulation, I'm showing you this biome map on the right. It's a really simplified, sort of based on the fossil record, we can kind of extrapolate across the surface and say this general group of plants lived in this latitudinal range. And so it's the simplest way to sort of guess at where those plants are distributed. And using just that initial simulation, we can start to look at variation across the paleotropics in terms of precipitation regimes. So I'm showing you two examples here. On the left, it's the ancestral Rocky Mountains, and this is characterized by highly seasonal precipitation. So you get some of the highest precipitation amounts across the tropics for part of the year, and then for an extended amount of time, you get little to no precipitation. And then you go all the way over to Cathasia, that island in the sea, and you have relatively high amounts of precipitation throughout the year. So this is just two extremes in the paleotropics. And so if you use that information, you can take a model like Paleobgc, and you can run that model in every grid cell across the land surface for every paleo plant you're interested in. And you can come up with a map, an updated map of where these different paleo plants would have survived across the land surface. And so what we can see based on this map of kind of dominant LAI to show you what plants would have dominated is that in the ancestral Rocky Mountains, where it's relatively more seasonal in precipitation, you have kind of a mixture of those kind of wet adapted and dry adapted plants. Whereas over in Cathasia, you have a dominance of those wet adapted lycopsid trees. And the reason for that, which we have learned from Paleobgc, is that essentially you have sort of a stem adaptation where your stems in these dry adapted plants are more resistant to cavitation. So it's almost as if when there's no water availability, your stems are, resistant to failure. Whereas in a lycopsid plant that's more wet adapted, if there isn't moisture available, the plant's going to die. And so I hope I've shown you sort of the basic information transfer between these three components. And now I want to show you how we can build on that initial set. So now let's take that information we learned from Paleobgc and the fossil record and update our CESM simulations. So rather than just prescribing vegetation based on those broad latitudinal distributions, we can now use Paleobgc to kind of update where plants would have survived across the land surface. So you can see there's, in this sort of like zoomed in panel of the tropics, there's a lot more variation longitudinally in where you have a biome versus desert. And so I prescribe vegetation the same way in both simulations, but the main difference between the simulations is that now I have sort of my first set of paleo plant functional types. So on the right is sort of the closest modern plant functional types that would represent most of our paleotropical plants. So tropical broadleaf evergreen tree is the main one. And then on the left, we have kind of a preliminary set of paleo plant functional types where they differ in terms of a few different parameters. So specific leaf area, carbon to nitrogen ratio of the leaves, one other sort of stomatal conductance parameter, and that sort of differentiates all these plants based on the fossil record. And So kind of the initial sort of test is, does this kind of information we've gained from this process actually make a difference in our simulations? So what I'm just showing you now is an example of summer, or JJA in the Paleotropics, and this region with, let's see, can you see that? Oh yeah, regions with positive precipitation minus evaporation are actually the Pangean monsoon. And this area, so you can see kind of the southern edge of the Pangean monsoon below it. And essentially the difference just due to changing those paleoplant parameters is that those plants, the paleoplants, are more sensitive to low vapor pressure deficit. And that's because the emergent sort of property from changing those parameters was that there's lower stomatal resistance. And that kind of makes sense with some theories of evolution of plants being more kind of effective at managing resources through time. But that's kind of just a side note. So what this also shows is that in some regions, that kind of climate vegetation coupling is a lot stronger, and you get much larger differences due to these parameterizations. So like in Western Pangaea, you see a really large difference there, whereas over in Cathasia, you really don't see a large difference due to these changes in the parameters. And I think, like in this scenario, I prescribe the vegetation. So let's say I were to run a dynamic vegetation model with these plant types. In this region in particular, where you see a lot of drying with those paleoplant functional types, those are actually the competitor plants, which are high, low water use efficiency, high resource users. So if this was a dynamic configuration, you'd probably see a replacement of those competitors with the stress tolerator plants. And that kind of makes sense with the fossil record in Western Pangaea, for instance. So there's a lot more to talk about with it, and I'm happy to talk more about the details, but what I really just want to finish with is this general framework for approaching reconstructing vegetation-climate interactions in deep time. So I hope I've kind of shown you one case study of the different information transfer that can happen between these tools, and I hope you can see how this could be applied during other times in Earth history. And if you have any questions, please check out our annual review paper, published just last week.
So very interesting. Has Paleobgc, have they been using that for modern? Because we've often talked about, I mean, there are intraspecies trait variations. Ponderosa pine may be completely different, have different traits than loblolly pine, and yet they're the same PFT. So have the people who created Paleobgc, have they been using the TRI database of modern traits to develop that model? And has there been an attempt to sort of, I have not heard that within the CESM or within the CLM community yet, but to replace a traditional PFT approach with a trait-based approach, and eventually you could translate back to what the species or PFTs are.
I'll just say that the main person working with Paleobgc is Will Matthews. He's at Trinity College in Dublin. I don't think that he's applied Paleobgc to modern ecosystems, but I think the debate of are we representing vegetation, differences in vegetation properly with the current representation of plant functional types is a huge debate. And I don't know necessarily how this work speaks to modern differences in vegetation, but I think one thing that this work emphasizes is that when we think about previous vegetation, even there's a lot of instances where people use a nearest living relative to learn about the physiology of a plant in the past. And you can't necessarily make those linkages just on the relative of that plant in the past. I think it's a really interesting point about reevaluating plant functional types in the representation, but I don't have a good, yeah.
That you can't necessarily make that assumption, that PFT assumption.
First, before we get back into the discussion, let's just thank all our speakers again for all the talks we had. Excellent. Just as a reminder, I'm going to put our slides back up again. So the question is, do we, as a community, have thoughts on what our relative priorities should be between high-resolution simulations versus other types of things that might be used for those resources if we were to do coarser resolution simulations? To give people a chance to share their thoughts before we break. Oh yeah, thanks.
So Eric made a good point that in terms of mesoscale eddies and ocean heat transport and how they're parameterized in our models. So I'd like to come back to that and thinking of Monday's cross-working group. Can we use, we should encourage a cat informing the dog approach. So the ultra-high or the high-resolution models informing how we can improve parameterizations of mesoscale eddies or other things that we have to parameterize in the low resolution.
Are you talking about things like LES simulations or?
Well, I would just start with the IHASP type simulations. I think they capture much of the, the deformation radius in the ocean gets big in the in the lower latitudes, but at least in the higher latitudes, I think you're capturing what you need. The problem is it's kind of easier said than done because I don't really know, first of all, how long you would have to sort of run a high-resolution simulation like that. It'd be great if you could use the IHASP simulation, since there's already quite a bit of that, but then if you start changing basin geometries and other kinds of things, then I don't know that you can necessarily kind of extrapolate to that. I mean, maybe you can, I think there's, I think that, what's her name, Laura Zana is working on a machine learning approach where you train a coarse resolution parameterization using the high resolution eddies. And I guess, I don't know really how far along she's come with that. So maybe that would be one thing to look at.
So, like, what parameterization should we be using? Do we need to improve on them? Yeah.
Well, not machine learning, but I have been hearing about these backscatter algorithms in MOM6 where they have a negative viscosity parameter that reinjects energy into the large scale, and then they add a hyperviscosity to extract energy at the smallest scales. So maybe in CESM3, these innovations will be useful.
I want to add a point that for some of the application, maybe coarse resolution configuration is still our best tool. For example, if you want to look at long-term sea level change and ice sheet evolution, we clearly cannot run even 1 degree resolution coupled model for a very long time. So still we will have to rely on the large-scale dynamics provided by the coarser resolution model. Sometimes they are not, of course, they are not accurate, but for example, as you can see here in the talk shown today, if your ocean heat transport is off by some amount, that could be picked up by the atmosphere. So in the end, we may have some large-scale feature that's probably okay for some type of question we are looking into. Just some thoughts.
If I could just add to that, and maybe Marika could help me think about this. The difference I could see between putting the heat transport in the atmosphere and the ocean is what happens to the sea ice margin. So I would think those things would be the things that you would look out for, and then you could maybe design an experiment just to see if maybe you don't have to run so many years to figure out if there really is a difference like that matters whether it's the ocean or the atmosphere doing the transport.
Well, to answer to the question, I'm neither a paleoclimate dog nor a cat because I'm doing LES and I study convection and clouds. But I'm super interested in paleoclimate. That's why I'm here. I just want to say something that I'm doing LES and convection, which I usually use model at tens of meters or hundreds of meters, but I'm at CGD, which is developing coarse resolution model at like 25 kilometer or 100 kilometer. So I'm literally a cat in a dog environment. But I feel like there is actually a need for this type of bridge because what I try to do is to understand some of those processes in the atmosphere or in convection so that with that improved knowledge, we can improve the convection schemes in a much coarser resolution model. So I think that's like the benefit of having both like coarse and like high resolution model. And also in terms of how we can best leverage, I can see something about what we do in the convection community. Because previously we can only run model at 25 kilometer, which is not very good resolution to resolve those mesoscale convective systems. But now we actually have those global convection permitting model. What they can do best is actually to resolve those MCS systems. I think it really depends on what scale you're looking at and also the phenomenon that you're trying to resolve with the increasing model resolution. So I think that might also be true in the paleoclimate community. It really depends on like if the resolution becomes finer and you can actually resolve certain processes better, for example, the precipitation or the clouds better, and then possibly you can understand like the monsoon dynamics or monsoon precipitation much better or in some way. So I think like both models are very valuable, but for different purposes and at different scales of the phenomenon that you're interested in.
That. Yeah, so I'm hearing a lot of support for the kind of cat-informing dog strategies. And yeah, but like as a paleoclimate community, as people have also pointed out, we're in the situation where we need to test not only effects of parameterizations, but also how that interacts with boundary conditions. And so there's a lot of trade-offs in terms of resource time. So I guess I was curious if people had thoughts on how we partition the limited computational resources that we have available as a community.
I will also say the dog can inform the cat. So if you think we're starting to do more data assimilation in paleo. So if you run a low resolution model and then you use data to improve on, for example, your SSTs, then you could still run a high resolution if you're worried about continental processes with the variable resolution or just so. We can use the dog to inform the cat with newer developments now we're having in data assimilation.
Oh, yes.
I don't have a good answer for how to properly leverage the resources if we want to run, let's say, one high-resolution case and compare it with an ensemble of low-resolution simulations. But I guess one question that I've thought about a lot in terms of high-resolution and paleoclimate is how do we decide on we have to make a lot of choices in paleoclimate in terms of what boundary condition enforcing that you're using. Obviously, if you're studying the Carboniferous, that's very different than LGM. But something like aerosols and how you treat them in the model is relevant to any paleoclimate interval. So if anyone has thoughts on how do we use the dog, for instance, to inform the cat in terms of choosing that right set of boundary conditions and forcings to use in our paleoclimate simulations. another question.
Answer that. Yeah. Sure. Yeah.
I guess that brings up the question of whether the uncertainty in those forcings or boundary conditions are larger than the uncertainty in the model. I mean, the structural model uncertainty. So in terms of deciding whether the dog model is appropriate for the science questions, if the structural model uncertainty is much smaller than the boundary forcing uncertainty, that might be where you put your resources, right? So it's, yeah.
I guess I'm speaking from a perspective of person who did more of proxy data in paleoclimate studies. That it's obviously very difficult or expensive to do these high-resolution simulations. So perhaps the community should think about a strategy to better share these data sets and also train a larger group of the people to better utilize these simulations. And after more people are using these simulations and we are including more people, being more inclusive, then people like me who do proxy data will bring probably different perspectives and can help us better shape our future directions in terms of like what to be, a cat or dog or a combination of both.
Access came up a lot in previous days of the workshop too. Thoughts? No? Okay, well, we're almost at time, so I guess that was a pretty good closing comment, right? So maybe we need the dog informing the cat informing the dog, and everyone coming together to become better able to interpret what the dog and the cat are telling us. So yeah, great. Thanks so much for this discussion and all the excellent presentations, and yeah, I guess